winning this challenge. Let's check it out.
Thanks for the kind words, Blair. Team Sunslicer is thrilled to rank first place in the inaugural NASA Lunar Payload Challenge, especially in the company of two other exceptional teams in Pooley Space and Microrad. We're excited, over the moon you might say, in the possibility that Sunslicer, created in a Santa Rosa garage, may fly and validate 18 months of extreme commitment and sacrifice. I cannot thank enough my teammates Garrett Jernigan, John Doty, Brian Silverman, Vadim Gerasimov, and the countless volunteers, partner and sponsor companies for their tireless efforts. Please check out sunslicer.com for full credits and updates. And in the words of Ralph Cramden, to the moon, Alice.
I tell you what, Phil and his team did a really good job with Sunslicer. I mean, I'm looking forward to seeing that on the lunar surface one day.
Man, I can't imagine entering a contest like this and actually winning, knowing that, as you said, your technology, your creation might one day fly to the moon.
Yeah, we talked about this before with CubeSats. You know, can you imagine your resume at that point? You go like, I've done X, Y, and Z, but I also have a payload that's working on the moon. That's really cool.
And in addition to Sunslicer, we can't forget about the other teams that were in the competition.
Absolutely. And so when we were talking to the teams, we were talking to Tibor in Hungary, his whole team, which wasn't just there. They had team members in CERN, they had team members all over the place. The effort that went into this, and Christian, who was up at MIT, and his team, lots of hours, lots of creativity and innovation came together. And the good news, guys, and this is really important, that whether you win the competition or not, because of that testing that they've all gone through, each one of these payloads is flight ready and has the potential to fly to the moon. Good job, Hero X. Good job, game changing in NASA. It looks like we got a winning plan for the return to the moon with Artemis.
You're watching NASA Edge.
An inside and outside look at all things NASA.
With show-ready technology.
I found a flaw in your system.
Uh-oh.
It's not the scale, Franklin.
Yeah.
You notice that?
You're like taller than everybody.
Hold on a second.
Oh,
what do you think? Something like that?
Yeah,
that's more like it. Yeah,
it's more like it.
Yeah.
The mystery surrounding the whereabouts of a supermassive black hole has deepened. Despite searching with NASA's Chandra X-ray Observatory and Hubble Space Telescope, astronomers have no evidence that a distant black hole, estimated to weigh between 3 billion and 100 billion times the mass of the Sun, is anywhere to be found. This missing black hole should be in the enormous galaxy in the center of the galaxy cluster Abell 2261, which is located about 2.7 billion light-years from Earth. Nearly all large galaxies contain a supermassive black hole with a mass that is millions or billions of times that of the Sun in their centers. Since the mass of a central black hole usually tracks with the mass of the galaxy itself, astronomers expect the galaxy in the center of Abell 2261 contains a supermassive black hole that rivals the heft of some of the largest known black holes in the universe. Such black holes are usually found in the centers of galaxies. Using Chandra data obtained in 1999 and 2004, astronomers had already searched the center of Abell 2261's large central galaxy for signs of a supermassive black hole. They looked for material that has been superheated as it fell toward the black hole and produced X-rays, but did not detect such a source. In 2018, a team of scientists used Chandra to get new, longer observations obtained that year of Abell 2261. They also considered an alternative explanation. What if the black hole was ejected from the host galaxy's center? During a merger of two galaxies, which likely happened in the past to form Abell 2261, the central black holes in each galaxy could have merged to form one enormous black hole. This violent event would have also generated a huge amount of gravitational waves. If the gravitational waves were stronger in one direction than another, theory predicts that the new, even more massive black hole would have been sent careening away from the center of the galaxy in the opposite direction. This is called a recoiling black hole. Astronomers have not found definitive evidence for recoiling black holes, and they do not know whether supermassive black holes even get close enough to each other to produce gravitational waves and merge. The detection of recoiling supermassive black holes would embolden scientists using and developing observatories to detect gravitational waves from merging supermassive black holes. The mystery of this Titanic-sized black hole in Able 2261 therefore continues. Although this latest search was unsuccessful, hope remains for astronomers looking for this supermassive black hole in the future. Once the James Webb Space Telescope launches, astronomers should be able to use its capabilities to join with Chandra's and others to look at Able 2261 and others like it.
En la NASA, nuestro recurso más importante es nuestra gente.
Una fuerza laboral talentosa, diversa,
dedicada a estudiar los secretos del universo y de nuestro planeta natal.
Para el beneficio de la humanidad.
La comunidad hispana contribuye a diario a misiones esenciales de la agencia.
Trabajando para mantener seguros a nuestros astronautas y misiones en órbita.
Monitoreando los efectos de cambios climáticos.
Prediciendo eventos meteorológicos que pueden afectar a nuestras comunidades.
Ayudando a la respuesta en desastres.
Diseñando los aviones de tecnología sostenible del futuro.
Desarrollando ciencia y tecnología a bordo de la Estación Espacial Internacional.
Desentrañando los orígenes del universo.
Buscando señales de vida antigua en otros planetas.
¡Hemos llegado! Perseverance llegó y preparándonos para llevar a la primera mujer y a la primera persona de color a la Luna.
Nuestra diversidad de orígenes y culturas impulsa nuestra capacidad para innovar.
Y hace que nuestra agencia sea más fuerte, incluyente y diversa.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos NASA.
Sigue nuestras historias en NASA en español.
Imagine living in a modern metropolis full of opportunities, endless sunshine, Hollywood celebrities, and fancy cars. That was the American dream. That was Los Angeles in the early 1940s. But in the morning of July 26, 1943, in the middle of World War II, the sun didn't rise over the city. A throat-burning noxious gas covered the sky. Entire city blocks faded away. A thick fog that made people's eyes sting and their noses run had taken hold of the city. They were under attack. Or so they thought at the time. But the attack didn't come from the outside. Massive wartime production facilities, a high increase in population, and the exhaust fumes of cars, combined with the geography of the valley, made the city a trap for air pollution. The day after the first event, city officials tried to control the damage by restricting emissions from power plants and industry. But while these efforts help reduce air pollution, smog episodes continue to occur. Scientists discovered that volatile compounds, like the gases produced due to evaporation of gasoline during the refining process, and nitrogen oxides generated during the combustion inside car engines, both reacted with sunlight, creating a highly toxic gas, ozone. And sunlight isn't precisely something Southern California lacks. But this wasn't a localized phenomenon. Other U.S. cities also experienced high ozone concentration levels. These cases made society aware of the importance of keeping track of emissions and lead politicians to implement policies to improve the quality of the air we all breathe.
Air quality is a serious global problem. More than 7 million people die per year due to the effects of air quality.
There's many economies around the world that are growing, and what the United States has seen is that your economy can still grow while your air pollution levels are decreasing, but it takes some effort to do that. The good news is that air pollution levels around the world are gradually decreasing.
In fact, air quality trends have improved in the last decade as a result of policies developed to reduce air pollution.
Back in the 1950s, Los Angeles had a really awful air quality problem.
So when the Clean Air Act began, it was a commitment to cleaning up the air. But the actual legislation and the differences took a long time to put into place. And so here in Asia, we're at the beginning of that process.
These nations that are still increasing in their standard of living and increasing in their pollution levels can learn from what's happened in the industrialized nations. We can have a more rapid decrease in pollution levels.
Now we know how to put together effective policies to control air quality.
Understanding that economic growth and industrial development bring air quality problems and knowing how to deal with it in the future is vital for us to keep progressing as a society. Now we have better tools, better technology, and more knowledge. We can act faster and more efficiently to address pollution issues.
Chorus AQ is an international cooperative field campaign between NASA and the Korean National Institute for Environmental Research.
The Ministry of Environment of Korea has put in a great deal of effort into improving air quality.
By working with our Korean colleagues, we've been able to design a campaign that is very specific to their knowledge of the air quality problem from the past decades.
Joint venture with NASA has provided us with many research opportunities.
The air in our planet does not know of national borders or countries. A worldwide effort is needed so that what we do in the name of progress does not have a negative impact on our health and helps preserve the only home we know, Earth.
Chorus AQ combines satellite-type observations with ground observations and airborne observations to create the most complete picture of air quality we've ever created.
Explore with us. Take a deep breath and join us on an expedition that will investigate a major public health problem, air pollution.
One of the difficulties in understanding air quality is that the pollution that affects your health the most is not the initial component put into the atmosphere.
Under certain atmospheric conditions, some of these pollutants react with each other and produce new harmful agents like ozone.
There's 3 key ingredients to make ozone: NOx, hydrocarbons, and sunlight.
So think of ozone as an important cleansing agent from the atmosphere. When you have a big stain to clean, you use a lot of cleanser. And when you create a lot of pollution, a lot of ozone becomes evident in the atmosphere. That's helping to clean the atmosphere, but it's also impacting our health. We have primary pollutants. Nitrogen oxides and reactive hydrocarbons are most important in the formation of ozone.
Your car emits both NOx and hydrocarbons are unburned fuel.
But the ozone itself comes from the chemistry, so we call it a secondary pollutant because it results from the chemistry that occurs after the emission of the nitrogen oxides and the reactive hydrocarbons.
When nitrogen oxides and hydrocarbons react with sunlight, they produce a harmful secondary pollutant, ozone. But wait, isn't ozone good for us? Well, it depends.
The role of ozone in the atmosphere is quite complex. In the stratosphere, ozone is a great benefit because it protects us from UV radiation. In the lower atmosphere, ozone is also a benefit because it's responsible for initiating the chemistry that cleanses the pollution out. But when pollution levels are very high, the chemistry runs amok and you create very high levels of ozone. And those ozone levels can become so high that they become reactive with our own body tissues and become a problem in terms of health.
Photochemical smog is considered to be a problem of modern industrialization. It is present in all modern cities, but it is more common in cities with sunny, warm, dry climates and a large number of motor vehicles. It can also affect rural areas, where agriculture, trees, and forest fires can release a considerable amount of volatile organic compounds, or VOCs.
What are the sources of VOCs? Well, we have just the evaporation of gasoline when you're filling your tank, petrochemical plants, the refineries that are making gasoline for us from oil, and also the plastic companies that are making plastics, polyethylene, polypropylene.
In terms of reactive nitrogen, man's activity far outpaces the natural sources, and so we can say that when nitrogen oxides are present, that's man. When you talk about reactive hydrocarbons, actually vegetation plays a major global role in creating them.
Trees can emit that pine tree smell you smell, but also a lot of the deciduous trees are emitting isoprene. Isoprene is very reactive and very good at making both particles and ozone.
But fortunately, they create very specific molecules, and when man creates pollution, it creates a different chemical mix. And so we can look at the constituents of the reactive hydrocarbons to determine whether it's nature or whether it's man.
But because these compounds travel with the wind, they can affect different parts of the world. Recently, scientists from other airborne campaigns were able to trace the origin of unusual high levels of ozone in the air above the western Pacific Ocean. They found that they were linked to the organic compounds released by forest fires in Southeast Asia and Africa, half a world away.
The atmosphere is a shared resource, and we're seeing more and more that the entire northern hemisphere is suffering from pollution background levels that are due to all of us, not just one.
Everyone living in a big city around the world is breathing polluted air, and it is having an impact.
It's part of the tug of war between progress and the price that we pay for that progress. And so that balance needs to be maintained into the future as we continue to develop economically, develop technologically. We have to pay attention to how that's impacting the air quality.
Our world is an interconnected system, and the impact of air pollution goes beyond the air we breathe.
All of the processes that are emitting and causing air pollution are also putting CO2 into the atmosphere, causing climate change, global warming.
It also affects our soils, our glaciers, our oceans, our climate.
And this is a problem that's going to affect our children and our grandchildren. So it's very selfish of us to ignore this long-term problem that is created by us.
In a laboratory setting, you can artificially control different parts of the problem, so each effect can be isolated. That's hard to find in nature.
Seoul, South Korea. A megacity with over 25 million people and a population density which is almost twice that of New York and 8 times greater than Rome. Despite being a modern and massive megacity, South Korea still counts with many forests and rural farming communities throughout the country. But why is South Korea an ideal natural laboratory to carry out air quality studies?
We have a bunch of factors. We have a very large city, a mega city, the 4th largest city on the planet, with lots of cars, lots of power plants. And then downwind from that, we have a forest. So we have the urban plume reacting with the natural emissions from the forest.
This is a perfect place on the globe to try to understand how the mixture between man's emissions and nature's emissions can create poor air quality.
Air pollution is an important environmental problem in modern societies. The rapid growth of new economies and industries in developing countries makes it very difficult to address environmental issues.
Korea has been developed very quickly after the Korean War. Actually, economic success gave us lots of benefits to the people. However, this also brought many environmental issues, including air quality.
So general public has been known about the yellow dust issue before, and in recent they start to learn about the fine particle issues and ozone issues. They're starting to pay their attention to those newer issues emerging to our society.
Korean government has been making persistent effort to improve air quality. We participate in this project as though understanding of current situation with aerial, ground, ship, on the top of current simple ground observation, crucial in future improving air quality.
We are definitely pay attention to solve this issue, and general public wants to know how we can actually achieve that goal.
Developing effective strategies to balance the economic growth and the good health of the population is key to continue growing and prospering as a society.
Unfortunately, policy always lags emissions, and so it usually takes time to understand what's causing the poor air quality, and then regulations can take effect.
It's a tough problem. We haven't solved it completely in the U.S. But here, I think you're right. We're learning a lot more about the specific sources in this area so that here locally the government can decide what's the most effective strategies to use, because we don't want to hinder economic development. We just want to know what are the smartest choices you can make so you get the best bang for the buck.
In the United States and in Europe, this has taken place over a long period of time. Things in Asia are growing very rapidly, and so we're in the middle of that process.
But the difference is that now, with our knowledge and technology, we are better prepared to address these complex environmental issues.
In these days, many countries in East Asia have been developing very quickly as well. Course AQ mission makes people aware of the seriousness of current air pollution.
So we are thinking, based on this mission, more general understanding, getting better and better, and eventually we can find something to actually reflect to the strategy.
Chorus AQ mission results will help develop improved ways to assess this challenging task.
Current investigation will definitely help us gain deep understanding of air pollution phenomenon in global scale.
This is a lab. Measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab. But maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA but from many universities and other government labs and organizations. And together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The Chorus AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the Chorus AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or LiDARs, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure air quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to connect what the satellite sees with what's at ground level.
Chorus AQ has in its team 2 smaller aircraft equipped with atmospheric chemistry measuring instrumentation. A King Air from NASA Langley Research Center and a King Air provided to the Korean National Institute for Environmental Research by Hanseo University.
The Hanseo King Air aircraft is relatively smaller than DC-8 in NASA. It can freely access source of pollution and measure air quality capital territory that cannot approach using DC-8.
Working all together, scientists from the Chorus AQ campaign will provide valuable data and test the technologies needed to better understand air quality and the flow of pollutants within our atmosphere.
We can only fly the planes for a very short period, but the details that you get from the aircraft help inform the observations from space and from the ground and how models can interpret those observations.
From this mission, we'll have better models and better mission data for Asia, and so we'll be able to extend the usefulness of this well beyond South Korea to other developing cities around the world.
We have the tools to study our atmosphere. Now, let's go exploring.
there's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It'll take us 3 years to make the rocket and only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today, and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the North and South poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Chelmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish if we can.
This is IceCat. It's been very quiet, very difficult to launch.
Do you think we're gonna launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
Imagine you are on the moon. Your job for the next 8 hours will be exploring, traversing up and down lunar hills, sampling rocks, and setting up equipment. Temperatures can reach a blistering 250 degrees Fahrenheit. Luckily, you have a portable life support system, a backpack that provides oxygen, water, power, and, for the excruciating temperatures, a cooling system. Under the Artemis program, NASA and its partners are planning to return astronauts to the moon, and the agency is testing new spacesuit technologies. As a new age of exploration heats up, engineers are looking to improve how to keep astronauts cool in space. Outside the International Space Station, astronauts perform extravehicular activities, EVAs, also known as spacewalks. During the Apollo era, spacewalks took place on the lunar surface, and with the Artemis program, humankind will once again return to live and work in the harsh environment of the moon. Future plans call for spacewalks to last longer and be more demanding, not just on the astronauts, but also on the spacesuits and systems that protect them and keep them alive and healthy. NASA has been working on advanced technologies needed for next-generation spacesuits. NASA's reference design, the Exploration Extravehicular Mobility Unit, or the XEMU, features greater mobility, visibility, and flexibility. This prototype is just the beginning. To meet the needs of future exploration as part of the Artemis program, NASA will share its newest designs, research, and data with commercial industry, whom NASA will partner with to build the next-generation spacesuit. It is an effort that will benefit from NASA's most recent studies and the agency's 50-plus years of spacewalk experience. Spacesuits are essentially a spacecraft made for one. They have many important life-preserving components, but none is more complex than the system to regulate the temperature of the astronaut. Engineers call this cooling system the thermal control loop.
The thermal control loop is part of the portable life support system, or the backpack that the astronaut wears when they do an EVA. The thermal control loop is designed to keep the astronauts cool. When the astronauts are doing spacewalks, they can be exposed to extreme temperature swings, say up to 250 degrees Fahrenheit. The thermal control loop is part of a system that consists of a liquid cooling ventilation garment, or LCVG, that the astronauts wear under the spacesuit. It consists of tubes that are filled with water that circulate from water pumps in the backpack to keep the astronauts cool.
During the Gemini program, engineers realized that astronauts not only needed protection from the temperatures of space, but also from the heat generated inside the suit, from their own bodies as they worked. Originally, the suit designers thought that airflow over the astronaut's body would keep temperatures regulated. What they discovered was that air cooling in a spacesuit is insufficient to do that job. During the Apollo era, it was decided running cool water through a garment that covers the body could help keep the astronauts from overheating. The means of cooling the astronaut was now an essential life-sustaining element to the spacesuit and was here to stay. The spacesuit currently in use on the space station, developed in the 1970s, also uses a water-cooled garment. Circulating water is still the best way to cool an astronaut. However, improvements can be made on how to move that water through the system, using new technologies and materials to test how to make the essential cooling system safer and more reliable than ever before. The result of this research is SERFI, the Spacesuit Evaporation Rejection Flight Experiment, all the critical elements of a spacesuit cooling system in one box. 2 SERFI units have been built, one to work here on Earth in our gravity, and another SERFI unit meant to be tested in the absence of gravity, in space. On board the International Space Station, astronauts take advantage of the microgravity environment to perform a variety of science experiments and to test exploration technologies. When engineers developed the spacesuits for the Apollo and Space Shuttle eras, NASA did not have a space station in operation. Today, the station presents a perfect platform for engineers to use microgravity to put the SERFI cooling system to the test.
In that experiment, we will test a couple different versions of the water pump that will be used to circulate the water through the system. We'll test temperature sensors, we'll test pressure sensors, integrate all those into one little package and test them for long duration to see how they'll perform over the expected life of a spacesuit.
SERFI shows how the water will move through the system as if it were inside a spacesuit, cooling the astronaut. But a spacesuit cooling system needs to do more than just circulate water. As the astronaut works, their body generates heat, which is transferred into the liquid cooling and ventilation garment. A thermal control loop needs a way to remove the heat from the water that is circulating through the system. That's where SWIMMY comes in, the spacesuit water membrane evaporator.
SWIMMY consists of some porous hollow fiber membranes that are contained in a metal manifold. When warm water flows through the porous membranes and then is exhausted into space, the cool water continues through the porous fibers and continues to flow through the LCVG liquid ventilation garment to cool the astronaut.
With the means to run a cooling system and offload heat and gases, the SURFI unit runs for 8 hours at a time, the span of what a spacewalk might last in space or on the moon. The tests are run again and again, simulating the rigors of what a spacesuit thermal control loop might encounter during its life cycle. Astronauts take water samples from SURFI for analysis. Just as a spacesuit might sit in storage for a time between spacewalks, like during a trip to the moon or Mars, SURFI is sometimes switched off. This time of dormancy is when contaminants can grow in the system.
That's when the bugs, the microbes, grow in the water system. And those little guys grow and they reproduce and they can grow through the system. They'll clog your filters, and once your filters get clogged, the water stops flowing.
When the water stops flowing, the suit stops cooling. Contaminants in the water are such a problem for current spacesuits that astronauts set aside time for regular water maintenance chores every 90 days. The SURFI tests hope to demonstrate that new technologies and materials will be far more robust in working through water contamination issues, reducing the risk of the cooling loop failing.
We don't want to have to worry about water quality. We want to be able, we've joked among the team, we want to be able to pour chicken soup into the exploration EMU and it'll still run the way it's supposed to run. Even if there's microbes in there that the system doesn't care. So we want the filters to catch the microbes, and if the filters don't catch the microbes and they flow through the pumps don't even notice the microbes or the contamination or whatever's in the water. They keep operating the way they're supposed to operate. We want our crews to be spending their time exploring, not running maintenance procedures on our spacesuits.
All the testing for SURFI in space is duplicated on Earth, with a twin SURFI running in 1G, Earth's gravity. By testing here and simultaneously testing in the microgravity of the space station, engineers can infer how the cooling unit will run in the 1/6 gravity of the Moon, the 1/3 gravity of Mars, and all points in between. The knowledge gained from building and testing the twin SURFI units is already paying off, as work is underway building a full-size backpack for NASA's prototype exploration spacesuit.
How's it going to perform in microgravity? Well, by sending SURFI to space station, we can actually test how it's going to perform in microgravity. That in itself buys down the risk. So now there's one less unknown that we have to worry about when we send our hardware off to do what it's supposed to do.
I am so excited that SURFI, SWIMMY is on orbit, that we're working great, our ground unit is working great. SURFI has made a difference. We've had engineers, scientists, thermal analysis, water experts. It's been an exciting multi-discipline collaboration.
It's a collaboration that will inform spacesuit technologies for the Moon and beyond. A new design for a thermal control loop and its ability to help regulate temperatures for astronauts during exploration can benefit from the data gathered from SURFI, making it one cool little experiment.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold like origami to fit inside the rocket fairing. And this brings us to our most challenging part of this mission, unfolding it in space.
This thing got.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you. Shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
Two weeks. That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers of approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2/1000ths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy aside. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sun shield release mechanisms need to fire on cue. 107! They free the 5 sun shield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything. We can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Flight loads is a crucial discipline. It is one of the areas that requires a good combination of both science and art. We often say that every airplane that we have ultimately goes through the loads lab.
In 1964, a new building was rising from the desert shore of Rogers Dry Lake. The tests this laboratory has conducted over the past 50 years have supported almost every type of vehicle the aerospace industry has to offer.
We do a lot of testing in the laboratories to make sure that components are going to withstand the environments that they will see.
Every time we go away from a standard configuration on a vehicle, it changes the loads, and we've got to understand how that affects the forces and stresses and things going on within the airplane.
We in the Flight Loads Lab have been interested in thermal testing for many years.
These specimens are being exposed to temperatures from 400 degrees to 1,000 degrees Fahrenheit.
In order to precisely calibrate the thermal effects on the strain gauges, ground heating tests were conducted.
Also, over the years, there's been low temperature testing using cryogenic cooling capability.
A cooling system was used to lower the glove temperature to the minus 30 degree Fahrenheit pre-launch condition. The heating and cooling systems work together to bring the entire glove to cold soak condition.
The type of loads that a wing will experience in flight are bending loads, torsion loads, and shear loads. They're loads that are applied to the wings as a result of the air loads that are put onto the airplane when it's flying or when it's maneuvering.
How far can we push it? Where is it going to fail and how is it going to fail? So this work here has really been key to being able to help us anchor the models that we're developing to analyze the performance of these structures and also to take that next step and optimize the design of these systems.
The second HIMAT aircraft underwent extensive ground vibration testing after its delivery to the UL Dryden Flight Research Center.
Any aircraft in flight has resonant modes which occur as its structure flexes under aerodynamic loads. These flexures can become rapid and large. Under extreme conditions, they may even result in structural failure.
In Dryden's Flight Loads Research Facility, mechanical vibrators are attached to portions of the aircraft structure. As the aircraft structure is excited at known amplitudes and frequencies, its mechanical responses are carefully measured and tabulated.
So we're trying to understand how the airplane rings, basically like a bell.
You actually want to see the structural characteristics and how it behaves. Once you go and fly it, if you experience any flutter or dangerous vibration motions, then it's practically too late.
We can tell if the structure is sound.
With all this data, we'll be able to update our models, which will be used in our flutter analysis to validate that we are good and can give flight clearance for the vehicle.
Inertia testing, understanding basically how the mass is distributed around a vehicle, which gets important for the control laws.
The moment of inertia essentially tells us the angular momentum properties of the vehicle. We want to understand during flight, when we're trying to control it, how it pitches up and down, we'll understand how much resistance and inertia happens during those pitching maneuvers.
We need to know for certain that our sensors are behaving properly so that when we put them on our structures or put them on our vehicles, we actually believe the data that's coming off.
Not only test a large test article, but to bring in some new test techniques like the FOSS and really calibrate that against more traditional strain measurements and the finite element modeling.
The Flight Loads Lab here at NASA Armstrong performs some of the most sophisticated tests that I've seen on vehicles, flight vehicles as well as entry vehicles.
This facility is not only very unique, but it's a national treasure.
All engine 50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible. Very pretty out here. Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off-planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
and more in testing,
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next-generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
an orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits
It will balance between the Earth and Moon's gravity.
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the Moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The Moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we're building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the Moon and on to Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the Moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going. We are going. We're going.
I call it the 10% rule. You got to be 10% smarter than the thing you're trying to operate. My name is Greg Cormouche, and I'm here to test rockets. We supply helium, air, nitrogen, and hydrogen so that they can use them while they're testing the rocket engines on the big stands. We have 4 compressors. Each compressor puts out 400 standard cubic feet per minute, and we send that to the test site. I'm a mechanical engineer. I did a lot of mechanical things besides go to college. I mean, I worked on my own cars, heating and air conditioning work. I was familiar with electricity. The first time I walked out on the engine deck and looked at a space shuttle main engine, I said, man, it was overwhelming, you know. Eventually, you know, you stick to it, and I was able to pick it up. The folks that work here are awesome. There's a wonderful group of men and women who keep this place up and running. When you're here as much time as we are, this place is like family. Being a part of the SLS program it's a life event, you know. This is going to be the culmination of all that hard work that everybody put in years ago.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
Our world is full of new and exciting inventions that continue to push the boundaries of technology forward. Every day, it seems something new is announced, developed, and implemented that changes how humans interact. Just in the past few decades, cell phones, internet speed, medical breakthroughs, and the reinvention of basic infrastructure is beginning to change the norms in our everyday lives. But have you considered how these changes in science, engineering, and medicine occur? To most of us, on the outside of these revolutionary practices, it seems like magic when innovations appear in our lives overnight. In reality, it's years of painstaking work, trial and error, and rigorous testing that occurs before a finished product is ever realized. Researchers in the world of engineering and science move in small incremental steps, slowly building a case for these new revelations until they are sure technologies are ready to be shared with the world. In fact, there is an old saying in research, quote, "An amateur works on a task until they get it right. but a professional works on a task until they can't get it wrong," end quote. Fortunately for all of us, over the past few years, NASA, the FAA, and industry have been engineering the next big idea that may completely change how we interact in our world with the implementation of unmanned aircraft. The idea for inclusion of these aircraft is not new. The basic concept for small flying vehicles has been in popular culture and in the limelight for quite some time. But until recently, these vehicles have rapidly accelerated off the drawing board and into the skies. Over the past few years, NASA has been testing and validating research associated with unmanned aircraft through a project called Unmanned Aircraft System Integration in the National Airspace System, or UAS in the NAS project. This project spanned several years and addressed many of the early concerns of how unmanned aircraft would be integrated into our national airspace. After years of study, the UAS in the NAS project has tackled many of the early concerns. But one last big hurdle remains: to successfully demonstrate how unmanned aircraft will work in harmony within the national airspace. With this in mind, the final phase of testing, called the Systems Integration and Operationalization Demonstration Activity, or SIO, has begun in earnest. Throughout our country, at various NASA field centers and other testing locations, NASA has assembled a core strategic group of researchers to analyze and test unmanned aircraft through the SIO demonstration. Some of the key flight activities will include using various sized unmanned aircraft built by 3 different companies to highlight commercial UAS missions that have the potential to provide economic and public benefit to the American people. Throughout the testing, NASA plans to document best practices and lessons learned from the SIO activity and provide it to the UAS community to prepare us for routine commercial unmanned aircraft operations in our communities. On this episode of NASA X, we will take a look back at years of testing and development that have led up to the SIO demonstration flights, and we'll meet the companies that are helping to make these flights happen. This research and engineering has the potential to influence a massive shift in how we receive products and services, and may ultimately make an impact on how people travel and interact in our world. To understand why the NASA team has set up the SIO demonstrations, we first have to look at why integrating unmanned aircraft into the NAS is such a Herculean effort. Here in the United States, we arguably have the best air traffic management system in the entire world. During normal times, around 50,000 flights take off and land daily, with nearly 3 million airline passengers traveling across the more than 29 million square miles that make up the U.S. national airspace system. In that system, close to 15,000 air traffic controllers, 4,500 aviation safety inspectors, and 5,800 technicians operate and maintain services for our National Airspace System, or NAS. It has more than 19,000 airports and 600 air traffic control facilities. In all, there are 41,000 NAS operational facilities and over 71,000 pieces of equipment, ranging from radar systems to communication relay stations. With all of this infrastructure, integrating unmanned aircraft systems into the NAS will be demanding, to say the least. But this integration is of vital importance to our country, because these new vehicles will be part of the next revolution in national security and defense, emergency management, science, and in commercial applications. For these reasons and more, NASA set out in 2009 to work on several main objectives for the project that included providing research findings that utilized simulation and flight tests, supporting the development and validation of detect and avoid and command and control technologies, and finally, the SIO demonstrations themselves. Two of the biggest challenges that needed solutions before the SIO demonstrations could take place was in the key areas of detect and avoid and command and control. For detect and avoid, One of the primary safety concerns with integrating these new systems is the inability of remote operators to see and avoid other aircraft. On all flights with pilots on board, the FAA requires the crew to be aware of all other surrounding aircraft, either visually or using onboard instrumentation. So in addition to instruments, the pilot physically looks out of the window to help safely avoid other aircraft. Because unmanned aircraft literally don't have a pilot on board, NASA and its partners worked on concepts and designs that allowed safe operation within the national airspace.
What detect and avoid is since the pilot for an unmanned aircraft is either remote off the aircraft or not there at all in the case of an autonomous aircraft, there is no human eyeball to go see other aircraft. So the technology needs to be developed to use other means such as radars or cameras to be able to detect where other aircraft are flying in the proximity of your aircraft, your unmanned aircraft, and then be able to somehow, like a pilot would, avoid those other aircraft. And the way that's done is through developing some mathematical algorithms to be able to direct the aircraft to a location that would be safe. And so that's the kind of research that NASA wanted to focus on, because that was the most critical aspect of how to safely integrate unmanned aircraft into the national airspace that industry writ large could not really understand.
The second hurdle was with command and control. Because unmanned aircraft are completely different from crewed aircraft, new techniques needed to be developed, including improving the avionics on board the UAS and on the ground. These aircraft must have reliable, safe, and secure data connections at all times while operating in the complex environment of controlled airspace.
Similarly, the command and control part of the UAS and the NEST project is based on the fact that most radio communications that are operated in the airspace now with pilots are voice communication. So it's a pilot talking to an air traffic controller or talking to other pilots, and they use voice to do that. Well, so the aviation spectrum that's been set aside for voice control doesn't work for an electronic control, because if you're going to control the aircraft through some sort of communication methodology, it's got to be done electronically, because you're sending a message to the aircraft to be able to turn or to be able to climb or descend, etc. And so, so the technology that NASA worked on was to develop a radio that could be used in that bandwidth, that spectrum bandwidth, to be able to send electronic messages to and from the vehicle, and thus be able to command the vehicle. So that's why the command and control work that's been done under the UAS and the NAS project is so important.
Over the years, researchers time and time again showed that they had developed the detect and avoid and command and control technology to the point where it could be reliably tested in real-world conditions. Although there were other flight demonstrations throughout this project, the last major hurdle of flying the SIO demonstrations is now at hand. NASA, in partnership with the FAA and industry partners, have begun the demonstrations of potential commercial applications using different sizes of unmanned aircraft systems for the SIO demonstrations. The goal of SIO is to work toward commercial UAS operations in the NAS. In order to accomplish this goal, NASA has partnered with 3 pioneering companies to conduct flight demonstrations in the NAS that emulate commercial missions and begin working toward Federal Aviation Administration or FAA type certification.
When NASA was selecting the partners for SIO, we went through a partnership process that included the evaluation of a number of candidate partners. And we were looking for some key aspects that these partners could bring to the table. And so the first was really great domain knowledge in unmanned aircraft and associated technologies. The second attribute was knowledge of certification and the knowledge that's really needed to kind of take these vehicles from the concept and early development stages through to becoming a commercial product. And then the third thing we were looking for are viable commercial missions that would be publicly beneficial. We really wanted to showcase how unmanned aircraft can play a role in the future of the world and have a positive impact. There's 3 different companies that are participating in the SIO activity: Bell, General Atomics, Aeronautical Systems, and AATI. Bell is bringing their AP-70 unmanned aircraft, which weighs approximately 300 pounds and is capable of vertical takeoff and landing and operations around urban areas. The primary mission that they're focused on is emergency medical supply transportation in an urban area. General Atomics is utilizing their Sky Guardian unmanned aircraft for multimodal long-endurance infrastructure inspection. That unmanned aircraft weighs approximately 12,000 pounds, so it's much bigger than the others that are participating in SIO, and is intended for an infrastructure inspection mission at altitudes above 10,000 feet. AATI is using their AI Ranger unmanned aircraft, which weighs approximately 180 pounds, for a pipeline inspection mission at lower altitudes between 1,000 and 5,000 feet. And then lastly, throughout this process, we've been collaborating with the FAA, who has provided extraordinary support and helped us to navigate the regulatory process that's in place for these demonstration activities.
The 3 partner companies are each using various sized and different types of unmanned aircraft configured for the SIO demonstrations.
Over the past several years, actually going back probably a couple decades, NASA's been working on UAS, first more in the technical side and now maybe more on the standard side. And I think the SIO activity was looking, or the objective was to address some of the gaps that still remain. And one of the ways that we were able to do that is by partnering with some companies to go after some of these things. The outcome of the demonstrations is to try to help the companies really get their arms around some of these barriers that still exist, work with the FAA to develop the processes, the solutions to be able to address some of these gaps, and then bring it to a place where the industry can learn off of those lessons. The aircraft that are participating in the SIO activity are really pretty unique, and they span quite a range. You've got airplanes that have propulsion systems that are all electric. You've got a turboprop. Another one is a piston powered. So from a propulsion side, they're pretty distinct. And then even if you look at the way that they just operate, you know, one takes off like a conventional airplane would take off from a commercial airport. Another one can basically launch off of almost anywhere and just land on some clearing. And then another one actually can take off also from anywhere, just vertically, and again landing vertically. So quite a range, even in altitudes, the way that they operate. Some of them were designed to operate at lower altitudes. Some of them were designed to be able to go pretty high, even maybe 40,000 feet.
Each company offers a unique perspective and engineering goal in performing the SIO tests.
So Bell's participation in NASA SIO is really about making sure we get the data that the regulators need to be able to understand not just the aircraft requirements, but the system environments for being able to get advanced aerial mobility actually into commercial space, integrated with the rest of aviation in the national airspace. Bell's actually been doing unmanned aerial vehicles for quite some time. From a commercial standpoint, APT is, a sizable vehicle, a little over 300 pounds, carries 70 pounds of payload. It's critical that we get this right so that we are safe and compliant in the airspace, and that's a part of what NASA SIO is about. They're a trusted data provider for the FAA and other regulators to be able to help us understand what really is required for the aircraft, for the airspace requirements, and then for the integration of those systems together. So NASA's involvement helps drive the technology to a high enough level that we have sufficient data for the FAA to make regulations. I would say the way it's being done right now is innovative. You see, NASA leaning forward with electric and hybrid propulsion, as well as, detect and avoid, and some of the things that we need for the airspace. You see the FAA leaning forward based on their small unmanned experience and knowing that we need to get out in front of this time to make sure that we do it right as we get to larger vehicles. And so that partnership and kind of active arrangement of let's discover together and work together towards what's both safe and economically viable viable as an overall community is really new.
On this particular mission, the APT-70 was armed from a ground control station, then was instructed to initiate a vertical takeoff. Per its design, it then rotated to fly on its wings, where it was nearly silent to the researchers below. It flew at an altitude of 500 feet above ground level, transitioned in and out of Class B airspace, all while staying in constant communication with the ground station through a redundant data link. On board was the prototype airborne detect and avoid system that provided the remote pilot with awareness of air traffic in the vicinity and recommended flight maneuvers. Initial results were promising, with more validation and testing to continue in the future. Another partner, General Atomics Aeronautical Systems Inc., or GA, flew their Sky Guardian aircraft. It had been used for unmanned missions for many years, totaling more than 6 million flight hours. For this NASA mission, a demo aircraft piloted remotely from California flew for 9 hours from its Gray Butte Flight Operations Facility near Palmdale, California, to Yuma, Arizona. Data was collected from the detect and avoid system to provide situational awareness of air traffic near the Sky Guardian. This system includes a traffic alert and collision avoidance system used in manned aircraft, which fly in civil airspace, and air-to-air radar to detect and track nearby aircraft that may not have active transponders. The particular aircraft in this test may provide services that include hundreds of miles of inspections of rail, power line, communication and canal infrastructure, agriculture monitoring and topological surveys, as well as wildfire and flood monitoring. According to GA CEO Lyndon Blue, quote, GA's work with NASA is opening the eyes of regulators to the safety and utility of unmanned aircraft systems and the performance of certain tasks for public and commercial good, end quote. Researchers believe these types of aircraft will also play an important role during crisis management events, such as wildfire containment. The onboard airborne sensors can see through thick smoke, enabling the craft to inform ground personnel about the location of fire lines so they can deploy resources more efficiently. The SIO demonstration also highlighted how the aircraft can be used for many other civilian and commercial missions as well. The third demonstration flight was a team from American Aerospace Technologies Incorporated, or AATI. Although AATI's craft was considerably smaller than the other test vehicles, its use case was invaluable. It can fly at medium altitudes and carry advanced sensors used to patrol our nation's more than 500,000 miles of midstream pipelines, providing a fundamentally new and unique capability that changes the way we manage health, safety and the environment, respond to disasters, optimize operations, and leverage human capital.
So the mission itself serves multiple purposes. We're proving out the capability of beyond visual line of sight UAS in the national airspace. And the specific applicability for this mission is that we are looking for ways to make critical infrastructure inspection processes safer and more efficient. And so for this specific mission, the Air Ranger took off from our launch and recovery site, and we flew downrange along a oil pipeline which is buried underground, and we performed an inspection of the right-of-way of that pipeline. And we are proving out not only the applicability for critical infrastructure itself, but we're proving out the safety case for actually operating UAS in the NAS, not only utilizing the aircraft's technology for flight, but also utilizing different technologies for safety, such as detect and avoid systems, ADS-B, and flight radar notification systems for having situational awareness of not only what's in the airspace around us, but being able to tell others in the airspace that we're flying as well. In my opinion, to safely regulate and certify these types of aircraft to fly, you have to prove out 3 different things. You have to prove out that the aircraft itself is mission capable. You have to prove that the aircraft is dynamically capable to change for different conditions. And you also, most importantly, have to prove out the safety case. And so utilizing different types of technology, utilizing different processes and workflows, building the safety case around operating procedures, and integrating all of these different components aside from the actual flight itself, really build the roadmap and really set the stage for the rest of the industry to say, hey, look, this is what the infrastructure looks like, this is what the framework looks like to do this on an operational basis in the future.
Although the SIO demonstrations are now complete, NASA and industry will continue to move forward with exciting new technologies and hardware built on the foundation of successful data collection and testing from the SIO activity. The future of unmanned aircraft is bright. UAS will continue to advance scientific research, benefit environmental protection, assist with disaster mitigation, and move more people and goods to their desired destinations safely and efficiently for decades to come.
This was just the results of a project with a specific goal that we had within NASA Aeronautics, but it's certainly not the end. I mean, integrating UAS into the national airspace is an evolving thing. There are many more challenges. There are many more use cases that the industry is going to come up with. And so we're sensitive to that, and we're keeping an eye on that so that we can really align our research with those areas that are emerging, and hopefully so that we can enable those to really be to come into fruition for the benefit of the American public. And so as we stand up new projects, we'll leverage our experience with UAS and the NAS project, but we'll do it into new areas, whether it's autonomy or other areas of research that will really enable a lot of these use cases and bring about some pretty exciting new markets for the country.
Antarctica. It is the world's coldest continent. Scattered among the ice in this harsh and unforgiving environment are numerous research stations. One of these is the Neumayer 3 station. Situated on the Ekstrom ice shelf and operated by the Alfred Wegener Institute, which coordinates German polar research efforts. Nearby Neumayer 3 is a small greenhouse, the German Aerospace Center's Eden ISS, which is working on developing innovations for cultivating food using closed-loop systems. In a space about the size of an apartment bedroom, this greenhouse recently grew more than 600 pounds of fresh food, including cucumbers, lettuce, and tomatoes, in a 9.5-month period, even with outside temperatures well below freezing. The researchers took scientific samples from their crops, but they ate the vast majority of what they grew in a powerful demonstration of the benefits of closed-loop agriculture. This research not only benefits indoor agriculture here on Earth, it also has applications for space exploration. For more than 20 years, people have continuously occupied the International Space Station, a laboratory about the size of a 6-bedroom house that orbits the Earth every 90 minutes, at an average altitude of approximately 250 miles. Astronauts working with researchers on the ground have used the space station as a proving ground for the technologies and know-how that will allow people to explore more of the moon than ever before and take the next step in space exploration, a crewed mission to Mars. Jess Bunchek is a plant scientist from Kennedy Space Center, NASA's leading center for growing plants in space. The agency is sending her to work with the German Aerospace Center on research that could one day help feed crews on long-duration missions to the Moon and Mars. Bunchek brings important experience to Eden ISS. Knowledge gained from working with astronauts growing salad crops in space. After a month-long voyage from Germany, Bunchek will spend about a year in Antarctica. There, she will work with a team of researchers connected to the Mission Control Center in Bremen, Germany, to solve challenges with closed-loop agriculture so that it can be robust and productive enough to help sustain astronauts on a 2 to 3 year long mission to Mars.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times. You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
In the beginning, the void, the darkness, then light, then life. And from life came man.
joining the caravan for the long, slow journey through a world of discovery, invention, exploration. His marks, his milestones, stretch out through the centuries. His footsteps echo down through the corridors of time. Time. July 1969 in Florida. The footsteps, the caravan quickened. The corridors shortened as man reached outside his world into another void. Today in Florida, they go about their lives, taking only a sideways glance at the reminders of that milestone. Reminders, images that vaguely jog our memory.
This is Apollo Saturn Launch Control, aiming toward a planned liftoff time of 32 minutes past the hour. The start of our launch window on this mission to land men on the moon. The countdown still proceeding very satisfactorily at this time.
Time, it plays tricks on us. It smudges and blurs the sharp edges of reality. But we turn the trick and summon up our own reality, images, sounds, to help us remember.
The batteries all look good. The next time we go internal will be at the 50-second mark with those batteries, and they will remain, of course, on internal power during the flight. The lunar module, which has been rather inactive during these latter phases of the count, also is going on internal power at this time on the 2 batteries in the ascent stage and the 4 batteries at the descent stage.
They came 1 million of them to this place, drawn by the magnet of history in the making.
The astronauts, the prime crew, were awakened at 4:15 a.m. Eastern Daylight and proceeded to have a physical examination in which they were declared flight ready. They sat down for the normal astronaut fare on launch day. As far as breakfast is concerned, orange juice, steak, scrambled eggs, toast, and coffee. The target for the Apollo 11 astronauts, the moon, at liftoff will be at a distance of 218,096 miles away. The astronauts departed from their crew quarters after checking out their suits. They departed from the crew quarters at 6:27 a.m. and some 27 minutes later, 8 miles away from the crew quarters at the Kennedy Space Center, atop the launch pad at Complex 39, 6:54 a.m., the commander, astronaut Neil Armstrong, was the first to board the spacecraft. He was followed about 5 minutes later by Mike Collins, and finally Buzz Aldrin, the man who's sitting in the middle seat during liftoff, was the 3rd astronaut to come aboard. The weather is certainly go. It's a beautiful morning for a launch to the moon. We expect a temperature of about 85 degrees in the Kennedy Space Center area. We're still go on Apollo 11 at this time. T-minus 25 seconds. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. Yeah, I'm going to step off the limb now. That's
One small step for man, one giant leap for mankind.
Apollo 11, Armstrong, Aldrin, and Collins. They and millions of others reached out and, in their own way, touched another planet. The images remind us that it happened, but not how it really was in the context of the times. George Lowe, one of the architects of the Apollo program, does remember.
If you think back at the period of the 60s, they weren't very happy years in general. We had, the ever-deepening involvement in Vietnam. We had riots on the campuses, riots in Watts and elsewhere, 3 terrible assassinations. A great deal of strife and turmoil in the country. And yet all of this was overcome by one single event, and that was Apollo 11. The decade ended with it. It was a fantastic adventure that I believe helped overcome all of the bad things of the decade. It represented Americans to ourselves, and particularly to the rest of the world, as we like to see ourselves and as we hope the rest of the world likes to see us.
The equipment of Apollo. Some of it is now in museums, artifacts from an age of discovery. These strange-looking objects, they're there as reminders that after all, it did happen, and it happened the way we remember. The facilities of Apollo, now silent and still. In Houston, Mission Control, the nerve center of manned flight operations. The chapters of space history, first Mercury, then Gemini, then Apollo, were written by the people who sat at these consoles. And these chapters of history came at us with breakneck speed. Christmas Eve, 1968, in the beginning, Apollo 8, the footsteps were quickening. A few months later, Apollo 9. The long years of preparation were contracting into days, hours, minutes. The first manned flight of the lunar module, the Spider. Apollo 10, the dress rehearsal for the real thing. In 5 months, 3 missions, and in the 7th month, the payoff. Then, the celebrations. The images and the sounds fade in our memories, but some things we can't forget. Names: Apollo 11, Armstrong, Aldrin, and Collins. Other names: Grissom, White, and Chaffee. They remind us that it wasn't all success and celebration. There was failure and tragedy. Early in 1967, the 3 crawled into the command module at Cape Kennedy for a test. There was a flash fire. All 3 died. After the shock came the long, painful job of picking up the pieces, learning the lessons, coming together for a common goal. The remains of the launch structure stand as a reminder that the goal was reached. These strange shapes, what do they mean? These towers of steel, what are they? Monuments or leftovers from some earlier age of discovery? In the long history of man, in the slow journey of the caravan, what point do these mark? Historian Arthur Schlesinger, I have no doubt at all that if posterity remembers the 20th century for anything, historians 500 years from now looking at the 20th century, it will be because it will be the century when man first began to break his terrestrial bonds and began the exploration of space. So that's it? As man learned, moved on, and discarded the earlier structures, he came to these. They're marked for further milestones, reserved for future missions, other reaches to other different voids. Historians 5 centuries from now will mark this century, this place, and they will further note that from the void, life, man, it took eons to reach this point. But once there, the centuries and years compressed into days, hours, split seconds of exploration. The wheel, the engine, the airplane, they came slowly at first, then with increasing velocity. And then this, so huge, so powerful, so different that no ordinary modern name would suffice. They reached backward through antiquity to Roman mythology, and they named it Saturn. Saturn. His father was heaven, his mother earth. Complex organization, the mammoth machines, the incredibly detailed technical knowledge, the dedication. It was all harnessed, sharpened to a fine edge, and focused. The program developed and matured. Apollo 17 was launched at night, and even the old hands, the hardened veterans of the space program, couldn't help but feel the awe, and wonder, and excitement. In the excitement of the split second of exploration, man doesn't stop to freeze the moment in history, to look at it and ask what it means. He simply lives it out. But in the Apollo program, on their way to the moon, they found a way to live out their strange moments in those strange spacecraft. It may be the peculiar nature of Americans to make history and to have fun in the making. Fun because we were confident of success. But the program teaches lessons. Confidence is a transitory thing. Apollo 13.
Hey, Houston, we've had a problem here. Can you say again, please? Oh, Houston, we've had a problem. Stand by, 13, we're looking at it.
3 days out, barreling toward the moon, an explosion. No one would see the problem for some time, but they went to work on it. The people of Apollo coalesced into a single dedicated unit. linked themselves with their technology and cheated tragedy. A new chapter in space history was written in Mission Control. Eugene Krantz was the flight director when the problem developed.
Throughout this entire next several days, there was one dominant thought in the minds of all of the flight controllers. We teach them that between God, country, and your own capability, that you can solve any problem that may occur in flight. Throughout the entire course of Apollo 13, there was never any doubt that we'd get the crew back. So there was a very positive approach, and with this kind of approach, you can solve just about any problem that comes up.
Solve any problem, country, capability, old-fashioned words during a time when some said the old-fashioned virtues were forgotten. Well, they weren't forgotten. They were translated into action, into programs which took man soaring above the surface of the moon, away from Earth, but always looking back on it. These divided thoughts, the moon, the Earth, run through the Apollo program a sort of theme. They went there flying in their graceful machines, but they always thought back to where they came from. Perhaps that's natural. The moon is a strange place for men to be flying to. If it's strange for men, for mankind, it's stranger still for the individual man. Harrison Schmitt, Dr. Harrison Schmitt, a geologist, he touched the moon and remembers how it was when Apollo 17 was making its descent, the last flight to the moon, the last time that man walked on its surface. Schmitt remembers how it was.
One's first feelings are a mixture, a very complex mixture of humility, excitement because of something you had planned to do was being accomplished, but of a great attention to detail, to the detail that you had thought about and learned about for so many years prior to the actual event. That detail keeps you occupied with where your hands are and where your feet are, which rung they might be. You try to remember, well, am I at the bottom of the rung? And then as one moves away and tests his way on the surface of the moon and looks around, and in my case, looked around a very magnificent valley, you see a rolling, hilly country that is interspersed with some blocky fields of rocks that you know because you've studied the photographs, and you saw them as you descended surround large craters that have been formed in that rolling countryside. These rolling dark hills merge in the distance a few kilometers away with the very smooth but very bright colored slopes of the massifs. And they rise with a majesty to rocky tops that are almost beyond description because there's nothing like it that we have seen on Earth.
The Sea of Tranquility, Hadley Rill, Taurus Littoral. They were once strange names on the map of the moon, but the men of Apollo gave reality to the names by being there and showing us the places. They explored 60 miles of its surface, and their travels took them to craters, foothills, to explore, to observe, and to sample. The hard rock proof of Apollo, enshrined in the Smithsonian Institution in Washington, D.C., 478.8 grams of microbreccia under glass for mere earthlings to see and whisper about. Other rocks from the moon, 840 pounds, are being studied and talked about by scientists in laboratories around the world. Not only rocks, tens of thousands of photographs of those strange, exotic features of the moon. And telemetry, data on tape, facts, figures. The studies will go on for years, and the answers will come slowly, answers to questions about the moon and the solar system. The science of Apollo is not merely concerned with samples from past milestones, yesterday's missions. In a special room in Houston, men sit at consoles and command instruments on the moon to send them today's data. Then they receive it today within 8 seconds of the command. Science, that's the key, and technology, and something else. In the drama of the moment, few stop to think of the essential element, the one thing that made it happen. People came to this program, government people, university people, contractor people. They brought to Apollo skills and knowledge and determination. This source of human intellectual energy was marshaled, focused, challenged. What came out of the effort was not just a very successful program, but a rich national resource of vast proportions. Crystals from the moon, the symbols of the science of Apollo. Behind it, causing it, was the spirit of Apollo.
I was strolling on the moon one day in the merry, merry month of December. No, May's the month. May, that's right. May is the year of the month. When, much to my surprise, a pair of bunny eyes. That's the truth. You do that in West Texas and you get a...
We saw something of this spirit. We shared in the adventure, the excitement, the euphoria of being there. We shared it with the men who bounced across the surface of the moon.
Look at the size of that biggie. It is a biggie, isn't it?
And the surprise of discovery. We were there too, all of us, watching, vicarious explorers.
On for the big boulder. Okay, we're headed that way. You get the tongs, John? Yep. I'll carry the rake. Look at the size of that rock. Can't believe it. I can't either. Okay, let's go on back. I am.
And the meaning, the significance of an occasion. That too came to us, flashed into our living rooms on a 19-inch window on the universe.
Countries throughout the world. We hope that this will be a symbol of what our feelings are, what the feelings of the Apollo program are, and a symbol of mankind that we can live in peace and harmony in the future.
There was also pride. They put up the flag and then posed for pictures as any visitor to a foreign place might do. The flag of each mission stood there as a reminder that we had been there, but there was the realization that in truth, it belonged to all the people. There are no boundaries on the moon. The focus was the moon. That's what it was all about. But by reaching up there, we, in a sense, came back here.
As one stands and scans a 360-degree panorama of his own, one of the first objects in the dark lunar sky that you see is a bright and beautiful bluish globe that we call Earth. This globe represented to all of us, I think, not only home, but a very fragile place that we have come back and felt that needed not only protection, but understanding.
They first went there in 1969. They last left there in late 1972. Between the beginning and the conclusion, they came to feel, to dimly perceive what it was all about, to come to a perspective on the meaning of it all. Poet Archibald MacLeish has said it better than most. To see the earth as it truly is, small and blue and beautiful, in that eternal silence where it floats, is to see ourselves as riders on the earth together, brothers who know now they are truly brothers. The excitement of the mission, the tension and drama of the splashdown, they remain only in our memories. And in time, they'll be replaced in the future by other missions, other memories. The moments of Apollo may be over, but the understanding and the discovery, they go on. And the full meaning, the real meaning, may yet be in the future too. But for now, for the present, the images and the sounds provide meaning enough to each in his own way and to each in his own time.
It's the first word from space before history is made. From landing a man on the moon to assembling the International Space Station, NASA's Johnson Space Center serves as the iconic beginning to some of the greatest moments in American history. Moments that are triumphs of engineering and international cooperation. Today, we are leveraging our past successes to create even more daring missions from the moon. Made possible with the Orion and Gateway programs, which are both orchestrated out of Johnson, the desolate moon will serve as NASA's jump-off point as we journey to unlock the secrets of the universe and understand how it all began. Today, we push forward to the moon. Tomorrow, we leap to greater heights and new destinations. There is history to be made. In Mission Control, we eagerly anticipate the first transmissions from unexplored worlds. Giant leaps start here.
Space Launch System is the next newest, biggest rocket that we're going to build, and it's not just a replacement for the Space Shuttle. This rocket is going to carry us much further than the shuttle would go. It's NASA's next big rocket for deep space exploration.
The SLS is a national capability that provides a unique access to space that America has not had in 40 years.
A large launch vehicle like this really opens the door to destinations beyond. It's not limited by destination. It's only limited really by imagination.
What we're focused on here at this center is the propulsion system. And that consists of 2 solid rocket boosters and a core with some tanks that feed some liquid rocket engines in the middle. And then the astronauts sit on the top in the Orion spacecraft.
One of the things we recognized for SLS is we had to be affordable. So we had to do things differently, more efficiently, and smarter.
We're all conscious about saving money, doing it more affordable than we have in the past. But at the same time, we can't sacrifice reliability or safety.
The system uses a significant amount of heritage hardware, which is things that we've evolved from the Space Shuttle program.
The Space Shuttle had two kind of candle-looking things, which are the solid rockets. Those are kept, and those are used on SLS.
We've added a segment to the 4-segment solid rocket boosters that we had on Shuttle. That gives it more power, more thrust, and it helps this larger rocket get off the ground. What those boosters are for is just to get you going. They burn for a couple of minutes and then they fall to the ground. Then your liquid engines, you're up high enough, your liquid engines can carry your vehicle to as high as you want to go, and if you have additional stages, like we're going to have one, then you can go further out into space.
Right now, the inventory that we've got consists of 14 engines that have flown on Shuttle. We've got one engine that was assembled and still needs green run testing or certification testing. We looked at all the spares. As we collected the spares, we determined that we could assemble a 16th engine. So we'll have 16 engines that we'll be able to use for flight.
We are making tremendous progress. We've got all of our prime contractors on board. We're testing engines, we're testing solid rocket boosters, our avionics systems.
J2X has recently set a record at Stennis. When we were testing, it was the first liquid oxygen engine to get to a full duration test in 4 tests.
We were developing this booster under the Ares program, and we're moving that into the SLS vehicle. The motor itself has been through 3 development firings, which are full-scale motors tested out in Utah, and we've gotten a lot of good data, engineering data from those tests.
This is an adapter that goes between the bottom of the Orion capsule and the top of the Space Launch System rocket that we're developing here at Marshall. It's been specifically designed to give strength to the adapter so that it can take the loads in flight and still be lightweight. This shape started out as a series of flat panels. The isogrid pattern was machined into the surfaces. Then they were formed, it was called in a process called bump forming, to make them into the shape that we need here. And we weld 3 of these segments together to form the cone that you see behind me.
We just delivered the first crew module to the O&C building at KSC. We've started a lot of the parts onto the outside of the CM, and we've actually put it in what we call the bird cage, so we can locate all those parts, within, thousandths of an inch to make sure that everything is going together okay.
Putting, wiring inside of it, putting tubes for the, for the propulsion system, putting valves and pumps, and so all of that happens in stages right there in the O&C building.
We have on contract with USA, United Space Alliance, to build our harnesses. They're set up shop in the O&C, and so their little shop delivers to the big shop.
Thermal protection is very difficult in re-entry vehicles to test and to model. I mean, really, you have to fly it to really understand what's going to happen. We're building ceramic thermal insulation tiles for the back shell of the capsule. We're building thermal barriers for the capsule, and we're building multi-layer insulation for that capsule.
I'm the heat shield design lead. So we're designing and building the heat shield for the future Orion missions.
The heat shield right now is in our big 20 by 20 router. It's a 5-axis router, and right now it's machining the interior bowl, if you will, of the heat shield.
To cut out that heat shield on the router, it could take weeks of machine time running multiple shifts.
It's the biggest heat shield ever constructed.
The other component is the heat shield skeleton, so that's the piece of the titanium substructure, the backbone that makes up the carrier structure itself.
Another unique thing is all the hand drilling that we're doing. So it's not automated by a router in this case, and it all has to be hand drilled by technicians on the inside.
200 plus titanium parts, all match drilled together.
So we have a tool that puts all the pieces in the right spot, and then we drill and high lock them all together.
MCC is transforming from supporting Space Shuttle and Space Station to a platform that will support Space Station and MPCB or Orion.
In order to adapt for the future, we need to go to a more modern system.
KSC will operate the vehicle all the way up until launch. We'll operate the vehicle until splashdown, and the recovery forces come in and take over after that.
Fire Room 1 is the launch control room we're going to use for Orion SLS for EM1 missions. We've been working with the Orion program to get the spacecraft data so we can process it with our software in the firing room, and we will be flight following that mission out of Fire Room 1. We refitted the room, we redid it, putting the sound suppression carpeting on the walls, making it kind of a more comfortable place to work. So we're aiming for about 50 people in Fire Room 1 for an EM1 mission. We are actually using Fire Room 1 right now to test Pad B subsystems.
This pad is going to be almost like a complete new pad because we will have refurbished each and every system that it's inside the pad. We're going to have the vehicle launch from the mobile launcher, and not only launch from the mobile launcher, but have a tower that will have all the services attached to the vehicle. The tower is going to be on the mobile launcher. The vehicle will be assembled at the VAB.
It's a return to a concept that we knew that worked very well during the Apollo years when the mobile launch platform had a tower on it. We knew that the VAB was designed to accommodate a launch tower on a mobile launch platform. We have to make sure that the VAB can remain adaptable and accommodate different vehicle architectures. And now we have a clean VAB shell, per se, the infrastructure, so that we can accommodate the new hardware, the new vehicle access with new platforms. And that is the first phase of what we're doing now.
And once the vehicle is ready with all the connections, the only thing we got to do is move the vehicle to the pad, do the connections to the mobile launcher. And once we do those connections, we're ready to launch.
There was a time where I had to explain what a crawler was. If you didn't work out here at the Space Center, or if you weren't in the Central Florida area, a lot of people just, somehow the vehicle got out to the pad. We knew what to expect from a load perspective with the new vehicle, the larger rocket, and things along those lines. And that goes from the crawler lifted load, the hydraulics, also to the crawler way. We're going to have to increase the load lifting capability for the crawler way itself with the rock. What we've essentially done is keep all the same hydraulic components, but just increase the size, the diameter of the hydraulic cylinders. Last November, we actually took a ride out with the completed crawler 2 out to the pad and tested out the systems and a couple punch list items, but everything worked great. The control system had been upgraded. The driver's cabs consoles had all been replaced. The brakes had all been replaced. Nearly every subsystem had some kind of work done to it. The traction support elements, each of the 4 corners has 22 rollers that are about the size of a car, to be honest with you, and we're changing out all of those, enlarging those as well.
What I love doing is reminding the outside world, whether it's within our government or especially the media, that has a perception that we're in a lull, there's nothing going on, that the space program's shutting down, to kind of dispel that rumor and say, no, this is the far opposite for us. We are utilizing this inter-program time frame to make all the modifications and all the infrastructure changes that it will help bring that agency vision into reality.
Many of us feel the country wants to go forward, and NASA has a big following, and every time I talk to people, they're excited about NASA.
Enabling people to go beyond where they have ever gone before and look and discover things that they didn't even know existed is just it's just a real honor.
It's been a pleasure to be involved with this project, and I can't say enough for the team that's put this together.
I'm privileged to work this program. I think most people who are working it today feel the same way.
I can't believe they pay me for this job. It's just wonderful. It's great.
Very rarely do you get the opportunity to kind of literally from the ground up put together a factory whose sole purpose is to go make history and do exciting things for not just NASA, but for America and for the whole world.
We're in the process of getting the factory ready for SLS production. And in that process, there's a series of new tools that we've been installing in the factory.
Now we have not just put in new tooling, there's some legacy tooling that we're using. Most of the external tank buildings are being reused. We have a lot of construction going on for those, getting ready for a rocket that's same diameter but a little bit longer.
Not only are we using the legacy knowledge, the lessons learned, we're also incorporating new technologies.
The tool today is in the vertical friction stir welding center, and its job is to produce the cylinders that make up the parts of the tank that will be stacked.
And that is going to be the tool that joins every panel on every barrel for the rocket.
This device will actually do the weld in a single pass and then also do inspection. So these are the large barrel sections of the core stage that will be the foundation or the beginning rocket that will actually take our crews beyond the moon and really propel us into space.
Here at Marshall, we've designed the interface hardware in between the Orion capsule and that upper stage.
The MSA, I think, is a great example of a couple things. One, it's actually a piece of hardware that we're flying on an early test, but we're also going to fly for the long term. So this is the same design that we'll use when Orion's on the SLS and we're actually flying people.
Today we've been taking the two unique pieces of hardware that are supposed to have a common interface, basically lowering them together, bolting and making sure that they fit.
Well, we're going to test a lot of the key systems on Orion and also for SLS with the upper stage of the MSA that are going to be used when we fly people into deep space.
Most recently, we've been involved with NASA with the SLS development using our unique forming technology along with our other core processes in terms of machining, welding, heat treating, and inspection technologies. Really is a one-stop shop is what way you would describe it.
Right behind me you have the first weld development cap, or I think you call it the weld confidence cap. The production order will start deliveries in 2014. Spincraft also builds the domes for the upper stage Delta IV vehicle, which will be used for the EFT-1 flight, as well as the first two production flights of the SLS program.
For the SLS PDR, our primary role was the overall communication and outreach support that we provide back to Todd May's office for SLS. We provide all of the communication support for that particular team, that program and project.
Well, it's a preliminary design review, and primarily it's a technical review to make sure that the design is acceptable and at the appropriate level of maturity.
There's a lot of discussions, there's a lot of meetings across the board from technical, cost, schedule, performance data, safety, human factors.
It's like a health check on the program. Those of us that are working on the program, we've got our head down, we're doing our pieces, and sometimes when you're working real close to things, you don't necessarily see everything.
So there's so many moving parts and so many things going on at the agency, as well as the center, that to show people that we are moving in the right direction, to pull together a complete story of where we are as a program.
Watching at it from a higher level headquarters viewpoint, it's just gratifying to see the accomplishments that the teams have made and continue to make every day.
For CT2, we're doing modifications not only to make it last another 20 years, but also to uprate the load capacity. The main project we're working on right now is the roller replacement project, which is the roller assembly. It's actually the rollers, the shafts, the bearings that support the crawler. Actually, if you go there, you'll see trucks A and C jacked up and on cribbing. And that's the first time in the career of the crawler it's ever actually been jacked off the ground. So the guys have easy access to the roller assemblies. And they're in the process now of removing the old rollers, old shafts and old parts. Once they've done the line boring, that's when they'll start assembling the new rollers and the new shafts and the new bearings and the new sleeves and new adapters and new plates. So there's quite a bit of work, and that work will go well from August through October. So there's going to be a lot of trucks delivering a lot of steel here at Kennedy.
We started actually the new design for flame deflector as well as refurbishment of the flame trench, and that's because of the new requirements for SLS and commercial vehicles. We've started the demolition of the flame deflector. We've got concerns of, due to age and the debonding of the flame trench structure, this would possibly be a safety hazard for our new program. And that's why we had to go in and do a new design and refurbish this flame deflector and flame trench.
These pieces here, they're not just one program, it's not just one mission, it's part of a capability that will enable this country to be a leader in space, to continue to take people from the Earth well beyond low Earth orbit out into deep space. And this is the hardware that will do that over multiple decades in the future.
So the work that's been accomplished so far is primarily structural type work, right? It's a lot of drilling, a lot of secondary structure installation, mechanical structures, the support structures. The next step is starting to install the subsystems. When we actually perform the welding on tubes for propulsion and the environmental controls and life support systems, those have to be at a higher level of cleanliness. When you look at the facility, there are these very large walls that are on the perimeter of the structure itself, and those are called HEPA filter walls. We can perform clean room work for the tubing concurrently while on the outside doing more standard clean room. So our goal is next summer sometime to turn the vehicle over, early summer, over to the ground operations organization so they can start their processing.
Well, the service module is attached below the crew module, and it has the prop tanks and the engine, radiators, solar panels. The service module all came in pieces. There's 49 composite panels on the SM. The actual structure itself is aluminum. That's the core skeleton where these composite panels were attached to. After the CM releases and the CM returns to Earth, the SM will just burn up with the upper stage of the Delta IV.
We performed two primary tests so far. The proof pressure test, which is just the pressure vessel, and that is put into the proof pressure cell. It's pressurized and a relatively high pressure. We're testing how well the vehicle was built. And then the follow-on test is the static loads test, where the vehicle goes through 8 different loads test cases. And so the vehicle is put under pressure, it's put under tension, it's put under compression. The whole intent in landing and recovery.
We usually get the abort motor first, and for this mission the abort motor is inert, being a nominal flight.
We're going to have instrumentation on it to again understand more about the loads and environments that we expect to see in flight, but it will be an inert propellant that's cast into the motor.
This time we got the jettison motor next, and that's the only live component of this vehicle. We do a nominal jettison, the jettison motor fires, the last separates from the CM, and the CM continues on its mission.
One of the challenges of any new system is understanding the loads as you ascend up through the atmosphere and the dynamics, the acoustics, and we'll be able to gather a lot of that information.
The back shell, it looks though it looks the same as what we flew on shuttle. It is different. We kind of took the best aspects and put them together to meet Lockheed Martin's requirements for the Orion capsule. Two major things we're trying to accomplish here. One of them is to prevent micrometeorite damage when we're on orbit for long duration. The other, of course, is the reentry aspect. The skin that you see on the capsule, what you would see on orbit, sits on top of a composite substrate, what we call the back shell panel, that when combined together gives you the complete back shell. There's some sections that have some very complex geometry. So what we're going to do for the first time is take a substrate that's built by Lockheed Martin and put it together with the tiles that are manufactured by Jacobs and validate the fit up. Like any test vehicle, you're heavily instrumented. We're going to come back with a tremendous amount of data on how the system performed.
This first flight test of Orion is really to understand how the heat shield performs, and that heat shield's going final manufacturing at Textron.
Textron's had a long association with NASA and working in the space area for space protection.
The technology today has advanced tremendously. Our manufacturing technology has advanced, but ironically, we're still using a material that has proven itself for the last 40 years.
AvCoat is a very efficient ablator, and as an ablator, what it does, it allows us to protect the capsule from the high heating that occurs during re-entry.
There is no material, non-ablator material, that can handle that kind of heat. You have to shed away the heat. Basically what you're doing is you peel off the layers of the heat shield, you're taking heat with it.
When we apply AvCoat to the heat shield, we bond the honeycomb onto the carrier structure, and then we inject the AvCoat ablative material into the cells. The honeycomb acts as a crack arrestor and gives it rigidity and strength as a whole.
We know we're on the critical path for the Orion program, and so our employees are literally working all hours, all days of the week to make sure that we hit our schedule. We know there'll be more heat shields coming, and we're very excited about that. Our job is to make sure they're perfect.
The development programs I find just awesome, because this is where you're coming up with the new ideas, you're creating the new vehicles, you're pushing the boundaries in essence.
You can feel that we're going to go do this. The hardware is starting to come. The Orion hardware is getting ready for its first flight test down at the Kennedy Space Center.
The excitement is here. We are really ready to get going. So we are far from being out of space. We are really getting ready to go into space.
That's so rewarding to see our focus into what's next, because this really is our future.
I know the day that we fly this thing, there are going to be thousands of people that are going to be excited that are working on this, and the NASA workforce and the contractor workforce. We're going to be proud of the work that this team has done, and I think we're going to be proud of our country too. It's going to be a pretty exciting time.
I'm ready to build a rocket, and we are ready, and we want to build it on time.
Hi, I'm Lori. I study the planets, our solar system, and I especially love volcanoes. And this is Ask NASA. The thing I love the most about our solar system is that it's an incredible natural laboratory. We have so many different types of objects in the solar system, from planets and moons and asteroids and comets. We can study each one of those, and they all have something they can tell us about how the solar system formed or how Earth ended up in its special place. And understanding why the other planets are different from Earth actually helps us better understand how we ended up the way we are today. So this is a globe of Mars right here, and many of the reasons why we're so interested in Mars, there's a lot of different processes going on Mars that help us better understand Earth. A lot of the surface of Mars has been preserved for almost 4 billion years, and so we can study a lot of things on Mars that you can't even find on Earth.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
So Perseverance rover is going to drive around and find some of the best rocks it can, drill down into the rock and soil and collect those samples so that on our next mission, Mars Sample Return, we'll be able to bring those back and study them in our laboratories here on Earth. There is volcano on Mars. In fact, there's lots of volcanoes on Mars. The largest volcano we know of in our whole solar system is on Mars. It's called Olympus Mons, and it is so giant that the entire chain of Hawaiian Islands could fit inside the crater at the top of that volcano. We see volcanoes really across the solar system on all of our rocky bodies. So on Mercury, we see evidence of lava flows on the surface of Mercury. Even on the moon, we have lava flows that we can see. On Venus, we see the entire surface of Venus is covered with lots of volcanoes and volcanic deposits. So this is a globe of the moon Io. Io is the moon of Jupiter. That's the most volcanically active body in our solar system. And that's because the pull of Jupiter's gravity on Io as it goes around Jupiter tugs and pulls at Io, and that heats up the inside, and that drives volcanoes. The heat needs to be released. This is the volcano Pele. And there's lava flows down here in the middle, but then there's also this big red-orange deposit, which is actually from explosive eruption of the gases that are falling down onto the surface of Io around the volcano. And it has no atmosphere, so if you were to turn it like this and look at this volcano from the side, you see a big umbrella of gas. The particles just come out and then they drop back down. And I started studying volcanoes on Earth about 35 years ago, and then started studying volcanoes on other planets, and that grew into my love of our solar system. So the asteroid belt really contains a lot of leftover material from solar system formation. You can imagine that when the solar system first formed, the particles kind of came together and made bigger particles. Some of those came together and created the planets. We actually find asteroids in lots of different parts of our solar system. We have asteroids that are near Jupiter, the Lucy mission, which is going to launch this year in 2021, and it's going to go study those special asteroids that are trapped in Jupiter's orbit. And then next year we have another mission called Psyche that's going to a particular asteroid called Psyche that looks to be made mostly of metal, of iron. It may actually be the exposed core of a small planet that may have had its crust blown off by an impact and left that metal core that we can see. There is definitely water on the moon. We know this because we've observed with some of our orbiters being able to identify that there's water molecules on the moon. And in fact, some of these we believe are preserved as water ice, perhaps in these permanently shadowed regions that are very, very cold near the poles. And what we need to do next is to actually go down to the surface of the moon and actually look at that ice up close. And so that's what we're doing with the Artemis mission. We'll be focused on looking for some of that water in the soil of the moon. We have explored really the far reaches of our solar system. We have sent missions to Mercury near the sun and visited all of the planets in our solar system, all the way out even to Pluto. And then one of our missions, called Voyager, actually has 2 spacecraft that have now even gone beyond the edges of our solar system. So we have really explored the whole expanse of our solar system.
Cool. Io and Mars are great.
Let's try it again. Oh, that's too high.
That was a fastball. She had a fastball.
Do you have a question for NASA? Send your questions to our experts using hashtag AskNASA.
Welcome to NASA Edge, an inside and outside look at all things NASA. We're joined by Michelle Monk and Steve Gaddis. How you guys doing?
Great.
And we have a very important topic today, and that's going to be EDL, or Entry, Descent, and Landing. Now, Michelle, you're the principal technologist for EDL.
Yes.
What is entry, descent, and landing?
Entry, descent, and landing is how we get a spacecraft from the top of an atmosphere to a planetary surface. So the entry part refers to, the atmospheric flight, most of it, and then we have descent and landing, which is usually propulsive and get us down on the surface safely. We do D and L at places that don't have atmospheres like the moon or, asteroids, but usually we talk about EDL when we talk about atmospheres.
So Michelle, what is your role as principal technologist for EDL?
I look across all the missions that NASA has coming up that will use entry, descent, and landing on any planet, and I look at the technologies we're going to need for those missions, and I bring them forward to the mission directorate for starting funding.
So you have a need in the EDL world, in the community. You're coming up with the technologies that are needed for future missions.
Right.
So you take some of those technologies that maybe are less mature, hand them off to you.
Right.
And then you mature those technologies.
Design, develop, test, and evaluate.
Is that a pretty easy task, trying to figure out
Not at all.
what technology you're going to need?
Not at all. I have to look at both the human missions that are coming up, so, sending humans to Mars.
Right.
I have to look at the scientific missions that are coming up and all the destinations the scientists want to go to. And I have to kind of rank those and prioritize them and figure out, where they are in terms of maturity and what the best infusion point will be. When is the first mission that can use that technology? And then I have to figure out what is the best program within STMD for the investment. Is it better to have a university work on it, or a small business, or is it better for a game-changing program element?
And your job is really hard because we're going to be talking about a suite of EDL projects over the next 2 shows because there's so much content in EDL.
There's a lot of content.
We can't do this into one show.
Absolutely.
So this will be part 1 of 2 parts. So how do you manage all that?
Well, one is it's hard, but it's also fun. And we've got excellent technologists leading every one of these activities. So we all work together, and we all know that we need these technologies, so we're motivated to see them be successful.
We're a very passionate community.
Yes.
I've seen it in all the interviews that we've done. You guys are definitely passionate. Now, the first one that we're going to be talking about is ESM, or Entry Systems Modeling. What is that about?
So that's the first part of it, where they develop these models and simulations to understand how the technology works and how it will be beneficial at a system level. It's very cross-cutting against all the projects, and the plan is to take that data and then infuse it into the projects.
Blair had a chance to go out to NASA Ames Research Center to talk to Mike Barnhart, who is the Integrated EDL Systems Lead. Let's check it out.
Mike, tell me a little bit about Entry Systems Modeling Project. What is it?
So the Entry Systems Modeling Project is tasked with developing a lot of these technologies that are coming from lower technology readiness level, things like academia, and trying to bring them up to a level so that we're ready to help them.
So in this particular situation, we're talking about EDL projects, and so you're actually helping them raise their technology readiness level?
That's right. So any of these things, Orion, Mars 2020, Mars Insight, anybody that's flying anywhere in the solar system and they need to enter an atmosphere, you have to go through an entry, descent, and landing phase. And we don't have all those problems solved. We don't have all those technologies built. And so we're continually trying to improve on our existing technologies and also renew with new ideas. And that's the real purpose of the Entry Systems Modeling Project.
How do we get the data we need to improve the EDL process across these missions?
Right, so there's a lot of different things that we can do. We have ground facilities, which we rely on a lot. So we have arc jets that we do for material characterization and developing models for material response. We have our shock tubes, which we use to develop radiation models. We have wind tunnels that we use to build aerodynamic models, the dynamic motion of a body as it's flying, that sort of thing. We need to know all that in order to have a successful entry into a planetary atmosphere. So that's the simplest thing that we have access to every day. And then we also have, some amount of flight data. So there was the Orion EFT-1 flight last year, which was very successful, and we can use that to take our models and look at our predictions and then try and back out, exactly how well are we doing, quantify, how well are we predicting that.
You used a lot of data from the Apollo era. Are you able to use data from things like MSL and more recent missions to help? Because I know we have limited data on entry.
Yeah, so MSL is a really great example because we flew Medley on MSL, and that allowed us to get some of the only data that we've had on entry at Mars. So heating data, pressure data, which we use to reconstruct the aerodynamics, is a fantastic tool for us, but there's a lot of challenges there as well. So it's really, it takes a village. You need to have your computational models because they're the only thing that's going to access the true flight space that we have here on the ground. We have ground facilities that simulate parts of the flight space, and then ultimately you have a little bit of flight data. And your goal is ground to flight traceability. Let's predict what we do on the ground. Let's predict what we do in the air. And let's see, how far apart are we so that we can quantify when we're designing the next mission exactly where we think we'll be.
Are you sharing that data with all the different EDL potential systems that are being developed?
Absolutely, absolutely. Everything that we do in the Intersystems Modeling Project is, for the greater good. We work very closely with academia. So we've got university partners that we are sharing this data with to help improve our models. We share it with other projects. So with radiation modeling, we were working very closely with the InSight project and OSIRIS-REx projects because they had issues with radiative heating on their back shell. So they call us because we're the radiation modeling experts, and they say, here's our problem, tell us, how worried do we need to be?
Be worried, be very worried.
Yeah, we're always looking to help everyone else around the agency, and that's really what Space Technology Mission Director is all about, right? Is trying to help the other directorates with the technology that they're going to need.
Tell you what, great interview with Mike Barnhart. I mean, it really kind of gives you the flavor of how difficult EDL really is.
Right.
I mean, if you can't characterize it and model it here on the ground,
Yeah.
I mean, you'll never be able to land.
That's right.
And you can't test an entry system on the ground and get the flight-like data that you need to design.
And that's the challenge but with Medley on MSL, that was a game changer, wasn't it?
Absolutely.
I mean, you actually, for the first time, were able to actually see the health of the spacecraft as it was entering the atmosphere.
Yeah.
Right. As engineers, it's great that we succeeded, but I want to know if I got an A+ or a C- on the design. So the Medley data allowed us to actually know how we designed the vehicle.
And based on that Medley data, what were the results? They were pretty good, weren't they?
They were fantastic. But we found some things that we didn't know. Radiative heating is important at Mars and at the scale of MSL. We didn't recognize that before.
And now, since it was such an important mission for you guys, now you're going to take it to the next level for Medley 2 for Mars 2020.
For Mars 2020, yeah, we've got that going, and they're right in the middle of their preliminary design phase. Right. They're all excited. They're going to put some new measurements on the back shell.
Yeah, they were actually at Aberdeen Proving Ground last week doing some testing to see where to put the pressure measurement on the back of the vehicle.
Right.
So yeah, it's really exciting to get this new data in the back shell and using new sensors.
We know Blair had a chance to sit down with Mark Schonenberger, who's the reconstruction lead, which I got to ask you about that when we come back, because I never heard of a reconstruction lead, but we're going to learn more about Medley 2. Let's check it out.
So Mark, when we think about the differences between Medley 1 and Medley 2, it's interesting because Medley 1, the M stood for MSL, Mars Science Laboratory. Now it's Mars 2020. You guys caught a break. You get to use the same letter.
We still get to use the same letter. I think it'll just be shortened to Mars, EDL instrumentation, and it'll hopefully continue for a bunch more Medleys, Medley 3, 4. We can always call it Mars.
Perfect. It's a nice little series you got going.
We're getting great data. So.
Now I'm wondering though, in terms of technology and in terms of how you're growing Medley, I mean, Medley 1 was a very successful mission as far as the data we got back. What are we expecting for Medley 2?
For Medley 2, it's really to dig in and look at the pieces that we couldn't quite get for Medley 1. The instrumentation there was it was the first time we'd flown instrumentation since Viking to get pressure and heating data. So we really tried to capture the whole event. And to do that, especially for pressures, we had these transducers that could see the peak high pressure as you went through the hypersonic phase and you're really slowing down around Mach 18. And then as you slow down, you really start getting in the noise there with the kind of information you can get. The signal is just really weak. It's sort of like using your bathroom scale to measure the ingredients for a cake. It's just, there's not a lot of resolution there. So it's tough. You don't really trust those measurements.
That's about how my cakes turn out,
that's
as
right.
if I measured ingredients with it.
So what we did here now is to use more of a postal scale for pressure. So we're measuring down at the low range when we're flying supersonically. Right as we get near parachute deploy, we're spending a lot of time just kind of slowing down, flying at the same altitude, but you're really at terminal velocity. You're not slowing down real well.
Now, is that pretty much in the part of the descent, if you will, that where you've burned away most of the heat shield that you're going to in the process?
Yeah, all the heating's over. I mean, it's still a little warm and things are kind of winding down, but yeah, all the exciting heating stuff is over, and you're really just trying to bleed off energy until you get down to a condition that's safe for the parachute. And so any error in your prediction of how that vehicle slows down, or your prediction of what the atmosphere is going to end up being on the day at Mars, can lead to being far uprange or far downrange. Your landing ellipse and how you target it, you need to account for that. So if we can get better data to characterize the aerodynamics, we can tighten that up and land in even smaller spaces.
Which is always the goal, right?
Yep.
You're trying to find out exactly where you need to land.
Yep.
So Mark, how is the instrumentation different on Medley 2 from Medley 1?
So, at least from my experiences with the pressure side, Medley 1 was really designed to capture the pressure all the way through entry. So it had this nice high maximum pressure it could measure. What we really wanted to do for Medley 2 was to look for the low pressures right before chute deploy. We're going to be coasting there, slowing down from, say, Mach 4 down to Mach 2 for a minute, 100 seconds, something like that. And that adds to the landing ellipse, any error in aerodynamics. So the transducers, we put more of them on the heat shield, and they're at a lower range, so they'll have much better resolution at those low speeds. So we can pull out things like winds, and we can get a better estimate of the drag. And we also have a pressure transducer on the backside. As you slow down, get down to supersonic speeds, the pressures on the back shell become a big contributor to the total forces acting on the capsule. And it's really hard to predict, actually, what those pressures are. So with some truth on the backside, that can really help us nail down the total behavior of the capsule as it's flying at those low speeds.
It seems like we're getting an awful lot of good data on the things that are happening during EDL and Mars, especially for Medley and Medley 2. Are we able to, in the future, maybe translate what you're doing here to potential different atmospheres or different EDL circumstances?
Absolutely. So Medley 1 definitely demonstrated, and it was the reason I think we have Medley 2, was it became the model of how you put an instrument package on a heat shield, how to work with the project to do it, so that they're not scared about putting holes in their pristine heat shield that's designed to keep their rover on the ground. We have a process now to do that. So you'll see missions going to Venus or Jupiter, Titan, those kinds of things. They'll all have instrumentation during entry, and NASA has the confidence to require that because we did so well with Medley 1 and hopefully again with Medley 2.
Mark did a really nice job discussing Medley 2, but I have to ask the question, in all my years at NASA, talking to subject matter experts from all 10 centers, what is a reconstruction lead?
Reconstruction is really important after a flight to understand exactly how and where the vehicle flew.
Oh, okay.
And without the proper data, it's really hard. You have to make some assumptions.
Okay.
So for instance, before Medley, when we didn't have an independent pressure measurement, we had to assume something about the aerodynamics of the vehicle in order to figure out how it flew.
Okay.
Now with that independent pressure measurement, we can nail it and we don't have to make any assumptions. So reconstruction lead is really key to understanding how we did.
See, you learn something new every day. I had no clue.
Yeah, he comes back up with that flight plan
Right.
that they had and where the data is along those flight plans. It's very important.
Now, speaking of that flight plan, with Medley 2, can you take the data from Medley 1 and kind of show what the flight plan is going to be for Mars 2020, or is that a completely different flight plan?
It's a lot the same because it's the same shape, size, vehicle. The mass will probably be a little different. They're using the same entry, descent, and landing system, but the atmosphere obviously will be a little bit different. The entry velocity will be a little bit different because of the different year.
Right.
But largely, we're going to use all of our MSL simulations as the basis for where we start on 2020.
No, I know, Steve, with game changing, you take technologies and you take them from a technology readiness level. We always talked about that 1 through that 9 scale.
Yeah.
And you're in that middle range.
Middle range, about 3 to 5 or 6.
Right. So, but with Medley, since you have proven you have a flight underneath you, and then you're working on Medley 2, is that still considered, technology at that level?
Yeah,
it's still not space ready.
Yeah, and it was like what Michelle was telling you was we learned so much through Medley 1 that we want to put different kinds of transducers to get the lower pressure range. We want to understand the back shell pressures and radiation rates. So we learned so much, so it's not really just a repeat of Medley 1.
Yeah, we have totally new sensors. Knowing what we know from Medley 1, we've moved a lot of our sensors, so we have kind of the same number of channels of data, but we've distributed them differently on the forebody and then moved some to the back of the vehicle.
Well, speaking of a new mission, we also have now, instead of Medley 2, we also have HIAD 2.
Yep.
Absolutely.
Which is a hypersonic aerodynamic inflatable decelerator.
Inflatable aerodynamic, yes.
We did it again. It's a hypersonic inflatable aerodynamic decelerator?
Yes.
Bravo.
Very cool.
Bravo.
All right, so that's a completely different type of EDL system from Medley 2.
It is.
And Franklin had a chance to sit down with the project manager, Joe Del Corso.
Yes.
And we're going to learn more about HIAD 2, so let's check that out.
So Joe, we're talking about HIAD 2. Tell me what has changed since HIAD 1.
So we've had a number of changes. The first one was we upgraded our thermal protection system. In HIAD 1, we used a Generation 1 thermal protection system, which was somewhat capable. It's low temperature capable, basically something on the order of 1,000 to 1,100 degrees Celsius on the surface. For HIAD 2, what we've looked at is much higher temperature capable materials, much more flexible and lighter weight. So now we're using custom built silicon carbide materials as an outer fabric. We're using COTS materials and some custom materials for our insulator systems. And then on the backside for the gas barrier, you have woven fabric systems with PTFE film wrapped around it. Our inflatable structure is also being upgraded. And then the other thing that we're doing is we are working on scalability. We're focusing on trying to get to a 12-meter scale. In order to do that, we've got to upgrade a lot of our equipment. We've got to work on something as simple as just picking up one of the gore seams. It takes a lot of development, a lot of careful coordination. So what we're focused on is not just upgrading our materials, but also upgrading our handling techniques, our manufacturing techniques.
Tell me about the HIAD timeline from the time it was conceived to where we are right now with HIAD 2.
So HIAD has been in development, previously it wasn't known as HIAD, but it's been in development now for almost a decade, and we still have probably another 4 years worth of work to do to get us to human access to Mars. We started out in 2006 doing material testing, and really all we were doing is we were doing low-level, trying to learn how to test fabric systems so that we could simulate an atmospheric entry condition. We were learning how to learn in the early phases. We had IRVI-1 happen. Unfortunately, there was a launch vehicle anomaly, so we lost that. But what it did do is enabled us to put in place IRVI-2 flight tests. People had enough confidence in what we were doing that they allowed us to build a build to print. That went up on a sounding rocket, launched out of Wallops, and it was an incredibly successful proof of concept. We had an inflatable structure, but no real TPS at the time, thermal protection system. Following the success of IRVI-2, we started up what we currently know as HIAD, which is the Hypersonic Inflatable Aerodynamic Decelerator project. During that project, we were doing all the lab scale development, small scale, little samples. We had learned how to do the initial testing. Now we were taking it through a maturation process, getting it ready for flight again. The third flight that we flew out of Wallops again was called IRVI-3. That was a much higher heating condition, and it was the first chance for us to actually test a thermal protection system with our inflatable structure. After the success of IRVI-3 and the closure of the initial HIAD, we attempted to fly
an orbital entry flight test called THOR, the Terrestrial High-Ad Orbital Reentry Flight Test. Unfortunately, due to the Orb-3 failure, we had to cancel THOR and we went back to a ground development effort. But unlike the first two ground development efforts, the third one wasn't focused on learning how to test or testing materials or developing materials. It's focused on scaling. So we did small scale in the early development phases, and now we're scaling to something more applicable for human access to Mars.
Now, the cool thing I understand about HIAD 2, that you guys have a partnership with ULA.
Yeah.
Let's talk about that.
So about a year ago, ULA announced that they wanted to use HIAD technology to recover their boosters as part of their new business model, affordability. And so we've been working on a flight demonstration with them over the last year and a half.
Yeah, and that would be at the 6-meter scale, which is about halfway to what ULA would need for their full booster recovery, 12 meters that Joe talked about on the video. And it's also the right scale for us to do maybe a technology demonstration mission leading up to putting humans on Mars.
So the idea is that you're using this HIAD technology to recover the first stage of a ULA rocket. And so is that going to be recoverable, and is that going to sort of land in the ocean? Is it going to land on dry land? How is that going to work?
They actually want to snatch it out of midair with a helicopter and to minimize any refurbishment costs.
Wait a minute, so you're going to have this booster coming down with the HIAD deployable shell.
Yes.
And then a helicopter's going to come and just kind of grab it
mid-air retrieval. Yeah, it'll come in. It'll have a catch hook, and the helicopter will come. It's a modified helicopter, obviously, but that's the plan.
Yeah, we've not air snatched anything of that mass yet, so that's a little bit of technology development as well.
Wow, I seriously hope that you go back to your ESM folks and do some modeling of that snatching, because I
reconstruction of the booster trajectory.
Reconstruction. So the reconstruction lead will be a part of that too.
Absolutely.
That's perfect. Well, we're looking forward to seeing that in action, because that will be something to see when that actually happens.
That would be awesome.
And also with HIAD, which is a win-win not only for ULA but for NASA. NASA gets a demonstration out of it, but then it kind of matures that technology to move on to an eventual test on Mars.
Yes.
Awesome. I tell you what, we've come to the close of just part one of EDL. I mean, we've covered a lot of technology today, and on the next show, we're going to be covering even more technologies.
Yeah, we should be talking about Adept and 3D Mat and heat.
And now, with regards to 3D mat and heat, that's more of the material side as opposed to the big system side, isn't it?
Right.
I'm looking forward to that, and so stay tuned. We're going to be talking more about EDL. You're watching NASA Edge.
mission specialist.
I'm Jeremy Hansen. I'm a mission specialist.
I'm Victor Glover. I'm the pilot.
I'm Reed Wiseman. I'm the commander for the Artemis II mission to the moon.
To the moon.
To the moon.
To the moon.
When I was young, I had a poster of the Earthrise picture, the famous picture that was taken on Apollo 8. And the fact that it was a human behind the lens that made that picture so profound and changed how we all thought of our own home was so amazing to me. The moon is not just a symbol of thinking about our place in the universe. It's not just a symbol of exploration. It's actually a beacon for science. It's a beacon for understanding where we came from.
You know, pushing ourselves to explore is just core to who we are. It's a part of being a human. That's our nature. We go out there and we explore to learn about where we are, why we are, understanding the big questions about our place in the universe. The exploration we're doing is the first few steps on the path of getting humans to Mars.
The Artemis campaign and missions have set such an ambitious goal for humanity that it's inspiring contributions from around the globe. Not just one nation is inspired and moved by this, but nations from around the globe are coming together.
When I look at the Artemis II crew with Victor, Christina, and Jeremy, they want to go do this mission. They are keenly driven. They are humble to a fault. It is so cool to be around them. Artemis II is a huge mission, but I hope we will look back and realize that this was one tiny step in humans on Mars and a sustained presence on our moon.
Before stage engine start.
Artemis II will be NASA's first crewed flight test of the Space Launch System rocket
and Orion spacecraft around the moon.
To verify today's capabilities for humans to explore deep space
and pave the way for NASA's long-term human and scientific presence
on the lunar surface.
We are ready.
We are going
to the moon
for all humanity.
We are Artemis.
The complexity, the systems that we've brought together in this one place to do something that very few places in the world do. Launch humans to a low Earth orbit, and hopefully with the new program into farther reaches of space. So when you go to a system or a place like that, you can't help but be overwhelmed.
Every space shuttle mission began with a fiery liftoff from Launch Complex 39 at NASA's Kennedy Space Center. The launch complex for the space shuttle had two pads, Pad A and Pad B. If the launch pads demonstrated anything, it's that complex is the right word for the two pad areas that handled the shuttles for about a month before they made their trips into space. Outfitted with everything a spacecraft and its crew would need to take the final leap into space, the pads handle fueling duties and crew support and held precision machinery for a range of payloads. Its graded floors and gray paint, along with armored boxes for instruments, telephones, and elevators, revealed a style more Spartan than space age.
You always find something that you didn't know. You've got so many systems. You've got system level experts and technicians that have been out there for so many years, dedicated, essentially, many of them, their entire careers out there. Even though, yeah, it's a lot of steel, a lot of wires and lights and tubing and that kind of stuff, it does it interfaces to, a flight vehicle, so you have those complex interfaces and there's always something to learn. It may look kind of Spartan, but yeah, it's got its hidden treasures.
The launch pad and all its fittings were built to withstand the brute force of a launch, which would rattle the pad with intense fire, corrosive exhaust, and thunderous sound waves.
Tested, let's put it that way. There's a tremendous amount of force that gets placed, liftoff on the structure, on the mobile launch platform, the MLP, heat, acoustics.
Each pad featured a shallow slope concrete pyramid about 40 feet high with a flame trench carved through the middle to channel exhaust away during launch. The launch pads were first built for the Saturn V rockets of the Apollo program. Back then, the launch complex did not have any permanent service towers because the support structure was on a mobile launch platform and traveled with the rocket to the pad.
It's an element of the history, to think back and to stand in places where people were launched to the moon. That has a real place for me.
For a shuttle, a pair of support structures called a fixed service structure, or FSS, and a rotating service structure, or RSS, were built at the pad and would remain there for all 30 years of flights. Both structures carried wiring and other infrastructure needed to support and protect the space shuttle for weeks at a time. A shuttle stack, meaning an orbiter attached to an external fuel tank and a pair of solid rocket boosters, would move to the launch pad about a month before liftoff. The shuttle was connected to networks of data cables, water lines, and the fueling system.
Unless you were out there when the workers and technicians and engineers were out there, it's hard to capture the elements of these people working together as a team, doing complex tasks, complex jobs, with a vehicle there that's just loaded with solid propellant. It could be dangerous as heck, it really is. And they did it routinely and made it safe.
There's also a bathroom, complete with stainless steel fixtures instead of brittle porcelain.
And when we do give give some tours up there, or groups come up there, I always point out that that's the last toilet on Earth.
Before launch day, the RSS covered most of the shuttle and provided a clean room that safely moved space probes, space station modules, and even NASA's Hubble Space Telescope into the shuttle's cargo bay without contaminating them. Other parts of the launch pad gave workers access to most areas of the shuttle stack, which stood up to 184 feet above the surface of the mobile launcher platform. The launch pad was woven throughout with propellant lines, wiring, and machinery.
There's so many complex things out there that could literally kill you, if you did something wrong, or not just yourself, it could be, devastating. And we do it safely, routinely, day in and day out. That's testament to the workforce and to what this nation built from the Apollo era, learning through hard lessons.
Launch day was also when most of the structures at the pad came to life, mostly by remote control to keep people a safe distance away. The huge white spheres on either side of the shuttle would pump supercold liquid hydrogen and liquid oxygen into the shuttle's external tank. Each propellant had to flow through long lines from the spheres about a half-mile from the shuttle.
As you get closer to launch, things just kind of step up, and you can feel it. Just pure excitement, really, as you're getting closer. And
the last people at the pad on launch day were the astronauts. They headed into the White Room, a kind of cramped locker room, before boarding the shuttle. With 2.5 minutes to go, the gaseous oxygen vent arm and its white beanie cap retracted from the top of the external tank, clearing the way for the launch. About 16 seconds before launch, some 300,000 gallons of water poured onto the launch pad. Though it might seem to be done to protect against the blazing fire, the water was actually for sound suppression to dampen the vibrations produced by 7 million pounds of thrust. The fire and thunder would produce a show unlike any other.
Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery. A tribute to the dedication, hard work, and pride of America's space shuttle team. The shuttle has cleared the tower.
some of our team would work late shifts, so you kind of had to go home and sometimes, watch it from the river, just like the other folks would, or something like that, which I actually kind of enjoy. If I couldn't make it into center in time, just kind of being out there with the general public and everything like that. Just sit back and watch the kids and people enjoy a beautiful launch. It's part of my joy, I guess.
Now that the space shuttle is retired, the pads are being prepared for another transition. The structures that marked the space shuttle era have been removed from Launch Pad 39B, so it can handle several different types of launchers that are expected to make up the next generation of space exploration. Pad 39A, the starting point for some of NASA's most famous flights, including Apollo 11 and the first and last shuttle flights, will look as it did during the shuttle years for the near term, echoing the thundering success of the space shuttle program.
Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery.
2 solid rocket motors. That's a pretty rough ride, but you can feel the thrust tail off right before they separate. And you get an indication PC less than 50, and then you're going to be there 2 minutes 5 seconds or so. They separate away. There's a huge flash in the front window, a big bang. You can hear the set motors push those away, and then it's just as smooth as can be on those main engines. They're phenomenal pieces of machinery.
The Space Shuttle main engines have been one of the brightest success stories of the Space Shuttle's 30-year career. Powered by a combination of fuel and oxygen, a single SSME, as the engines are called, produces about 500,000 pounds of thrust. Working with the 2 solid rocket boosters for the first 2 minutes of launch, 3 main engines push a shuttle up to Mach 25 and into orbit in 8.5 minutes.
We call the SSME an extreme machine, and it's extreme because on the inlets you got liquid oxygen and liquid hydrogen, and liquid hydrogen is minus 420 degrees Fahrenheit, so it's extremely cold propellant that we're putting through the turbo machinery, and then we're burning it in the main combustion chamber at 6,000 degrees Fahrenheit, so that's hot enough to melt iron.
It can do that without melting because the engine pumps the cryogenic hydrogen through a series of 1,040 tubes lining the nozzle. The supercold fuel keeps the flames from touching the sides of the nozzle. There also are a pair of turbopumps that move the propellants through the machinery and into the combustion chamber quickly. The turbopumps alone produce more power than a locomotive, even though they would fit on a desk. Providing that amount of power safely calls for extensive testing and inspections of each engine and their turbopumps. A main engine gets examined from the time the shuttle lands until liftoff. Highly trained technicians use long, flexible lenses called borescopes to look at each engine's insides for cracks and other defects.
A skilled technician engineer can perform a real good borescope inspection of bearings, seals, and actually the turbine blades, nozzle vanes, pump blades, and diffusers.
The engine's success did not come easy. Engineers began testing engine designs in 1975 at NASA's Stennis Space Center in Mississippi. Just getting the startup sequence right took months and months of complex work.
Well, of course, the first test of the Space Shuttle main engine on A1 test stand was like 20 milliseconds. I mean, it took a long time to develop the start sequence of the engine, and it was 20 milliseconds at the time, finally 40. They worked their way up to 1.5 seconds, which is a critical time period in the thrust buildup of the start sequence, and then it just went on from there, and it took a long time to actually finally get to main stage.
The shuttle's main engines made their first flight test on April 12, 1981, along with the rest of the Space Shuttle system. Although the engines had been fired on test stands, no crew flew with them until Commander John Young and pilot Bob Crippen rode them into orbit on STS-1.
And when that whole vehicle got together, we put the crew in and we counted down, and we saw engine ignition and all 3 engines come up. It was just an extremely rewarding experience to see that and see the SRBs fire and that whole orbiter take off and fly. It was hard to describe because of all of the activities that I know led up to that and all the people involved in it to see that as a successful mission, because we didn't have an opportunity to fly it unmanned before we flew it manned. So that's the first time this country really did an experiment with people on board, and it all worked.
Though the shuttle engines are smaller than the mammoth F-1s that powered the Saturn V's first stage, they had to be far more efficient.
And then this is the first time we had to design an engine that would operate for 8.5 minutes. In the Apollo program, the first stage engines operate for about 200 seconds, and it basically gets you up to about 50,000 feet or higher through the heavy atmosphere, and then the first stage is spent and then the second stage takes over. In this case, the SSME was designed to start on the ground, have the ability to health check it before the solid rocket motors ignited, and then commit the launch, and then stay running all the way through orbital injection velocity. So that made it run for 8.5 minutes. So that was different than engines we had built previously.
Along with the brawn of hundreds of thousands of pounds of thrust, the engines carry very delicate brains that take constant measurements of the systems dozens of times every second.
This is the first engine we built that had an active onboard digital computer. And the computer has a program in it that runs through its full cycle in 20 milliseconds, so 50 times a second. It's out reading valve positions, sensor data, and we have algorithms in there that allow that engine to have what we'll call health monitoring. So we have active flight red lines that in the event that temperature should exceed the limit, that engine will automatically shut itself down to prevent a catastrophic failure.
No mission ever failed because of a space shuttle main engine. Not a couple saw close calls during launch. In 1985, one of the engines on Space Shuttle Challenger picked up a problem.
So they actually shut that engine down at about 18,000 feet per second, let the other 2 engines run the vehicle until it reached the actual velocity required to make orbit. So it was a successful mission, and it just showed that the redundancy built into the engines really paid off.
The Space Shuttle's main engines also had a requirement no other engine faced before. They had to be reusable.
Reusability created issues with hardware embrittlement. It was hydrogen molecules embedding themselves in the material, causing embrittlement later on. So that created life cycle issues, and we were always talking about what's the remaining life in the hardware.
The SSMEs produce nothing but steam when they fire, another departure from previous rocket engines.
Oxygen, hydrogen, when it combines and creates water, it's very clean. A lot different from the Apollo days when you had liquid oxygen and kerosene. Well, this engine's extremely clean. And people are amazed when they look at the engines in the shop that have flown 10 times or more. They look brand new.
The shuttle main engines have proven to be extremely reliable machines with a record of reusability and success without parallel in rocketry.
But SSME's in a class all by itself. And of course, the reliability that we get out of the SSME is is the reliability and the performance that allows the shuttle to fly.
As far as the extreme temperatures, the pressures they operate, the fact that they have been reusable and so reliable from STS-1 to STS-135, I still rate the main engines at the top.
For two of NASA's storied space shuttle orbiters, the lights have gone out for the last time. Discovery and Atlantis were permanently powered down in December 2011 as teams at NASA's Kennedy Space Center in Florida prepare the vehicles for public display. It was an emotional milestone for the technicians, test conductors, and system engineers who have spent years, even decades, preparing each spacecraft for its next flight.
It's okay. You can
The final assignment for Discovery's processing team on December 16, 2011, was to close the 60-foot-long payload bay doors. Many gathered for one last look inside the shuttle's payload bay.
Even at the Smithsonian, there's no plans to open those payload bay doors on Discovery, so as far as we know right now, those doors will never open again.
Then it was time for the spacecraft operators on Discovery's flight deck to shut down the power.
Okay, PRT 1 off now, PRT 2 off now, PRT 3 off now.
Actually, our center director, Bob Cabana, was there, so he actually pulled the plug on that power up sign, and that was it for Discovery.
December 22nd was the last day that work on Atlantis would require power. Its starboard robotic arm and Ku-band antenna were stowed inside the payload bay for the vehicle's upcoming move into temporary storage.
So we were anxious to get as much work done on Atlantis and get to a point where we could then continue to do work on Atlantis in the vehicle assembly building while she was staged there in a waiting mode.
Then the focus turned to the flight deck as Atlantis, known by the shuttle team as OV-104, was powered down for the last time.
AC bus sensor 1 off now. AC bus sensor 2 off now. OV-104 final power down complete.
Discovery and Atlantis have gone dark, but the team has one more power down to get through. Shuttle Endeavour will be next.
It's sad, but you know, progress, you have to move on. So something has to be done, and I'm extremely proud to be a part of it till the end. Extremely.
Throughout the Space Shuttle program, a familiar launch day sight was the shiny silver vehicle known as the Astrovan. Before each launch, astronauts smiled and waved as they left the crew quarters and boarded the van that would carry them to meet their fully fueled ride to space. The vehicle would wind its way across NASA's Kennedy Space Center in Florida as it carried the crew to the launch pad. It was an exciting ride for the crew members, but especially for the rookies ready for their first trip to space.
The first time, it's just everything about it. It's just, you know, the anticipation, excitement, you know, you're a little bit nervous, but it's, I mean, it's just neat to know that, you know, you're one in the series of a very long line of astronauts that rode in this vehicle going to the pad, you know, for flight to space, so it's pretty cool.
Early shuttle crews had fewer astronauts, so they rode to the launch pad in an Apollo-era transport van. But since 1984, each shuttle crew traveled those 9 miles aboard the current vehicle. The modified Airstream motorhome only racked up about 27,000 miles in its 27 years of service. That's because it's used solely to transport the astronauts for each mission.
But I always associate this vehicle with flying, because you only get in here twice. You get in here for TCDT, which of course is the launch rehearsal, and then launch day.
The only other time the Astrovan was used was to take the astronaut back to crew quarters after landing. The vehicle's appeal is rooted in its tradition rather than its decor.
It's not really extravagant, kind of like bench seating, and it's pretty crowded on launch day, especially with a crew of 7. You know, I think everyone's trying to cut the tension with a joke or two from time to time.
The interior's narrow center aisle is paralleled by long benches. Lift-out sections accommodate the ventilator units used to circulate cool air through the astronauts' bulky orange launch and entry suits.
This is the only place they have liquid air, and liquid air is really good. You know, we have this this cooling garment that circulates water cooling, and in the hot Florida sun, it's nice to have it. They plug that liquid air into you, and it just blows this cool air throughout your suit, which is really nice because it actually dries your suit. And the only place we get to have it is in here. And I don't know why, it was like a special treat on launch day.
Now, while each crew no doubt had their own unique take on their ride to the launch pad, Shuttle Atlantis STS-135 mission crew took in the significance of the final ride for the Space Shuttle program.
It was really special this time because there were so many people here. And I think even though it's kind of an anxious time as you head out to the launch pad because you know this might actually be the day, on this particular day, you know, the last flight, I think we were all really amazed at how many people showed up. I mean, even on the road, you hang the right turn to go to the pad, and the road was lined with people waving American flags. It made me feel good, you know, to know that the shuttle program meant this much to so many people, and not just national, but international. I mean, a lot of people turned out to watch the grand finale, if you would.
While the vehicle won't be taking any more shuttle crews to the launch pad, NASA plans to keep it ready to ferry future astronaut crews to the pad.
I would like to keep this tradition. You know, I don't know if any of us will get to fly on the next vehicle, whatever that vehicle may be, a U.S. vehicle, but it would be kind of neat to have some of it be the same.
You know, and actually traditions are important in a business like this. It keeps everybody connected.
Everybody ready?
Let it happen, Captain.
Hold on, everybody.
So after riding the Astrovan to the launch pad a number of times, what would it be like if a Space Shuttle commander got the keys to take it for a spin? STS-135 Commander Chris Ferguson found out.
There's 0 to 35 in a minute and a half. That was the most white-knuckled event I've had. I pronounce this vehicle fit for another space program.
Orion is getting ready to launch. My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right: fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. we are headed 3,600 miles above Earth, 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home. The upper stage of the rocket triggers separation. Orion's jets fire to turn it into the proper position to re-enter Earth's atmosphere. No matter what happens now, we're coming in. 75 miles above Earth, the spacecraft enters the atmosphere. Things happen quickly. We're now traveling more than 20,000 miles per hour. Air particles pushed out of the way heat up. An envelope of hot plasma surrounds the vehicle as it plummets towards Earth. The plasma reaches temperatures of 4,000 degrees Fahrenheit, almost twice as hot as molten lava. This may be the most dangerous part of the flight. Mission Control is monitoring all the data from the spacecraft, and then we lose communication again. No data can penetrate the plasma. Orion is on its own. Orion is inside a fireball. Onboard systems ignite jets to keep the ship pointed correctly, so the specially constructed heat shield takes the full brunt of the inferno. This is the largest heat shield of its kind ever made. Orion's computers command the spacecraft to bank like an airplane, keeping a precise path to the landing site. Even though we've slowed from 20,000 miles per hour to about 300 miles per hour, we're still traveling amazingly fast. We must slow down to safely land in the ocean. Luckily, we have parachutes. Specially designed for Orion, the parachutes help us hit the brakes, but not too quickly. One day people will be aboard, so deceleration must happen in stages to keep things comfortable for the crew. The forward bay cover jettisons. Two drogue chutes deploy and slow the returning spacecraft down to 175 miles per hour. Then, the three main parachutes open. Once fully engaged, this canopy would cover an American football field. It takes parachutes this size and strength to slow our descent to 20 miles per hour, and then splashdown. For this first flight, we won't have astronauts inside, but we still have some very precious cargo. The flight data from this mission is stored inside the Orion spacecraft. While our flight might be over, there is still a lot of work to do. Onboard sensors recorded every detail, from launch to flying in space, to re-entry to landing. Flight tests are difficult and complex, but they give us confidence that the systems we have designed work under real flight conditions. It's great to be a part of this first space flight for Orion, and we're looking forward to beginning a new chapter in human space exploration.
Excited to feature the Honey, I Shrunk the Payload Challenge on our show. The challenge was made possible by the NASA Tournament Lab, which facilitates the use of crowdsourcing to tackle NASA challenges. The challenge is funded by the Game Changing Development Program in support of NASA's Lunar Surface Innovation Initiative, which champions technologies needed to live and work on the moon. Judging for this competition included representatives from the Space Technology and Science Mission Directorates, as well as engineers from NASA's Jet Propulsion Laboratory. The instrument payloads developed under this challenge could enhance future science missions on small platforms like rovers, helicopters, and CubeSats. Data from these types of crowdsourced miniaturized sensors could enable future robotic missions to protect and improve life on Earth and in space, and to discover the secrets of the universe. Finally, the Center of Excellence for Collaborative Innovation managed the contract with HeroX for the competition and awards under the Prizes, Challenges, and Crowdsourcing program at NASA. Clearly, a lot of effort went into this incredible challenge. And now, on with the show.
Welcome to NASA Edge, an inside and outside look at all things NASA.
Hey guys, today we're going to do things a little bit differently on set.
I know, the set looks great. I look great. This is great.
Today we're talking about miniaturized payloads, about HeroX's Honey, I Shrunk the Payload challenge, where teams are shrinking down flight hardware to fit on small robots that NASA is sending back to the moon.
You know, Blair, I really love this idea, and I'm guessing you're going to tell us about a mission to do just that? Yeah, and I'm guessing it's going to be a super cool idea, Chris, just like all of Blair's ideas.
That's right, Franklin, but to help our audience understand exactly what I'm talking about, I had a chance to sit down with NASA Langley's Mark Thornblum to tell us all about the Honey, I Shrunk the Payload challenge.
Sweet. Hey, let's check it out.
Mark, you work with Game Changing, and not only is that a really cool name, tell us what it is and how you develop these cool technologies for NASA.
Sure. Well, Game Changing is the Game Changing Development Program Office based out of NASA's Space Technology Mission Directorate. And we have about over 100 projects that are at what we would call the mid-technology readiness level. So they're great ideas and great new concepts for how we would have either a new technology or advance a current state-of-the-art that has a future in making and enabling our future missions for NASA, either for NASA science or for NASA exploration. And a lot of our projects right now have a future on lunar exploration and a sustainable presence of humans on the lunar surface.
And that's with Artemis, right?
Right. Most of our projects right now, or at least a good bit of them, are working on what we'd call a technology demonstration in order to prove themselves to be ready to be infused into an Artemis-like mission. So what we do is we start where the projects are now. They're better than just a good idea at this point. They've been shown that they're feasible and that they've shown that they really have a promise to work. So we work with these projects around the country to get them ready, get them packaged, form, function, and then demonstrated either on the lunar surface or on a ground demonstration or maybe a suborbital flight. If they're successful, then our goal is to put them onto a mission and to infuse them, or to infuse them into the commercial market and let these technologies become commercial products that the whole space economy can utilize.
You now have competitions where you're inviting people to participate in this process. Tell me about these competitions that Game Changing's working with.
Right. Well, let me specifically talk about Honey, I Shrunk the Payload, because that's where we want to kind of talk about today. With Honey, I Shrunk the Payload, we are engaging the public. So in this particular competition, we were interested in small instruments. Our platforms for space flight have gotten smaller. The rovers are getting smaller. Even the lunar landers that are developing now for the commercial lunar payload services, those are a little bit smaller in scale than what you might be kind of used to for, like, I'd say, a human landing system or something like that. So with these smaller platforms, you need smaller instruments to put on them just because of their capabilities. And so with Honey, I Shrunk the Payload, we have asked the public to generate ideas, submit their ideas, and really see what they've got and see what's out there. So we get a lot of benefit out of that. We get to see what small instruments are out there, which ones would be useful to advance science and exploration on the lunar surface. And then hopefully we get to actually fly them.
Was there any specific guidance that you gave the participants as they worked at this competition?
Absolutely. So we knew that we wanted to engage the public with this, and we knew that we were going to have to help them. So we worked with our partners at JPL, and we came up with what we would call an interface document. We gave all the participants constraints and parameters for how they needed to design their payload. So first, it has to be a certain size.
Small.
So think bar of soap. So 100 millimeters by 100 millimeters by 50 millimeters. That's the package that you have to fit inside. You have to weigh less than 400 grams. And then on average, you can only consume about 4 watts of power on average. And that's kind of the parameters that we gave them. And then the last thing was your instrument has to do something useful and interesting on the lunar surface. And it has to also be applicable to the types of challenges that NASA is facing for Artemis and for sustained presence on the lunar surface.
And it makes perfect sense, because if you are sending smaller spacecraft, then you will need these smaller instruments.
Right.
And so how do you know when you've been successful at game changing? When do you know that you've actually achieved your goal in delivering this technology?
So in the world of technology development, we have a numerical scale, which we call appropriately the technology readiness level. And it's a scale from 1 to 9, 1 being basically a really good idea on the back of a napkin. Okay, that's, hey, here's a great idea.
Where all minds stop.
Yeah, right. And a lot of good ideas end. And then all the way to TRL 9, or technology readiness level 9, which means used regularly for a particular mission, available to purchase on the commercial market, and is readily accepted as this is a space flight, instrument, if we're talking TRLs for space flight. And so all of our projects are in that kind of 4 to 6 range, and it can go a little below, it can go a little above, just depending. Typically, our projects end with some type of demonstration, and that can be on the ground, in a lab, that can be on a suborbital rocket flight, it could be on a sounding rocket, it could be on a full LEO mission, it could be on the space station, and in this case, for Honey I Shrunk the Payload, we're hoping that this will be on the lunar surface demonstrated. So when those demonstrations are done, that typically gives us confidence that from a technology standpoint, that particular technology has the fit, form, and function to be useful and survive in that environment that we're going to put it in. So at that point, we would then look for infusion opportunities. We look for a mission to adopt that technology to use, or we look for a commercial partner to go and develop it further and then commercialize it.
Man, that was probably the best interview we have ever done, Blair. Spot on. Yeah, very informative, but now I want to know more about Honey I Shrunk. Uh-oh. What? What is it? What are you doing?
I just finished shooting the first segment of our show with these way cool miniaturized versions of ourselves. I mean, look at the accuracy. I mean, I'm depicted perfectly. And you can see the detail. It's so profound.
Now, how did you do all this without using our voices?
Oh, trust me, I got that all worked out.
I don't like the way that you're handling me, Blair.
It's fine.
I don't think you should be doing this with toys.
Oh, no, it's acceptable.
Hey, I look pretty good. Well, I guess I look pretty good as well. Where are we at, Chris? You're watching NASA Edge. And inside and outside?
Man, we don't need to do that. I've already done that. I did the first segment. It's already done.
You already interviewed Mark?
Oh, yeah, it was great. He's great.
So what action figure did you use for him?
Actually didn't use action figures, did the actual Mark.
Oh, he was 1-to-1?
Yeah, 1-to-1. Yeah, scale lingo. Yeah, absolutely.
Now, what kind of scale are we talking about? Are we talking about CubeSat small, or are we talking about Saturday morning cartoon shrink ray small?
It's a good point, Franklin, because I love the shrink ray idea, and that's what I thought it would be. But it turns out that they're looking about wallet size, which is kind of CubeSat size, but they're using real science and engineering to bring that technology into this new form factor for the challenge itself.
Chris Small.
Yeah, there you go, right? So I had a chance to talk to the teams about their particular payloads and how they actually managed to get it down to size. Let's check it out. Joining us now are 3 representatives for the finalists competing in the Honey I Shrunk the Payload Challenge. Those teams are Sunslicer, Water Snooper, and URAD. Let's talk about URAD first. Christian, can you tell us about your payload, URAD?
Sure. So URAD, or microrad, is intended to be a more compact, lower-cost radiation sensor that will enable future missions to deploy radiation monitoring equipment much more broadly than has been done in the past. So the name was inspired by the radiation assessment detector that was carried on the Curiosity rover, which was used to survey the Martian radiation environment both once the rover got to the planet, but also to assess what the radiation dose would be on the journey to Mars. So sort of following on from that basic concept of being a very generic, broadly applicable radiation sensor that can tell you a lot about different types of particles and measure the energies of those particles, we decided to name our payload microrad, reflecting that it has as much as possible similar capabilities, but in a much smaller package.
What were the challenges of taking that standard radiation detector and sort of getting it down to that very wallet-esque size payload which you accomplished?
So there were definitely a lot of challenges, both implementation difficulties. For example, the chip shortage really caused us a few issues, but also technically as far as getting the capabilities we wanted in such a small package. But thankfully, we were able to leverage some novel technologies that really only became available in the last couple of years to do that. So that was definitely a challenge. Basically, how many new technologies we were trying to leverage and cram into such a small payload, and also do it with such a small team and on such a short schedule.
Christian, what are some of the broader uses for the technology you've developed for URAD?
So URAD is very unique as far as being very low cost and small size. And it's also not specifically focused to any one type of measurement. So it's very good at characterizing sort of a general radiation environment. And that sort of lends itself to a lot of other applications beyond the immediate needs of NASA or the immediate needs of the Artemis program. Potentially, I could see applications related to national security, for example, assessing whether someone's trying to smuggle radioactive material into a port, for example. But there's also other applications in space. For example, it's small and cheap enough that you could put one on a large number of spacecraft, and then that would give you spatial diversity as far as the radiation measurement, which could be useful for understanding the structure of CMEs, perhaps, or perhaps it could be used for being able to discriminate between hostile anti-satellite action versus natural effects as far as when radiation effects show up on a spacecraft, being able to tell, is someone pointing a particle accelerator up at the satellite, or is that the radiation that's just coming naturally from the sun, for example.
Christian, thanks so much for taking the time to explain URAD. Next, let's talk with Phil, who has Sun Slicer. Phil, can you tell us about Sun Slicer?
Hello, Blair. Yes, Sun Slicer is a miniaturized X-ray spectrometer that's been adapted for the harsh lunar environment, as well as to ride around on a miniaturized lunar rover.
What would you use a spectrometer, X-ray spectrometer for on the lunar surface?
We've tried to keep the instrument as versatile as possible. So there's many different science experiments you can do. The big one is prospecting for the purpose of in situ resource utilization. And we can leverage the sun somewhat as a X-ray or alpha or radioactive source to illuminate the regolith, and then leveraging X-ray spectroscopy, we can see what the rock-forming elements and hopefully their relative abundances in the regolith.
I like that, a lunar prospector of sorts.
Correct. There are also a couple of other applications. For the initial phase of the competition, we came up with a cool science idea that allowed measuring active regions of the sun to very high angular accuracy compared to what you could do with orbital assets. And that experiment was all about lunar rover mounted sun slicer pointed at craters on the moon that could shutter or block the sun's X-rays as it rose or fall behind that crater, and then get enough imaging information to map the size of those active regions. And then lastly, for free, you get radiation monitoring ability up into the high X-ray range, which is interested in to keep our astronauts safe when they return to the moon on the Artemis program.
Awesome. Thanks so much, Phil. Appreciate it. Let's go now to Tibor Pasher, who is actually in Budapest, and he's going to tell us about Water Snooper. Tibor, what is Water Snooper?
Hi, Blair. Greetings from Budapest. The Water Snooper is a very small, actually a neutron detector, which is able to look for volatiles, hydrogen and water ice on the moon surface.
How did you accomplish this task in such a small form factor for Honey, I Shrunk the Payload?
The idea is actually from our colleague David. He was thinking of how can we use industrial CMOS sensors to detect neutrons. This looks crazy, but we managed to put just 3 really good quality industrial CMOS sensors in this very small 10 times 10 times 3.4 centimeter box actually, and it looks fine. It works everything. The challenge was actually to put also the electronics into the box, but we managed that as well.
Now, the idea would be that you would put this payload on a rover, correct?
Yeah, that's correct. Actually, so if we manage to put the snooper on a rover, then we can just go around and look specifically water if we know that the area is a potential area for water ice or hydrogen. On the other side, we can make a kind of prospecting map, looking at what is there actually, where it would be useful to dig for water ice. So the snooper is able to look about 1 meter into the regolith, and this is the upper region of the regolith where we expect to have water ice. And if we know how much is there, how much water equivalent hydrogen is there, then it might be a good chance for somebody to follow up, dig it up and make water and then hydrogen and oxygen from the water ice.
That's awesome. Tibor, thanks so much to you and your team. And I want to thank everybody who joined us today, all the participants for Honey, I Shrunk the Payload. We wish you all the best of luck and hope to see you all fly these payloads to the moon. Thanks, guys.
Thank you so much.
What really impressed me about these teams, guys, is the fact that they've taken technology and miniaturized it, basically shrunk it down for the challenge, but all the things they're looking at are all things that NASA needs to accomplish for us to develop the sustainable presence on the moon in Artemis.
That's a great point. NASA's not going to be able to do it alone. We're going to need, commercial industry, academia, other government institutions, the international community, and the general public. And this is a great way to get the general public involved and excited about the Artemis mission.
Yeah, and crowdsourcing the development of flight hardware is just brilliant. And this will be the first time that it will be done.
Not only that, but this technique will be used in other challenges to come down the road.
Yeah, and the payload interface requirements were developed by JPL, and all the teams had to submit their payloads to them for testing. My next interview had a lot to do with that. Let's check it out. I'm here with Josh Ravage, who is a mechanical engineer at the Jet Propulsion Laboratory, and he was part of a team who received the Honey, I Shrunk the payloads to test their flight worthiness. Joshua, can you tell us a little bit about the testing process?
So it's actually an interesting problem figuring out how to test these payloads, which came from very, very diverse places with very diverse functions, and that were going to be potentially accommodated on a mission to the moon, on a lander that wasn't yet selected, and on a host spacecraft mission that also wasn't selected. So to do this, we took kind of a twofold approach. The first, we looked at just characterizing whether they would survive during launch events. So we did random vibration testing using standard NASA specification for this. We took all 3 payloads, put them on a vibration table, shook them, see if they turned on afterwards. Everything so far so good. The other aspect was thermal vacuum testing, and that's did we think that we could survive in the lunar environment. This, we took a more custom approach. The standard NASA spec wasn't quite designed for this mission where it could be a single cycle on the lunar surface. So we took a pretty simplistic test approach of 1 cycle from minimum temperature to maximum non-operational temperature, and then 1 cycle from minimum temperature up to operational temperature, turning on every 15 or 20 degrees Celsius or so, see if these payloads are able to turn on, how they function, and inform the future if they move to a lunar mission and were accommodated. Did we think that they'd be able to survive and operate?
Now, these payloads were smaller than most payloads that would fly. Did that impact the testing at all?
These payloads were small. We actually originally set them at about half U, which is standard CubeSat size, about half of that. So it's about 10 centimeters, 10 centimeters, 5 centimeters. That they were so small, actually, the truth be told, made testing a little bit easier. We didn't need particularly large, complex tooling to be able to accommodate them. So it's actually made the testing go fairly smoothly, and it was pretty convenient.
What is the next step for these 3 payloads?
Yeah, so testing through vibration testing appears to be successful. Thermal vacuum is actually, as we speak, almost completed, and so far so good. If any of these are selected to actually fly to the moon, we'll begin the official accommodation process with our host missions. There'll be some interface. I'm sure interface hardware will be designed to manage them. They'll get delivered to those missions, and they'll get tested and certified along with those missions. And hopefully they'll get a ride in the next couple of years.
Sounds great. Josh Ravage, thanks for joining us on NASA Edge today.
Thank you so much.
It's interesting that these payloads from these teams were tested at JPL just like any other flight hardware or satellite would be for a mission. The vibration testing, the thermal vacuum, all of that. So these are legitimate flight hardware that could fly on any mission.
Yeah, that's what I love about what Hero X has done here. And in addition to a catchy title that led to a cool part of our show, as you said, Franklin, winners or just any of the teams that participated and got their hardware flight ready, they have a chance to fly to the moon. This is an incredible thing, and to have your hardware there is great. Now, I have some good news.
Okay.
There has been an announcement for a winner
Oh, really?
for the challenge. So all the teams did a great job. The 3 finalists were spectacular, but we do have a winner. It is Phil Jobson of Sunslicer.
The miniature X-ray spectrometer.
Yeah, with that cool dust mitigation gear mechanism.
Oh, very
really cool stuff. Yeah, they won. I sent him a message, and he sent us his thoughts on winning this challenge. Let's check it out.
Thanks for the kind words, Blair. Team Sunslicer is thrilled to rank first place in the inaugural NASA Lunar Payload Challenge, especially in the company of 2 other exceptional teams in Puli Space and Microrad. We're excited, over the moon you might say, in the possibility that Sunslicer, created in a Santa Rosa garage, may fly and validate 18 months of extreme commitment and sacrifice. I cannot thank enough my teammates Garrett Jernigan, John Doty, Brian Silverman, Vadim Gerasimov, and the countless volunteers, partner and sponsor companies for their tireless efforts. Please check out sunslicer.com for full credits and updates. And in the words of Ralph Cramden, to the moon, Alice.
I tell you what, Phil and his team did a really good job with Sunslicer. I mean, I'm looking forward to seeing that on the lunar surface one day.
Man, I can't imagine entering a contest like this and actually winning, knowing that, as you said, your technology, your creation might one day fly to the moon.
Yeah, we talked about this before with CubeSats. Can you imagine your resume at that point? You go like, I've done X, Y, and Z, but I also have a payload that's working on the moon. That's really cool.
And in addition to Sunslicer, we can't forget about the other teams that were in the competition.
Absolutely. And so when we were talking to the teams, we were talking to Tibor in Hungary, his whole team, which wasn't just there. They had team members in CERN, they had team members all over the place. The effort that went into this, and Christian, who was up at MIT, and his team, lots of hours, lots of creativity and innovation came together. And the good news, guys, and this is really important, that whether you win the competition or not, because of that testing that they've all gone through, each one of these payloads is flight ready and has the potential to fly to the moon. Good job, Hero X. Good job, game changing in NASA. It looks like we got a winning plan for the return to the moon with Artemis.
You're watching NASA Edge.
An inside and outside look at all things NASA.
With show-ready technology.
I found a flaw in your system.
Uh-oh.
It's not the scale, Franklin.
Yeah.
You notice that?
You're like taller than everybody.
Hold on a second.
Oh,
what do you think? Something like that? Yeah, it's more like it. Yeah,
it's more like it.
Yeah.
The mystery surrounding the whereabouts of a supermassive black hole has deepened. Despite searching with NASA's Chandra X-ray Observatory and Hubble Space Telescope, astronomers have no evidence that a distant black hole, estimated to weigh between 3 billion and 100 billion times the mass of the Sun, is anywhere to be found. This missing black hole should be in the enormous galaxy in the center of the galaxy cluster Abell 2261, which is located about 2.7 billion light-years from Earth. Nearly all large galaxies contain a supermassive black hole with a mass that is millions or billions of times that of the Sun in their centers. Since the mass of a central black hole usually tracks with the mass of the galaxy itself, astronomers expect the galaxy in the center of Abell 2261 contains a supermassive black hole that rivals the heft of some of the largest known black holes in the universe. Such black holes are usually found in the centers of galaxies. Using Chandra data obtained in 1999 and 2004, astronomers had already searched the center of Abell 2261's large central galaxy for signs of a supermassive black hole. They looked for material that has been superheated as it fell toward the black hole and produced X-rays, but did not detect such a source. In 2018, a team of scientists used Chandra to get new, longer observations obtained that year of Abell 2261. They also considered an alternative explanation. What if the black hole was ejected from the host galaxy's center? During a merger of two galaxies, which likely happened in the past to form Abell 2261, the central black holes in each galaxy could have merged to form one enormous black hole. This violent event would have also generated a huge amount of gravitational waves. If the gravitational waves were stronger in one direction than another, theory predicts that the new, even more massive black hole would have been sent careening away from the center of the galaxy in the opposite direction. This is called a recoiling black hole. Astronomers have not found definitive evidence for recoiling black holes, and they do not know whether supermassive black holes even get close enough to each other to produce gravitational waves and merge. The detection of recoiling supermassive black holes would embolden scientists using and developing observatories to detect gravitational waves from merging supermassive black holes. The mystery of this Titanic-sized black hole in Abell 2261 therefore continues. Although this latest search was unsuccessful, hope remains for astronomers looking for this supermassive black hole in the future. Once the James Webb Space Telescope launches, astronomers should be able to use its capabilities to join with Chandra's and others to look at Abell 2261 and others like it.
En la NASA, nuestro recurso más importante es nuestra gente.
Una fuerza laboral talentosa, diversa,
dedicada a estudiar los secretos del universo y de nuestro planeta natal.
Para el beneficio de la humanidad.
La comunidad hispana contribuye a diario a misiones esenciales de la agencia.
Trabajando para mantener seguros a nuestros astronautas y misiones en órbita.
Monitoreando los efectos de cambios climáticos.
Prediciendo eventos meteorológicos que pueden afectar a nuestras comunidades.
Ayudando a la respuesta en desastres.
Diseñando los aviones de tecnología sostenible del futuro.
Desarrollando ciencia y tecnología a bordo de la Estación Espacial Internacional.
Desentrañando los orígenes del universo.
Buscando señales de vida antigua en otros planetas.
¡Hemos llegado! Perseverance llegó y preparándonos para llevar a la primera mujer y a la primera persona de color a la Luna.
Nuestra diversidad de orígenes y culturas impulsa nuestra capacidad para innovar.
Y hace que nuestra agencia sea más fuerte, incluyente y diversa.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos hispanos.
Somos NASA.
Sigue nuestras historias en NASA en español.
imagine living in a modern metropolis full of opportunities, endless sunshine, Hollywood celebrities, and fancy cars. That was the American dream. That was Los Angeles in the early 1940s. But in the morning of July 26, 1943, in the middle of World War II, the sun didn't rise over the city. A throat-burning noxious gas covered the sky. Entire city blocks faded away. A thick fog that made people's eyes sting and their noses run had taken hold of the city. They were under attack. Or so they thought at the time. But the attack didn't come from the outside. Massive wartime production facilities, a high increase in population, and the exhaust fumes of cars, combined with the geography of the valley, made the city a trap for air pollution. The day after the first event, city officials tried to control the damage by restricting emissions from power plants and industry. But while these efforts helped reduce air pollution, smog episodes continued to occur. Scientists discovered that volatile compounds, like the gases produced due to evaporation of gasoline during the refining process, and nitrogen oxides generated during the combustion inside car engines, both reacted with sunlight, creating a highly toxic gas, ozone. And sunlight isn't precisely something Southern California lacks. But this wasn't a localized phenomenon. Other U.S. cities also experienced high ozone concentration levels. These cases made society aware of the importance of keeping track of emissions and lead politicians to implement policies to improve the quality of the air we all breathe.
Air quality is a serious global problem. More than 7 million people die per year due to the effects of air quality.
There's many economies around the world that are growing, and what the United States has seen is that your economy can still grow while your air pollution levels are decreasing, but it takes some effort to do that. The good news is that air pollution levels around the world are gradually decreasing.
In fact, air quality trends have improved in the last decade as a result of policies developed to reduce air pollution.
Back in the 1950s, Los Angeles had a really awful air quality problem.
So when the Clean Air Act began, it was a commitment to cleaning up the air. But the actual legislation and the differences took a long time to put into place. And so here in Asia, we're at the beginning of that process.
These nations that are still increasing in their standard of living and increasing in their pollution levels can learn from what's happened in the industrialized nations. We can have a more rapid decrease in pollution levels.
Now we know how to put together effective policies to control air quality.
Understanding that economic growth and industrial development bring air quality problems and knowing how to deal with it in the future is vital for us to keep progressing as a society. Now we have better tools, better technology, and more knowledge. We can act faster and more efficiently to address pollution issues.
Chorus AQ is an international cooperative field campaign between NASA and the Korean National Institute for Environmental Research.
The Ministry of Environment of Korea has put in a great deal of effort into improving air quality.
By working with our Korean colleagues, we've been able to design a campaign that is very specific to their knowledge of the air quality problem from the past decades.
Joint venture with NASA has provided us with many research opportunities.
The air in our planet does not know of national borders or countries. A worldwide effort is needed so that what we do in the name of progress does not have a negative impact on our health and helps preserve the only home we know, Earth.
Chorus AQ combines satellite-type observations with ground observations and airborne observations to create the most complete picture of air quality we've ever created.
Explore with us. Take a deep breath and join us on an expedition that will investigate a major public health problem, air pollution.
One of the difficulties in understanding air quality is that the pollution that affects your health the most is not the initial component put into the atmosphere.
Under certain atmospheric conditions, some of these pollutants react with each other and produce new harmful agents like ozone.
There's three key ingredients to make ozone: NOx, hydrocarbons, and sunlight.
So think of ozone as an important cleansing agent from the atmosphere. When you have a big stain to clean, you use a lot of cleanser. And when you create a lot of pollution, a lot of ozone becomes evident in the atmosphere. That's helping to clean the atmosphere, but it's also impacting our health. We have primary pollutants. Nitrogen oxides and reactive hydrocarbons are most important in the formation of ozone.
Your car emits both NOx and hydrocarbons, sort of unburned fuel.
But the ozone itself comes from the chemistry, so we call it a secondary pollutant because it results from the chemistry that occurs after the emission of the nitrogen oxides and the reactive hydrocarbons.
When nitrogen oxides and hydrocarbons react with sunlight, they produce a harmful secondary pollutant, ozone. But wait, isn't ozone good for us? Well, it depends.
The role of ozone in the atmosphere is quite complex. In the stratosphere, ozone is a great benefit because it protects us from UV radiation. In the lower atmosphere, ozone is also a benefit because it's responsible for initiating the chemistry that cleanses the pollution out. But when pollution levels are very high, the chemistry runs amok and you create very high levels of ozone. And those ozone levels can become so high that they become reactive with our own body tissues and become a problem in terms of health.
Photochemical smog is considered to be a problem of modern industrialization. It is present in all modern cities, but it is more common in cities with sunny, warm, dry climates and a large number of motor vehicles. It can also affect rural areas, where agriculture, trees, and forest fires can release a considerable amount of volatile organic compounds, or VOCs.
What are the sources of VOCs? Well, we have just the evaporation of gasoline when you're filling your tank, petrochemical plants, the refineries that are making gasoline for us from oil, and also the plastic companies that are making plastics, polyethylene, polypropylene.
In terms of reactive nitrogen, man's activity far outpaces the natural sources, and so we can say that when nitrogen oxides are present, that's man. When you talk about reactive hydrocarbons, actually vegetation plays a major global role in creating them.
Trees can emit that pine tree smell you smell, but also a lot of the deciduous trees are emitting isoprene. Isoprene is very reactive and very good at making both particles and ozone.
But fortunately, they create very specific molecules, and when man creates pollution, it creates a different chemical mix. And so we can look at the constituents of the reactive hydrocarbons to determine whether it's nature or whether it's man.
But because these compounds travel with the wind, they can affect different parts of the world. Recently, scientists from other airborne campaigns were able to trace the origin of unusual high levels of ozone in the air above the western Pacific Ocean. They found that they were linked to the organic compounds released by forest fires in Southeast Asia and Africa, half a world away.
The atmosphere is a shared resource, and we're seeing more and more that the entire northern hemisphere is suffering from pollution background levels that are due to all of us, not just one.
Everyone living in a big city around the world is breathing polluted air, and it is having an impact.
It's part of the tug of war between progress and the price that we pay for that progress. And so that balance needs to be maintained into the future as we continue to develop economically, develop technologically. We have to pay attention to how that's impacting the air quality.
Our world is an interconnected system, and the impact of air pollution goes beyond the air we breathe.
All of the processes that are emitting and causing air pollution are also putting CO2 into the atmosphere, causing climate change, global warming.
It also affects our soils, our glaciers, our oceans, our climate.
And this is a problem that's going to affect our children and our grandchildren. So it's very selfish of us to ignore this long-term problem that is created by us.
In a laboratory setting, you can artificially control different parts of the problem, so each effect can be isolated. That's hard to find in nature.
Seoul, South Korea. A megacity with over 25 million people and a population density which is almost twice that of New York and 8 times greater than Rome. Despite being a modern and massive megacity, South Korea still counts with many forest and rural farming communities throughout the country. But why is South Korea an ideal natural laboratory to carry out air quality studies?
We have a bunch of factors. We have a very large city, a mega city, the 4th largest city on the planet, with lots of cars, lots of power plants. And then downwind from that, we have a forest. So we have the urban plume reacting with the natural emissions from the forest.
This is a perfect place on the globe to try to understand how the mixture between man's emissions and nature's emissions can create poor air quality.
Air pollution is an important environmental problem in modern societies. The rapid growth of new economies and industries in developing countries makes it very difficult to address environmental issues.
Korea has been developed very quickly after the Korean War. Actually, economic success gave us lots of benefits to the people. However, this also brought many environmental issues, including air quality.
So general public has been known about the yellow dust issue before, and in recent they start to learn about the fine particle issues and ozone issues. They're starting to pay their attention to those newer issues emerging to our society.
Korean government has been making persistent effort to improving air quality. We participate in this project as though understanding of current situation with aerial, ground, ship, on the top of current simple ground observation, crucial in future improving air quality.
We are definitely pay attention to solve this issue, and general public wants to know how we can actually achieve that goal.
Developing effective strategies to balance the economic growth and the good health of the population is key to continue growing and prospering as a society.
Unfortunately, policy always lags emissions, and so it usually takes time to understand what's causing the poor air quality, and then regulations can take effect.
It's a tough problem. We haven't solved it completely in the U.S., but here I think you're right. We're learning a lot more about the specific sources in this area so that here locally the government can decide what's the most effective strategies to use, because we don't want to hinder economic development. We just want to know what are the smartest choices you can make so you get the best bang for the buck.
In the United States and in Europe, this has taken place over a long period of time. Things in Asia are growing very rapidly, and so we're in the middle of that process.
But the difference is that now, with our knowledge and technology, we are better prepared to address these complex environmental issues.
In these days, many countries in East Asia have been developing very quickly as well. Course AQ mission makes people aware of the seriousness of current air pollution.
So we are thinking, based on this mission, more general understanding, getting better and better, and eventually we can find something to actually reflect to the strategy.
Chorus AQ mission results will help develop improved ways to assess this challenging task.
Current investigation will definitely help us gain deep understanding of air pollution phenomenon in global scale.
This is a lab. Measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA but from many universities and other government labs and organizations. And together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows, covered with the in situ probes that are there.
The Chorus AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the Chorus AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or LiDARs, as well as we can fly lower, we can do vertical profiles with our in situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure air quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to connect what the satellite sees with what's at ground level.
Chorus AQ has in its team 2 smaller aircraft equipped with atmospheric chemistry measuring instrumentation. A King Air from NASA Langley Research Center, and a King Air provided to the Korean National Institute for Environmental Research by Hanseo University.
The Hanseo King Air aircraft is relatively smaller than DC-8 in NASA. It can freely access source of pollution and measure air quality capital territory that cannot approach using DCA.
Working all together, scientists from the Chorus AQ campaign will provide valuable data and test the technologies needed to better understand air quality and the flow of pollutants within our atmosphere.
We can only fly the planes for a very short period, but the details that you get from the aircraft help inform the observations from space and from the ground, and how models can interpret those observations.
From this mission, we'll have better models and better mission data for Asia, and so we'll be able to extend the usefulness of this well beyond South Korea to other developing cities around the world.
We have the tools to study our atmosphere. Now, let's go exploring.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is, how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative, CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It'll take us 3 years to make the rocket, only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today, and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the North and South poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Kjellmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
Do you think we're gonna launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
The Rescue Coordination Center started receiving distress signals.
The bridge was starting to fill up with water. The ship was sinking and got them out on top of the rescue boat.
Winds up to 60, 70 knots.
We started to separate one by one.
Wave height 50 to 60 feet.
Finally I was alone and no rescue boat or nothing. The rescue boat drifted away.
It's freezing out there.
All I had to do was just wait and hope some kind of miracle would happen.
There is almost no chance to survive in conditions like that.
AIS, the automatic identification system. All ships out on the open oceans are obliged to transmit their position and their identity and their direction of speed, heading and speed, etc. It's kind of like air traffic control for the sea.
It's very useful to help provide assistance to ships in distress.
First of all, to see, do we have assets in the area that could help somebody in distress. In the days before AIS, we didn't even know if there were any vessels in a particular area where we have an incident.
They were more or less invisible to the coastal traffic administration.
But as of today, if we have an incident out in open water, we have the chance to see what vessels are in the area and could contact them directly to route them to the position or the distress, and in that way, in a more effective way, rescue more people within a shorter time frame than we ever have before.
AIS receiving stations along the coast, they can only look a certain distance out into the sea.
Ships that go out beyond 75 kilometers outside the coast were over the horizon and invisible to us. But if you think about these signals going straight, they go maybe several hundred kilometers out into space. And you know what circles around the Earth about 400 kilometers above us? The International Space Station.
The European Space Agency contacted the Norwegian Defence Research Establishment and gave them the opportunity to mount an AIS receiver on board the space station to test out this technology from space. All our calculations indicated that this should work, but we really did not know before we switched on the receiver on the space station. 1st of June 2010, the system was turned on.
The switch was flipped and the light came on and we were actually able to get the first data in. Yes, the instrument works.
We all got very excited.
And suddenly we could see a whole world full of ship data. It was I would say, a quantum leap really in our ability to look at global ship traffic.
It's like a blind man starting to see.
Yeah, it was a huge relief and great satisfaction to see.
So this brought a whole new dimension to the monitoring of ship traffic on the open oceans.
Nobody knew how many ships really are out there at any given time, and suddenly we had, if not the complete picture, then almost the complete picture.
On a typical day, the space station is observing about 30,000 ships out on the open ocean.
I was kind of overwhelmed, I guess, by the response that's got. The space station really is an excellent lab for testing this type of technology.
This project demonstrates that the International Space Station is not just for science and astronauts, but it really benefits the whole mankind with down-to-earth applications.
Based on the AIS, we had another vessels in the area that we contacted who continued to the area, and they searched together with the helicopters. Nobody expected to find anybody surviving in that conditions. They actually spotted one man in the sea.
After floating in the North Atlantic Ocean for 4 hours, I was finally rescued.
Thanks to AIS data and AIS data from the space station, this lone survivor was rescued. A absolutely happy ending for him.
And luckily for technology that made something that was basically impossible to survive possible.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That in many ways was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful. That we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than one or two satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GIM airlock, it's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
The first pictures now coming in from Puerto Rico after taking a direct hit. Hurricane Maria slamming into the island. One official saying the island is destroyed.
Hours with winds and rain, and didn't stop.
Power lines are down, streets are impassable, many roads are flooded.
High winds uprooting trees, overturning cars, and turning buildings into piles of twisted metal.
It is something that will change Puerto Rico forever.
We had no water, no food, no gasoline, no communication at all.
Not knowing where my next meal will come from, it hasn't been easy.
After Hurricane Maria, everything was gray, all the plants were dead. Hurricane Maria took the color away from us.
I am sure that these children will not be the same. They will not be the same. They are still struggling and trying to recover from this.
My name is Joe Acaba. I'm a NASA astronaut of Puerto Rican descent. I was about a week into my mission on the International Space Station. Hurricane Maria was forming up, and from there, if you looked out the window, Maria took up a big chunk of what we could see. It was going to cover the entire island. After the hurricane, their power grid was pretty much taken out. You just couldn't see the island anymore. The hurricane, I think, had a huge impact on, the island as a whole, but especially the kids.
Joe Acaba was our hero, and we need something positive. The students need something positive.
We wanted to pull through, forget all that happened, and lift up our spirits and lift off the island.
So I knew I couldn't do much from up on the International Space Station, but I did want to connect with the students to show them that there is hope and that there are people out there that care about them.
NASA has the STEM station, which allows the students and teachers to talk to the astronaut in the space station.
It's making that connection so that maybe, they become more interested and we can inspire them more to study the STEM fields.
So we were able to establish and coordinate with NASA one of these video conferences. Thousands of students from different parts of the island watching the video conference with the space station, talking to Joe.
This is Joe aboard the International Space Station. I have you loud and clear.
How do you compare?
What is the most impressive view?
How did Puerto Rico look after astronauts allowed to visit?
How often? What is the minimum number of?
It was awesome because, as soon as it came up, you could hear people clapping, people were excited. So even though I couldn't see them, I could feel them, and that was pretty neat.
It was amazing. He called from the International Space Station to see how Puerto Rico was doing, and that means a lot for us, a lot.
In May of 2018, I was able to go back to the island, my first time since the hurricane. It was a great opportunity to get out and kind of come full circle with those students, to go and see them in person and, kind of reiterate how important they are, and just to give them a little bit more hope because there's still a long way to go on the island.
He's a hero for us. Kids love him, and everybody loves him here. Joe Acaba is the role model that we need at this time.
I want to be like him. I want to go far, and I want to be an example for little kids when I'm older.
Not only is the International Space Station a great tool for scientific research and exploration, but for students from Puerto Rico in particular, I think that having that video conference with them, it did provide some hope. It did provide some inspiration. And so it's just one of the benefits that we get from the International Space Station.
In order to support International Space Station, we're constantly having to build new hardware to send to space, but as well, we need to make training hardware on the ground. So we ask ourselves, what if we got high school students to build us some training hardware and get them out of the textbook,
get them some hands-on lessons to work with. And by doing that, we'll be inspiring the next generation of students. So that's when we decided to create Hunch. Hunch goes to the local high schools, partners with the high schools, and gives these students opportunities to design, build hardware that'll fly in space or be used for training hardware on the ground. Students did the design and engineering, the CAD drafting, the 3D print prototyping, the machining, the procurement of the hardware. All this done by high school students to get this article to fly in space. From the quality perspective, the students have exceeded all of our expectations. The hardware we're getting in is top-notch.
This program actually helps them focus into the engineering and the STEM fields.
I've been teaching for 23 years. I've never seen anything that even remotely compares to having the type of impact on students that Hunch has had. Absolutely phenomenal.
Working with the Hunch program, we fabricated training hardware for the ISS.
I created and designed interactive simulations.
We're making a Mexican paella and hopefully gets chosen to go to the International Space Station.
From the Hunch program, I've learned how to use AutoCAD.
We're learning a lot of teamwork.
I've definitely gained some communication skills.
We're learning more about food science, technology, but everything basically doing this.
It gives them a confidence that I don't think they would have had to that level before this.
Maybe I would actually be able to be an engineer. So it was never something that I'd thought that much about. And then I was working on this stuff that went to space, and I couldn't think of anything more exciting. And I still can't.
It's a pretty cool thing to be able to tell other people or family when you go visit that I work with NASA programs.
I mean, I told everybody, like literally everybody.
We have an opportunity here for them that is unbelievable.
It's kind of like getting a master's at age 16.
They truly have moved on to a level they wouldn't have approached or wouldn't reach, I believe, without this program and without the International Space Station.
Before the Hunch program, I really was just a C student with no direction in my life. And since then, I've been on the Dean's List for the past 4 years and will be transferring to pursue mechanical engineering.
It really helped me find my passion for aerospace. The Hunch program gave me my career.
The impact on their lives has been amazing. They're more successful, they're more driven, they're more determined. They know they can achieve. And that's all, I think, through this program, through the Hunch program and interaction with the International Space Station.
Today's telescopes study the sky across the electromagnetic spectrum. Each part of the spectrum tells us different things about the universe, giving us more pieces of the cosmic jigsaw puzzle. The most powerful telescopes on the ground and in space have joined forces over the last decade in a unique observing campaign known as GOODS, which reaches across the spectrum and deep back into cosmic time.
Hello and welcome to this very special multicast. We'll be exploring a unique collaboration between some of the world's most powerful telescopes, both on the ground and in space. Now to do this, we've set up a similar collaboration between the ESOcast, the Hubblecast, the Spitzer Space Telescope's Hidden Universe, and the Chandra X-ray Observatory's Beautiful Universe.
I'm Megan Watsky for the Beautiful Universe from the Chandra X-ray Center.
And I'm Dr. Robert Hurt for the Hidden Universe from NASA's Spitzer Science Center.
It's the combination of deep observations from many different telescopes that makes this project so important.
The longer a telescope spends looking at a target, the more sensitive the observations become, and the deeper we can look into space. But to get the full picture of what's happening in the universe, astronomers also need observations at a range of different wavelengths, requiring different telescopes. These are the key ideas behind the Great Observatory's Origins Deep Survey, or GOODS for short.
The GOODS project unites the world's most advanced observatories. These include ESO's Very Large Telescope, the NASA ESA Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Observatory, and many more, each making extremely deep observations of the distant universe across the electromagnetic spectrum. By combining their powers and observing the same piece of sky, the GOODS observatories are giving us a unique view of the formation and evolution of galaxies across cosmic time, and mapping the history of the expansion of the universe.
Now, this is not the first time that telescopes have been used to give us extremely deep views of the cosmos. For example, the Hubble Deep Field is a very deep image of a small region of sky in the northern constellation of Ursa Major. This revealed thousands of distant galaxies, despite the fact that the whole field is actually only a tiny speck of sky, about the size of a grain of sand held at arm's length.
Now, with GOODS, many different observatories have brought their powers to bear on two larger targets, one centered on the original Hubble Deep Field in the northern sky, and one centered on a different deep target, the Chandra Deep Field South in the southern sky. The main GOODS fields are each 30 times larger than the Hubble Deep Field, and additional observations cover an area the size of the full moon.
These areas of the sky were already some of the most extensively explored, and so the combination of the existing archival data with the many new dedicated observations gives us an unprecedented view of the history of galaxies.
At ESO's Very Large Telescope on Serra Paranal, the 8.2-meter diameter giants were used for a total of almost 100 nights of dedicated observations. The telescopes made images of the region both in near-infrared light and on the boundary between visible light and ultraviolet light. At these short wavelengths, only telescopes on exceptional sites, such as the VLT's Serra Paranal, have a chance to observe through the Earth's atmosphere.
The NASA ESA Hubble Space Telescope observed the GOODS regions at optical and near-infrared wavelengths in order to detect distant star-forming galaxies, among other things. Now, Hubble spent a total of 5 days observing the fields, spread over 5 repeat visits. Each of these was separated from the previous one by about 45 days. Now, by spreading out the observations like this, Hubble was able to watch out for new supernovae appearing over the months, providing key information for studying the expansion and acceleration of the universe due to the mysterious dark energy.
But it wasn't just Hubble making space-based observations for GOODS. NASA's Spitzer Space Telescope imaged the GOODS regions in near and mid-infrared light for 5 days at wavelengths up to 30 times longer than the Hubble observations. These longer wavelengths are important for revealing distant galaxies whose light may be obscured by cosmic dust or stretched by the expansion of the universe, making them invisible to Hubble. For these distant galaxies, the Spitzer images also tell astronomers about their age and their total mass of stars, complementary information to the data from Hubble. Now, let's move from the infrared to much shorter wavelengths.
Also in orbit, the Chandra X-ray Observatory had already observed the GOODS field in many long observations taken over the course of a year. The Chandra images are the deepest X-ray images ever taken and detected more than 200 X-ray sources believed to be supermassive black holes in the centers of young galaxies. The X-rays are produced by extremely hot interstellar gases falling into the black holes.
These multi-wavelength observations identified tens of thousands of galaxies. To get a full understanding of the history and development of galaxies over the vast stretch of the universe's history, we need to be able to pin down their distances more precisely, to fix them in cosmic time. As these galaxies are so far away, the light waves we see from them today started their journey up to about 13 billion years ago. And because the universe has been expanding since the Big Bang, back then the universe was less than 1/7 of its current size.
During the billions of years of the light's journey, its wavelength has been stretched as the fabric of space has expanded. This effect is known as redshift because, for example, light that was originally blue or ultraviolet in color is shifted to longer and redder wavelengths.
Back on the ground, astronomers used spectrographs on ESO's Very Large Telescope to capture the spectra of galaxies, spreading out their light like the colors of a rainbow. Now the spectra allow astronomers to measure the redshifts of the galaxies and hence their distances. An extensive campaign produced redshifts for almost 3,000 galaxies in the Goods fields. Now with this knowledge, we can place the galaxies at their distances along a vast cone of space, stretching out from our own vantage point like a searchlight beam into the cosmos. We can take an amazing journey through kind of a tunnel towards the edge of the universe. In some places, the galaxies cluster together, forming structures which are up to tens of millions of light years in scale.
Thanks to Goods and other surveys of the same region, these areas of the sky are uniquely well studied, with high-resolution, deep observations across a wide wavelength range. Plus, there's more to come. For example, the Atacama Pathfinder Experiment Telescope, or APEX, has spent a total of 300 hours, nearly 2 full weeks, imaging the region at sub-millimeter wavelengths from its high site on the 5,000 meter altitude plateau of Chajnantur in the Chilean Andes.
Observations at these wavelengths are ideal for finding the redshifted light of distant, dusty galaxies in the very early universe. Because of the longer wavelength of its sub-millimeter light, the apex image is not as sharp as the visible light and infrared images. However, thanks to the deep Spitzer images, as well as images made at radio wavelengths, we can match up and identify the objects found by apex with galaxies seen at other wavelengths. The sub-millimeter light glow reveals that hundreds of stars are being formed per year in these galaxies. In the next couple of years, ALMA, the Atacama Large Millimeter Submillimeter Array, currently under construction on the same plateau as APEX, will begin its first science observations. Also observing at submillimeter wavelengths, it will have much greater sensitivity than APEX, and resolution even better than Hubble. ALMA will revolutionize our understanding of the early universe, by revealing many more distant, dust-obscured galaxies that cannot be seen at all by visible light and infrared telescopes.
These projects are an excellent example of how great observatories are joining together across the electromagnetic spectrum to give us a more complete view of galaxies over the history of the universe. Already, astronomers have written over 400 papers based on these data, with even more in the pipeline. And on top of that, the observations of the Goods fields will continue in the future. These patches of the sky will be prime targets for the next generation of telescopes, both on the ground and in space. And astronomers around the world will use these data to learn new things about the universe for many years to come. Saying goodbye to our friends at the other observatories, this is Dr. J, signing off for the ESOcast and the Hubblecast.
This is Dr. Robert Hurt signing off for the Hidden Universe and the Spitzer Science Center, reminding you there's a hidden universe just waiting to be discovered.
And this is Megan Waske signing off for the Chandra X-ray Observatory and the beautiful universe.
Join me again next time for another cosmic adventure, which I'm sure will surprise us beyond our wildest imagination.
Welcome to NASA Edge,
an inside and outside look at all things NASA.
We're here in sunny Florida at the NASA Kennedy Space Center.
And joining us now is Mike Cinelli, who is the program manager for the Apollo Challenger Columbia Lessons Learned program.
Thanks for being on the show, Mike.
Thank you for the invitation.
Now, this program is near and dear to your heart. Can you tell us a little bit about that Lessons Learned program?
Certainly. The Apollo Challenger Columbia Lessons Learned program is a brand new innovative effort, agency-wide, to take the lessons of the past and showcase them towards a future perspective. So we're looking at a very exciting future for NASA. We've got exciting programs such as SLS going back to the moon by 2024, and a host of other programs and missions that the agency is having. With those new programs and missions also come a brand new workforce, thousands of new people. And a lot of those folks haven't had the time yet to bridge the lessons of the past to the future. And that's our responsibility. So we're taking a look at the past, both the things we did right and the things we could have done better, putting them through that lens, focusing on the future, so therefore they can take the lessons of the past, look at the future, and apply those to increase their mission success going forward.
So with Apollo, Challenger, and Columbia, and we're looking at the tragedies that were involved with those three.
We primarily focus on Apollo 1, Apollo 13, Challenger, and Columbia. We teach the lessons of how things could have done better. However, we also do take time to look at the good things, because through 60 years plus of NASA history, there's a lot of great lessons of NASA's done things really, really well. For example, STS-1, the first launch of Space Shuttle Columbia in 1981, was a stunning success, the first reusable spacecraft in the world. So we want to take examples like that and showcase them, because all the new vehicles coming online, both commercial and NASA, will have their first processing flows and their first launches. So we can glean a lot of great expertise and knowledge from those times as well. So it's a mix both of things we could have done better, plus times we got it spot on right.
Now, a part of that program is the Columbia Room, where you have artifacts from the tragedy of Columbia Space Shuttle. Can you tell us a little bit about that?
Certainly. When we lost Columbia on February 1st, 2003, we had an effort, the largest ground search in American history, to bring Columbia home. Once that was completed, the decision by our leadership at the time was to make Columbia accessible to the workforce, and is accessible for the purpose of teaching. So Columbia now still has a mission to perform. The crew still has a job to do, and that job is to teach and inspire the next generation. So folks that come into the Columbia Preservation Room will see artifacts of Columbia. As they walk through those, it's a storytelling journey, explaining what happened, but also the lessons that came out of every single phase of the flight, of how decisions were made, and how perhaps in some ways we could have made better decisions. So they can then take those examples, take them back into the workplace, and as they're working on their programs and missions, they can reflect back and hopefully serve as an instrument of guide to them going forward. If they reach those decision points, they can use that as a tool making the right decisions forward.
And of course, there's some sensitivity to that. We want to be very respectful of the family, so you don't allow us going in there and doing the show in there or showing video from that, although people can visit it.
The families have been unbelievably gracious and allowing us to share Columbia with our workforce for teaching purposes. We thank them very much for that. We take really good care of Columbia and protect her very well, as if she was still solid flight hardware flying. So we want to protect the dignity and the respect and reverence of the room. And within those constraints, we take folks in the proper way and make it a teaching, a learning environment, if you will.
Now, as you started this program, how important was it to you to get senior leadership behind this?
That's one thing. When you start a brand new program up, buy-in and collaboration is key. So my first step was to approach our senior leadership. I am so humbled and thankful that our senior leadership stepped right up and gave full support and backing to the creation of this program. And that support has not only continued, but it's strengthened over the last couple of years. So, in great appreciation to our leadership for helping us.
Speaking of leadership, we had a chance to sit down with Bob Cabana to get his perspective on the Apollo Challenger Columbia Lessons Learned program. Let's check it out. Bob, I know you're very familiar with the Lessons Learned program, but tell me a little bit about your history with the program.
So it's one of the things I'm very proud of here at the Kennedy Space Center. Mike Cinelli has just done an outstanding job. And what we don't want to do is forget the lessons learned from the past. You know, after the Challenger accident, they just kind of took what remained a Challenger and buried it in a silo. And it was like, we want to forget about this and move on. Columbia was different. We have Columbia in a room preserved over in the Vehicle Assembly Building. And it's actually used by universities. Folks can get parts loaned out to them for research to help make spacecraft better, to learn about the impacts of, returning in that kind of environment, what we can do to make it better. But the more important part is not just the way we have treated the hardware, but it's also how we treat our people and the lessons that we want to remember from this. You know, if you look at Apollo, Challenger, Columbia, all the time when you go back, the hardware was talking to us, and Challenger was the normalization of deviancy, that we had O-rings that were bad, we saw soot, but we came to accept it because nothing bad happened. And then you look at Columbia, the foam's coming off, but nothing bad has happened, and we accepted it. We don't want to forget that. And part of Apollo, Challenger, Columbia lessons learned is helping to keep it in the forefront, to help folks see what we learned so that we don't repeat those mistakes again, and help to create an environment where people are listened to.
Yeah, I imagine that's very important, that idea of, not letting things become rote and letting them just continue as they were, but constantly being vigilant about looking at all our processes and things like that moving forward.
No, I mean, nothing that we do is without risk if it's worthwhile. And flying in space is an extremely risky business. But, we've been given this goal now. Boots on the moon by 2024, right? And I'm all in. I want to see that happen. But we have to do it in an environment that allows people to speak up. Now, that doesn't mean we do what you want to do, but we have to address people's concerns. I greet all our new employees every 2 weeks when they come on board, and I talk about our core values, and I talk about lessons learned from Challenger and Columbia, and the need to create an environment in your meetings where you feel free to speak up. And we hire a lot of really smart people, okay? But when you're new and you're going to a meeting, sometimes you may know something, but you think, oh, all these other people, they're a lot smarter than me. They've been here a lot longer. They know more than I know. I'm just going to be quiet and listen. And what we have to do is ensure that we get everybody's input so that the decision makers are making informed decisions. And so it's incumbent upon us who are leaders, you have to stimulate discussion. If nobody's speaking up, then you have to ask questions to stimulate that discussion and get people talking so that all the concerns are addressed so that we make our decisions in an informed manner. I had an all hands the other day, and I said, let me see a show of hands out in the audience. How many of you were not here when we lost Columbia? And it was close to half the audience raised their hand, all right? So that's a lot of folks that weren't part of that loss, that grieving, that learning experience that we had. So we have to find a way to make those lessons known to them. If I had my way, every new senior executive at NASA would have to walk through the Columbia room and see the results of the decisions we make. And none of the people that made any of those decisions on Apollo, Challenger, or Columbia thought they were putting the crew in harm's way. They thought they were making good decisions.
Mike, Bob talked about when Challenger happened, NASA decided sort of to close the door and put everything away and not even address it. But with Columbia, you came out and said, look, we got to change our ways.
I get that question a lot. Folks ask of, why was Challenger handled this way? Perhaps in Columbia was different. And I think the only way to really answer that question effectively is say it's a different time. The folks that handled the Challenger aftermath were doing the very best they could and doing what they thought was best to continue the program and to do what was right. And the folks in Columbia did the same. So I never look back and say which one is better, which one's worse. I say that they're different in many ways. And from having the honor for so many years of helping share Columbia with thousands of folks around the country, I can tell you that the power of Columbia to effectively change the hearts and minds of people, and the power that the crew has through their stories, through their sacrifice, has been overwhelming. So I can tell you the impact she's had and will continue to have even larger going forward. What's fascinating, one of my tour guests brought this up at one time. He said, do you realize this is the only place in the world that this exists? The only place in the world that you have a spacecraft on limited display that you can teach the lessons learned. That was a very powerful observation and insight. Even in aviation, there's not many examples where you can go and actually tour a fallen aircraft to explore. So Columbia is something extremely unique for the agency, for our country, and even for the world, because we share Columbia with our partners, international partners. So we realize how special Columbia really is and how much potential that uniqueness can serve us in the future in a very good way.
And one last point that Bob brought up was talking about Artemis, the mission getting back to the moon by 2024, and taking all these lessons learned and applying it, like as you said before, to the next generation of engineers and scientists, and how they're going to learn about those lessons learned and apply it to SLS and to Orion and to the Artemis program.
You know, what's amazing is when you look at history and you look at the present, there's so many similarities. History repeats itself. So we can look back and see how Apollo progressed, especially looking at the Apollo 1 accident and then Apollo 13 during the flight history of the Saturn program. And we can learn those lessons because we're flying a capsule again. Orion, in many ways, is similar to Apollo 1. Some technology, of course, will change, it'll advance. Some of our thinking, we grow and learn and do things better, hopefully. But human nature and human instincts, that's pretty consistent when you look over time. So when you look back to Titanic, when you look back way before that, accidents and the cause of accidents and human behavior, human instincts. As a matter of fact, I call it the DNA thing. If we could just fix the DNA thing, we'd be in good shape. But that's what makes us individuals and unique. So we have the understanding that we have those challenges. We're always going to have those challenges, and we can have those potential shortcomings. We have to be proactive and be ready for that and do better.
Well, you know, Mike, another one of your great supporters is Chief Engineer Ralph Rowe from NASA headquarters. And I had a chance to sit down with Ralph and learn from his perspective, not only from the Columbia accident investigation, but also from the Lessons Learned program. Let's check it out. So Ralph, this may be a hard question to answer, but are there one or two key lessons learned from Columbia that you can share from your point of view?
Yeah, I think there are some key safety tenets that we inherited from Apollo that we have to always remember. The way Apollo was successful is they followed these safety tenets, and we've seen when we don't follow those tenets, we have issues. Strong inline checks and balances is engineers checking engineers. Nobody checks their own homework, right? Healthy tension between the responsible organizations in the program so that there are separate but equal chains of command, any one of which that can raise an issue and create that healthy tension that we need between the organizations to make the right decisions. And the third tenet is value-added independent assessment, where any program is willing to bring in folks with a fresh set of eyes to look at their critical problems so that they don't make mistakes. And on top of those three safety tenets, leadership has to really create the right environment for those safety tenets to work. So to me, those are the key aspects that I talk about when I talk with our folks and anyone working in our industry, really.
And it seems like this is even more important than ever, because now with the Artemis program going back to the moon, with the commercialization of space, working with a lot of partners, a lot of outside companies, it's really not just NASA within, but it's going to be NASA and its partners working this together. So how important is it going to be down the road?
Absolutely. It seems like we're almost in a boom era for space, with new companies participating with us more than ever before. And so sharing our lessons, not only with our employees, but our partners, is critical, right? They need to know what we've learned from Challenger and Columbia and Apollo 1, as well as our own folks. So I spent a lot of time going around to those companies and talking about the lessons from Columbia. I know Mike in the Columbia room is going to do a road show, and there'll be an opportunity for those folks to see the impact of the hardware from Columbia.
And speaking about the roadshow, I'm glad you brought that up, because it's not just a roadshow internal to NASA itself, but it's also to other outside organizations outside the aerospace industry that are interested in our lessons learned.
That's right. The lessons just don't apply to aerospace. It's any industry, really. The fundamental things that we made mistakes with apply in any industry, really. So those root causes, those organizational issues that we had, those are things any company could learn from.
Mike, thinking the tremendous benefit of this program, can you give us an example of the lessons that you've learned that you've been able to share with NASA and maybe some of its partners?
Certainly. That's one thing with the lessons we've come through with. They've been very applicable across industries and programs, which is very interesting. For example, communication. It's one of the things we do every single day. We communicate. It seems like all we do today, we're texting, we're typing, we're talking, communicating in a whole different array of ways. But are we communicating effectively? When we look back at Challenger, for example, we can see so many examples throughout pre-launch of where people did not communicate effectively or communicated in ways that perhaps weren't very effective to getting the right results. We look at Columbia and how we handled that situation. There's also many examples of where we could have done much better. So communication is something that even though we do it a lot, doesn't mean we do it great all the time. So we look at that, we can take those lessons and apply those into other industries. It could be any industry, it could be our home lives. Those lessons are so applicable across all kinds of genres. Another one, for example, is normalization of deviance. And that's a fancy NASA way of saying something that creeps into our system that slowly changes over time that shouldn't, but it's kind of a hitchhiker onto change. For example, during Challenger's time, before Challenger, we start seeing small degradation of the O-rings. We start getting used to seeing that damage. We didn't forget about it, we didn't ignore it, we were working the problem, but it became normalized, almost expected in some ways. Fast forward to Columbia, we start seeing foam coming off the external tank since the first flight. We dealt with that issue for decades, trying to find a solution to it. We got very used to the foam coming off. And as a matter of fact, I'll speak for myself, when the vehicles would come back home after landing, you'd see some damage on the belly. And if the vehicles had less damage, that seemed a little abnormal. You were expecting to see more damage. So that became normalized over time. Those are that human DNA I mentioned earlier. It's so easy to sneak into our system. How often have any of us driven with our car and you had that little light on the dashboard on? And then that one day,
You're shaming us.
I heard stories about you. And then one day the light goes out, right? And it's like, wow, why'd that light go out? That's really weird. Well, I could probably guess when you bought the car, it didn't come off the lot with that light on, right? But we got so normalized to that, or the knock in the engine, or that thump in the tire. We just, as people, get normalized and used to things that are different. So although stuff does change, we got to be extra vigilant to watch out for the things that shouldn't change and then respond quickly to those, communicate effectively to those, and solve it before it becomes a larger issue.
Well, is it fair to say, in that regard, let's take the car for as an example, where, when we drive our car, we hear the knock, we always say, well, we'll deal with it next week, we'll deal with it the week after, until something happens where we can't drive the car. Well, in the space industry, you can't do that, right?
You can't do that. I mean, you're flying 17,500 miles an hour, you just can't pull over and take a look under the hood. We're dealing with microsecond decisions, we're making split-second decisions, systems that aren't very hospitable to things that shouldn't happen. So we have to be vigilant, we have to be watching for those. And it goes beyond rockets and spaceflight. These critically important lessons can help us do better in other fields, like public and private aviation, in the automotive industry with safer cars for our friends and our families. Other modes of transportation like trains, helicopters, and ships can benefit. They can even help us in construction, leading to safer equipment, which help us lead to safer roads and buildings and bridges. We're also very honored to be sharing our lessons with the Department of Defense and all branches of our military as they try to ensure the safety of our heroes, whether they be on land, in the skies above us, or even under and on the sea. Excitingly, we're now even building strategic partnerships with folks we never before envisioned, like the Centers for Disease Control and even the nuclear power industry. Simply put, there are so many different and diverse areas where we believe we can make a really great contribution to our future.
Wow, Mike, you're working with a lot of institutions and companies. But with lessons learned, it's not just about number of partners, it's also about diversity of voice. We went to NASA headquarters to find out how NASA is making sure we listen and learn from every voice within the agency.
I'm here at NASA headquarters today talking with Steve Shee. Steve, tell us a little bit about what you do here at NASA.
Sure, I'm the Associate Administrator for Diversity and Equal Opportunity here at NASA. And what that means is it's my job to help the different organizations and people at NASA work together effectively.
You do a lot of work in your office, but tell us how you're working with the Lessons Learned program.
When we look at the Lessons Learned program, we see a number of accidents, and it's easy to remember the technical issues, the engineering problems, the technical defects that occurred that contributed to those accidents. But if you examine those accidents, you also see that there were people and culture inclusion issues as well. Specifically, certain individuals with maybe unconventional thinking, unpopular opinions weren't fully included we didn't have the benefit of including all of the information, the data, the perspectives, the concerns that they shared. And if we had fully included all of that thinking, that cognitive diversity, then maybe we would have had a different outcome, or at least been able to assure the mission and safety in a better way.
How does that stretch out into NASA's partners in how they conduct business as it pertains to risk management and a diversity of opinions and information?
We provide leadership, we provide technical assistance, and we actually do audits of recipients of NASA grants. These are scientific and research organizations, including universities and colleges, that do research for us. And as a condition of receiving those grants, they have to comply with anti-discrimination statutes. So that helps ensure that there's discrimination-free workplaces in those organizations. They're accessing and including the best minds, the best thinking, the best talent to be able to arrive to the best product to help NASA. The other thing here is that NASA is uniquely positioned to actually lead the world because of our mission. We have a peaceful mission to explore, to discover, and to expand knowledge for all humankind. And so because of that role, not only is the work we do inspirational, but if you look at the technological advances that we bring to the world, the way individuals and organizations will follow our leadership because of the inspiration and because of what we're doing. And by how we conduct ourselves and provide that as a model, we have the ability to be able to really have far-reaching impacts.
NASA has many big missions in its future. What does success look like through lessons learned for the agency?
I think with any type of program, the success ultimately is dependent on how it contributes to safety and mission assurance. And so if we're able to launch these missions safely and successfully and on time, and it's because of lessons learned to a certain extent, then I think that's an indication of success. But ultimately, we have this incredible platform to make an even bigger difference beyond NASA. So what I like to talk about is that it's the job of my office to help NASA provide air. That's psychological safety, feeling that people won't be retaliated against, so that they have oxygen to breathe. They don't have to hold their breath. They can really be at their best. And it's also our job to help NASA provide space. And that means room for people to be included and to feel like they belong. Because if they feel that way, they're going to be at their best and they're going to fully contribute. And the great thing is that our mission is, as an agency, is about exploration, discovery, and expansion of knowledge for the benefit of all humankind. And so I like to say at NASA, we make air and space available for everyone.
So Mike, another part about the Lessons Learned program that I love is the tour stops. It's kind of like the rock concert tour. I need the t-shirt with the dates on it. Tell us about the tour stops.
And that's something really, really exciting coming along. As we talked earlier, the power of the Columbia Room, the power of sharing the artifacts and the stories of the crew and how we can change the future. Over time, I kept thinking, this is great, we're getting thousands of people to the room, but you know what, that's not enough. There's so many more people we can help impact in a positive way. So how do we do that? We can't take them all here to the Kennedy Space Center. We can't bring them all into the VAB or in the Columbia Room. But what if Columbia came to them? So the concept of the Space Shuttle Columbia National Tour became to take Columbia on the road, to bring it to those literally millions of people that can't come here, and to share those stories, to share those lessons forward. So we started off in April. We did April 12th in retrospect of the 30th anniversary of STS-1, the first launch of Columbia. So now we relaunched Columbia on her first anniversary to bring Columbia on our next mission. So the mission continues, mission to inspire, to educate, and change hearts and minds. So we're here at the Kennedy Space Center, and we shared the artifacts in a new display for the workforce. We also had a center-wide event that we had senior leadership there, and the workforce was able to come. As we travel from center to center around the country, Columbia comes, we come with a message, a center-wide event, reinforced training, and then we're also going to take breakout meetings and go into branch level and division level meetings and take this story to smaller groups of folks and have those more intimate conversations on how these lessons can be applicable and helpful to their organizations.
And that also isn't limited to NASA centers. There's a possibility that you can go beyond that.
That's the exciting part. As this continues, one thing that's just amazed me is the potential. It's unbelievable and it's exciting. because NASA, our charter is to help everyone, right? We want to make the world a better place and more safe and successful for everyone. So within that charter to go do that, we see the potential. For example, when you look at a firing room and what happens in a firing room to launch a rocket, I would offer to say an operating room and a firing room are very, very similar, and you can't make mistakes. Time is of the essence. Communication is critical. You can't have deviance in the system. You got to be very effective what you do. So there's the medical industry, and I can give you dozens of other examples of how. So I'm more amazed every time you think about it or talk to other folks. You get more inspired of how many ways NASA, through this program, can actually impact in a positive way and partner and collaborate with organizations within the federal government and with outside the federal government, private organizations, international organizations, academia.
Incredible.
Well, Mike, I just want to congratulate you on a job well done. You still have a lot of work to do because it's just in its infancy, but you're going in the right direction.
Thank you. And I'm working with a lot of great people, and the great exciting part of this, it's not just me. I may be leading this effort, but there are thousands of people inside and outside the agency that are going to help make this successful, in addition to the crew that's watching over us as well. So all together, we're going to make this an amazing program and help a lot of people.
Awesome. Well, thanks so much, Mike, for being on the show. I feel like I have a lot of lessons I still need to learn, but tell you what, it has been fabulous.
Thank you so much for the opportunity.
No, thank you.
You're watching NASA Edge.
An inside and outside look at all things NASA.
Antarctica. It is the world's coldest continent. Scattered among the ice in this harsh and unforgiving environment are numerous research stations. One of these is the Neumayer 3 station. Situated on the Ekstrom ice shelf and operated by the Alfred Wegener Institute, which coordinates German polar research efforts. Nearby Neumayer 3 is a small greenhouse, the German Aerospace Center's Eden ISS, which is working on developing innovations for cultivating food using closed-loop systems. In a space about the size of an apartment bedroom, this greenhouse recently grew more than 600 pounds of fresh food, including cucumbers, lettuce, and tomatoes, in a 9.5-month period, even with outside temperatures well below freezing. The researchers took scientific samples from their crops, but they ate the vast majority of what they grew in a powerful demonstration of the benefits of closed-loop agriculture. This research not only benefits indoor agriculture here on Earth, it also has applications for space exploration. For more than 20 years, people have continuously occupied the International Space Station, a laboratory about the size of a 6-bedroom house that orbits the Earth every 90 minutes at an average altitude of approximately 250 miles. Astronauts working with researchers on the ground have used the space station as a proving ground for the technologies and know-how that will allow people to explore more of the moon than ever before and take the next step in space exploration, a crewed mission to Mars. Jess Bunchek is a plant scientist from Kennedy Space Center, NASA's leading center for growing plants in space. The agency is sending her to work with the German Aerospace Center on research that could one day help feed crews on long-duration missions to the Moon and Mars. Bunchek brings important experience to Eden ISS. Knowledge gained from working with astronauts growing salad crops in space. After a month-long voyage from Germany, Bunchek will spend about a year in Antarctica. There, she will work with a team of researchers connected to the Mission Control Center in Bremen, Germany, to solve challenges with closed-loop agriculture so that it can be robust and productive enough to help sustain astronauts on a 2 to 3 year long mission to Mars.
Feeling weighed down? Feeling the constant pull to the Earth? We all are. It's gravity, and it's a part of every single thing we do, including our science. But what if we're 250 miles above Earth, aboard the International Space Station, a laboratory like no other that offers something we can't get on our home planet?
My name is Dr. Serena Anand-Chancellor, NASA astronaut. I recently flew to the International Space Station aboard Expedition 56 and 57. My relationship with microgravity is that I got to live in microgravity for 197 days when I was on orbit. So many people ask, what is microgravity? Why do you float on board the International Space Station? Gravity acts upon all objects. We're never truly in zero gravity on board the space station. But because the space station is traveling so fast around the surface of the Earth, we're actually in a constant free fall. And that's why everything and everybody appears to float on board the space station.
We are experiencing the Earth's gravity. In fact, we're actually experiencing about 90% of what you all experience on the surface of the Earth. The difference is we're just moving so fast that as we fall, we actually fall around the Earth, and that defines orbit. So microgravity means we're not, it's not the absence of mass, which of course creates gravity, but all the objects together are in the same gravitational field and all falling together. So yes, it is a lot of fun. Floating around, of course, is one of the exciting parts of being up here on board and being an astronaut, but even more importantly, it lends itself to all the amazing experiments that we can do on board that take advantage of that microgravity environment to do things that we can't do on Earth, but that can benefit life back on Earth.
The important thing is it's so different than what we have here on the ground, where everything is pulled by the Earth at what we call one force of gravity. And what that does is it allows you to see the small forces, the small processes, the small effects of what goes on in life cell development or technical processes like combustion or fluid flow. And it helps you understand things that you may not have fully understood on Earth, where you see something happening, something assembling or disassembling, or the shape of something now going into 3 dimensions. And you learn, that's really what was driving this thing on Earth that we didn't really understand.
On Earth, gravity is affecting all research we do, and sometimes that can get in the way. Studying things in different environments can give a better picture of how they work, from diseases to fires and even things that make up products like milk or shampoo.
One of the main things we perform on the ISS is science. In fact, probably 70 to 80% of our day is performing scientific experiments.
The International Space Station is a great place to do research for several perspectives. One of those is it's a big, huge satellite orbiting the Earth. So if you have an instrument that wants to look at the Earth or look out at space, we provide the power, we provide the data, the platform for it. You don't have to go do your own new satellite. The outside of the ISS is also a very extreme environment, and sometimes you learn things by exposing your hardware, your polymers or whatever, to a different environment. You'll see something happen different than what is on the Earth. But probably one of the most pervasive uses of the ISS is just the microgravity environment, the things that we do inside the ISS. To be able to do your experiment in space without gravity, which we've all lived with forever here on the ground, which we live with every day, and we don't even realize how it governs so many things that happen around us. If you take gravity away, now some of the small phenomena, some of the small processes and forces start to come out, and you can see them, and you can see the behaviors of your experiment happening differently in space and in microgravity than you would on the ground.
It takes a lot of people to make all of that microgravity science happen. 4,000 scientists, companies, and students from over 100 countries have sent more than 2,700 experiments to the orbiting laboratory. Over the past 20 years, these studies have unlocked new discoveries and even kicked off hundreds of new microgravity experiments.
We're studying the physiology of how blood flow and the fluids in our body shift as a result of microgravity.
Yesterday I spent some time setting up a veggie experiment. We'll actually be growing Mizuna lettuce up here.
Drew and I actually have been helping start a new experiment called the Cold Atom Lab, which will create one of the coldest places in the universe right here on the space station, almost at absolute zero.
But who are these scientists? And how do they get their research to the space station? This season, we'll take you behind the scenes of the years of preparing an experiment for space. You'll see it launch off the planet and splash back down in the ocean, and hear what it's like to hand off your research to the astronauts who serve as the eyes and hands of the scientists aboard the International Space Station.
This is our first
project that is going up to the station, and our first project working with anyone involved in the space program. So it's a very exciting time for us. It'll be interesting to see how all of our planning is played out when someone else has the experiment in their hands.
These two tanks are from the Sphere's slosh experiment, which we've been working on up here.
Microgravity has a lot to teach us. Take these containers. The green liquid inside is showing us how fuel swirls around in a tank while it moves through space. What we learn could help us design safer, more efficient spacecraft. At any given time, we are conducting close to 300 different experiments aboard the International Space Station. Research like this is preparing us for the future of space exploration.
That's cool.
We really can't mimic the environment on the space station anywhere on this planet. And it's what makes it such a special place and why scientists from many universities, several companies, like to send their science up, because once you remove gravity, many things act differently.
This season, we're exploring why we send science to space and what it takes to get it there. Spoiler alert, you don't have to be a rocket scientist to conduct research in microgravity.
So this is our first project that is going up to the station, and our first project working with anyone involved in the space program. So it's a very exciting time for us. The transition from what am I going to do with my life in the middle of graduate school to here I am sitting in Houston getting ready for our launch. I can't hardly believe that it's actually happening.
Meet Elaine, one of the co-founders of Tympanogen, a medical device startup based in Virginia. Her company is developing a gel patch that can serve as a replacement for eardrum repair surgery. That could have huge benefits here on Earth, but launch that gel to space, and the opportunities for use grow even more. First, we have to back up a few steps. Putting your life's work on top of a rocket may seem like a daunting task, but there's a system in place to help scientists who know nothing about spaceflight get their research into orbit. You see, NASA and its international partners aren't the only source of science aboard the space station. The ISS U.S. National Laboratory creates pathways to space for companies, universities, and even young students. If you're starting a journey into the unknown, it helps to have an expert at your side to navigate the way. The National Lab connects researchers with implementation partners who provide resources and guidance for taking an experiment from Earth to microgravity. Elaine and her team are working with nanoracks.
They have the plate reader on the space station that's going to be used for our project, and they're coordinating the launch and getting all the materials together for us. We're glad that we're working with them because we're glad that somebody has done this before and can help us along with the process.
7,643.
The project that we're sending to the space station is looking at how hydrogels behave in microgravity conditions. And we're specifically looking at how the structure changes and how drug release profiles change in the absence of gravity.
My name is Paris Du. I'm a co-founder and co-inventor of this technology, and I've been with Tympanogen since day zero. Hydrogels are a very important materials. They are high volume water that can very well mimic the extracellular matrix of our body. So we really thought that answering this question can really help the scientific community.
Confused? Don't worry, we've got you covered. Think of hydrogels like a scoop of gelatin. Not quite a liquid, not quite a solid, definitely made up of mostly water. We can use hydrogels to cover wounds and even deliver antibiotics to promote healing. For that reason, hydrogels are being studied for use for things like wound care for soldiers on battlefields.
If you are far away from a hospital or a clinic and you can't get good medical care right away, and that soldier has a wound, could you apply that hydrogel directly to the wound site and begin to treat any infection that might be coming on. What about in space, though? What if we are far away from Earth's surface on our way towards Mars, and we also have another wound on an arm or a leg, and we need a better way to treat that wound and make sure it doesn't become infected? So Tympanogen, the hydrogel itself, is a great example of a dual-purpose technology. It's something we can use not only on the Earth, but up in space.
This research could provide previously unknown foundations for future hydrogel studies. It's a great example of how microgravity can offer new insights into systems we've already explored on Earth.
The data that we're collecting is so basic science that it's hard to find those sorts of projects at this stage. As a researcher, that's really exciting for us as well. And it's in space.
And when it gets to space, it goes into the hands of astronauts who will run the experiment in orbit. Just like training for launch, landing, and spacewalks, crew members participate in hours of scientific training to prepare them for running many of the hundreds of experiments that are ongoing aboard the space station. Ready to go to class with an astronaut? We'll take you along.
Well, a lot had changed in 11 years since he was up there. It was a new experiment, so he hadn't seen that either. They tell us, you know, hey, this is a lot easier if you just go upside down. You know, you're going to be in microgravity and this will work differently.
Hi, I'm Terry Virts, and I want to talk about floating in space. One of the first things that you need to realize when you get into space is that even though you feel like you're falling, you're not. You can let go and you float. It's not a problem. It's something you really have to train your brain to think about. Another thing that you need to learn when you first get into space is how little force is required to move you. And another cool thing is you could be on the ceiling. It makes it very easy when you're working. You have to get some work done up here. You just go up on the ceiling and get your work done.
Our team of scientists is busy getting their experiment ready for launch. At the same time, NASA is preparing the space scientists who will operate the experiment aboard the International Space Station.
So as astronauts on board the space station, we are the hands and eyes of the researcher. They are telling us how best to do the science, but it's up to us to make sure that science runs correctly.
Astronauts train all over to Glenn Research Center in Cleveland, Ohio.
Christina, this is Sharon with an answer to your question. So they do want you to go ahead and install the cable tie. Copy all. Thanks for having that done for me. Anytime.
Being able to operate and maintain the space station while conducting crucial research could get overwhelming. Luckily, astronauts have strong support teams on the ground and often develop personal connections to the research.
I was so impressed at the different things we'd be working on, cancer or Parkinson's or even Alzheimer's disease. So as a physician, these meant a lot to me. These personally were very important experiments that we needed to do. But in all honesty, the entire crew, not just myself as the physician, were excited about working on these experiments. You get a little nervous at first as you begin to pipette or even utilize a microscope, which I hadn't used in years. But you quickly learn because you realize how important it is to the science, and the investigators and scientists running you through all these experiments were fantastic and just walked us through every step of the way.
Yeah, just keep us posted, but Drew and I are ready to continue up. Good working with you guys today, and I'll see you soon.
We got here on a Thursday, and it's currently Sunday. We've been in a big day yesterday filling up these wells with gel solution and getting ready for handover at 7:30 a.m. on Monday, ahead of launch on Tuesday afternoon.
Failure is an option. It's where you learn from your mistakes, get back up again, and try again. My name is Anwin, and I'm bringing new capabilities to small spacecraft. CubeSats are a class of small satellites. This is a spacecraft. People have been adopting them all the way from elementary schools to NASA and commercial ventures. If we want to go beyond Earth, we need these capabilities. We are the first to fly these technologies. They are risky. You can get creative to do the test that you want to do. If one of these spacecraft goes out of commission, then we send up a few more. This is what we've done. We've qualified all these components in space, and we've qualified this technology that it can be done on a CubeSat. As humans, we're so interested to see what's out there, what can we do. Me and my NASA friends here, we go exploring a lot. Multi-day rafting trips, backpacking trips, we go scuba diving together. It's kind of that same exploration. What could we do to push the boundaries?
From space, we see deep into the heart and veins of our ever-changing planet. Pictures of Earth are worth more than 1,000 words. They are the blueprint for our future. To unlock the full potential of space's unique vantage point, we've created powerful tools. Tools that gather valuable data. Data that enables farmers to efficiently manage water and fertilizer for stronger food yields. Data that scientists use to monitor ticks and mosquitoes that carry harmful diseases. Data that first responders use to find the fastest routes to save lives. That's only a glimpse of what we can do today. In the future, when combined with AI and powerful computing, a broader range of space data would generate infinite solutions for Canadians. Imagine a future where we can use space data to better understand and predict the impacts of climate change, like rising sea levels, extreme weather, wildfire risk, and flooding. Measure the health of our forests and create predictive maps of pest damage and burn extent. Produce real-time dynamic navigation routes to protect whales and other endangered species. Ensure security and sovereignty in Canada's vast Arctic. Tomorrow's challenges require investing in innovative solutions today. Earth observation is key to securing economic opportunities and improving the lives of Canadians. Together, we can define Canada's future.
The reason that you would do any kind of experiment in space is if there's something particular about the space environment, and most often that is microgravity. So mostly the ISS gives us the ability to either do something that we can't do in a facility on Earth or investigate some phenomenon, some property in a way that we can't on Earth. So for example, some of the tissue architecture, these really delicate tissues, as you start to build them up, they would collapse because you have gravity, or the cells would naturally settle to the bottom of the plate. And so you just can't study the answer to the question that you're looking for. So the space station lets us have that ability to either test what the effect of gravity is or remove that problem entirely from our experimental setup. Yeah, the space station's an incredible place to conduct research. It was sort of like being in the world's most amazing lab when I was up there in 2016. So when you're a scientist, you're used to working on one thing over and over and maybe really refining the details on that over the course of a PhD thesis or a lab project. On space station, you get somebody's incredibly refined project times 200 different fields. So for me, it was a chance to learn about all of these different areas of science, and they each have a team behind them. So I was usually pretty excited to open the container and do whatever experiment that day brought. I also really got a chance to talk to those PIs, the principal investigators, and those scientific teams, and understand everything that was going on behind their experiments and read their papers. So by the time I got to doing the experiment, I was pretty excited to take it out and to see what was going to change in microgravity. Yeah, science in space, it's an amazing lab and it's incredibly fun. So we are smiling all the time. I'm Kate Rubens. I'm a scientist and an astronaut.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, And I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's got better legs today than it did then.
group of people what organization is most responsible for revolutionary advances in space technology, and there is little doubt their answer would be NASA. Clearly, over its long history, NASA has been one of the most innovative and exciting change agents the world has ever seen, proving that we can accomplish great things if only given a goal and the opportunity. That feeling has been firmly imprinted on the NASA DNA and continues to motivate all those who push the envelope of technology. But rather than just rest on its laurels, NASA is moving to expand its role as a change agent in new and exciting ways. In order to do this, the NASA culture will need some minor tweaking first. Today's generation of NASA researchers are working to alter some outmoded practices of how technologies are developed and implemented at NASA. If these ideas take root, they have the potential to revolutionize NASA from the inside out. Coming up on this episode of NASA X, we will follow members of Space Technology's Game-Changing Development Program Office as they work to revolutionize and mature new technologies within NASA. We will feature a few of the many technologies managed by the GCDP to see how these innovative ideas are advancing the missions of today and missions of the future as well. NASA has a long and storied past. In its short history, the agency has accomplished truly breathtaking achievements, forever changing how humans view themselves in the universe. The NASA of today is no different than the one of the past, of course. It is still the world leader in space technology and is still accomplishing truly unbelievable feats. But many in the NASA community have seen the pace of technological breakthroughs slow in recent years. That was not always the case. In NASA's early years, it seemed like many of its projects were stuck in fast forward, none more so than the Apollo program. President Kennedy made his famous Man on the Moon speech at Rice University in 1962, and by July of 1969, Neil Armstrong was stepping out of the lander onto the surface of the moon. One reason we got there so quickly was because NASA made the decision early on to let the engineers lead the charge toward the moon, rather than the norm, which was to have a more bureaucratic structure. That is not to say there was not structure. There was just an understanding that more risk must be taken in order to complete the mission in the given timeline. But as the Apollo program retired and the shuttle came online, a shift began. The culture within NASA became much more risk-averse and, rightly, more focused on safety and successful missions. But with this new posture, less focus went into the development of transformative technologies. This mindset permeated throughout NASA, and eventually, in the words of one NASA official, NASA became more evolutionary and less revolutionary. NASA never stopped innovating, but researchers developing new technologies often found substantial hurdles in their way. To better understand this, let's look at what NASA calls TRLs, or Technology Readiness Levels. The 9 TRLs measure the maturity of evolving technologies and order them from 1, which is the lowest, to 9, which is a technology that is fully developed. An example from history of how the TRL system works can be seen in the late 1950s, when the famed NASA engineer Max Faget came up with an idea for the Mercury spacecraft. Dr. Faget was sitting in the cafeteria at NASA Langley drawing on a napkin when he came up with the idea for the basic shape of the Mercury capsule. He fleshed out the details with his team, and soon they had the beginnings of the craft, which put them at Technology Readiness Level 1 for the Mercury project. He and his team then began moving through the other levels, testing and building models, and after a few years, arrived at TRL 9, which culminated with the first manned flight of the vehicle on May 5, 1961. The same basic concept is still used today. Researchers come up with concepts and ideas and hope to move them through the early TRL stages all the way to full maturity. This system is the framework from which NASA engineers develop technologies, so it goes without saying that the TRLs are very important within NASA. But in the last few decades, many researchers have come up with great ideas only to find themselves stuck in the lower TRL stages. But in the early 2000s, pushback began happening within the NASA research community. It was widely agreed that there needed to be a way to push important concepts to the front of the line and move them more quickly through the technology readiness level stages. To do this, a sea change needed to happen within NASA, which would completely alter the current culture and get us back to our leaner, engineer leads the way mentality. That sea change happened when NASA's Space Technology Mission Directorate created the GCDP, or the Game Changing Development Program Office. Space Technology developed the GCDP with the idea that new, exciting, disruptive technologies would be rapidly infused and given the chance to prove themselves more quickly.
If you look at the Space Technology Program, especially if you look at the Game Changing Program within, our projects are about 2 years long with an option to extend them for a third year. So basically we are carrying on executing our existing portfolio, and by the end of the year we will develop dozens of new technologies that we can make available to other programs within space technology, other stakeholders such as human explorations under the AES project, or maybe we can pass on technologies to Science Mission Directorate as well.
The idea here is to take some more risks and to do some things instead of incrementally, but in a transformative or disruptive way. Let's look outside of the box. Let's look for completely different ways of doing technology. And so the idea is that we can afford to take risks and target technologies that will hopefully have orders of magnitude improvement that can do things that we've never been able to do before.
With this idea firmly established, the team needed to begin looking throughout NASA to determine which projects would be first on the list.
Somebody might have a great idea, a new way of doing navigation or communication, and they'll come and they'll pitch that idea to a PI. If the PI believes it's a good fit within our portfolio, that it meets game-changing metrics, that it's aligned well with agency priorities, then they'll develop what we call a New Start proposal, and they'll bring that to our program board. So they have to be a TRL3, and that's, they've gone through the proof of concept. It's not basic research, it's not a scientist in the lab, but it's someone who's taken it and said, look, I've checked it out in a small way, a small scale, and it's proven itself. I need to get it from TRL3 to TRL5, through the Valley of Death, we call it.
This term, Valley of Death, is apropos because this is where so many promising technology ideas falter. Generally, an idea in the TRL range of 1 to 3 are proof of concept ideas. But once they get into the TRL3 range, more often than not, excess funding and time needs to be spent on them to move them forward. This level is where so many technologies of the past fizzled out. But one of Game Changing's central goals is to grab the hand of some of these ideas and lead them through this valley of death and on to actual missions.
What we are doing here in Game Changing is we're taking a bunch of technologies in this 3 to 6 range, and we're rapidly advancing them. We can take selective ones, the best ones that we can find, we can advance them for a 2 to 3 year period, we can mature them from this lower TRL to where they can be used by projects and missions, and then we can go on to the next one and do it again and again and again.
With the goal set, the team began the process of looking at some of the best ideas within NASA, choosing a wide-ranging set of technologies to help rapidly mature and begin this new approach for the agency. The GCDP manages over 30 projects that focus on everything from nanotechnology and lightweight materials to nuclear systems and solar electric propulsion. The hope is that with enough support, the GCDP-managed technologies will eventually be used to help create innovative new space technologies for our nation's exploration, science, and economic future. One of the first technologies they chose is from NASA's Robotics and Autonomous Systems and is located in this lab at the NASA Johnson Space Center. Here, a small team of highly motivated young robotics engineers are working on an idea that has the potential to help astronauts on long-duration missions, and may end up changing the lives of millions as well. One of the first Space Technologies GCDP projects we will explore is located in this lab at the NASA Johnson Space Center. Here, a group of NASA researchers have come up with an exoskeleton that they call the X1. It has the potential to solve some major problems for astronauts on long-duration missions. This 60-pound assisted mobility device is worn on the legs of the wearer and is used to assist them in various ways. To understand why NASA is interested in a device like this, you have to understand a little about physics in space. A major problem faced by astronauts in space is bone loss and muscle atrophy due to a lack of use. Generally, on shorter trips, the bone and muscle density problem can be easily managed, but longer duration missions pose a much greater threat to crew health and performance. Here on Earth, we use our legs every day to walk around. But on orbit, the astronauts are in microgravity, so muscles and bones, especially those in the legs, aren't being used as they would be normally. Because of this, muscles weaken and bones begin to lose their density. As a result, some astronauts come back to Earth with up to 30% less bone structure in their legs and with significantly weakened muscles. To combat this, NASA doctors prescribe a strict regimen of exercise on orbit, but there is only so much that can be done. Generally, there is a treadmill and other bulky devices used to keep in shape, but these only provide limited success. The X1 may be able to change that.
I guess one of the biggest things for NASA and their astronauts is keeping their astronauts safe and keeping them fit and keeping them in good shape. We're looking at in the next few years, we're going to start sending astronauts to the space station for year-long missions instead of just 6 months, right? And so how do we keep them fit? How do we look at muscle density loss and bone density loss and muscle atrophy and things like that? If we look at a device like this, look how much, you can see how much smaller and compact it is. And this is really going to hopefully pave the way towards smaller technologies for countermeasures that we can use when we're in a smaller capsule and we want to go back to the moon and L2 and Mars. So the goal on Space Station, we're looking at two different things right now. We're looking at it for dynamometry applications, which is basically measuring muscle strength. And so we've been working with the Human Health and Performance Group and saying, wouldn't it be great if we had a device on Space Station that we could use to measure muscle strength while they're up there? Because they don't do that right now. So now what we're looking at this to do is say, you go use ARED, you go use the treadmill or the stationary bike, and then maybe once a month or once every 2 weeks, you use the X1 as a dynamometry application so we can measure your muscle strength. And we can really start to close the loop with the physicians on the ground and the prescriptions of exercise that they're giving the astronauts to see how effective they are. At its core, it's a mobility assistance device. So you can imagine that when we go to Mars, no matter how much you exercise along the way, you're going to be very tired when you get there. And so now maybe we can use this not only for exercise, but you can use it for mobility assistance when you get there, because you're going to be weak. All of your joints that are actuated, you can use them to resist you, or you can use them to assist you.
NASA is very interested in the X1 for use in space, and this same device could also be a game changer for anyone who needs rehabilitation, like stroke victims. X1 could be even more life-changing for paraplegics. Early on in its development, the team partnered with the Florida Institute for Human and Machine Cognition. This group has been working on a mobility device that could serve as the legs for wheelchair-bound patients.
At that time, they had their own exoskeleton that they had developed called Mina V0, and they were really focused on mobility assistance, helping persons with paraplegia get up out of the wheelchair, walking again. And at that same time, we had, Robonaut, which we had just flown to space station. We worked on all this hardware. We developed all the actuators and all the mechanical and electrical assemblies for that. We developed all the safety systems in order to be able to send it to space station. And so we said, well, why don't we come together? We take that knowledge that we have about building these structures, and we'll take the knowledge that you guys have with assisted mobility and your high-level software, and we'll come together and build X1. And so X1 is really about improving life for people here on Earth and in space.
The X1 has the potential to change the lives of anyone suffering from limited mobility. When asked, many paraplegics say just being able to stand, reach the top of a shelf, or have a conversation with another person at eye level can improve their quality of life significantly. Much work is going into the X1 to make it accessible to as many people as possible. It is relatively lightweight and has been designed in a way where it can be adjusted to fit many different body types. And for persons who have lost their ability to walk, there's also a pre-recorded walking gait that can be adjusted to help them learn to walk again. In this iteration of the X1, paraplegics must still use crutches to help them balance and walk. But the hope is that the technology will develop to where the device can be utilized without crutches.
You know, my mom has multiple sclerosis, and she is 80% kind of confined. And for a device like this to help her, that's something that she looks at saying, I wish I could have that. But in 10 years from now, people won't be saying that. I think people will be saying, oh, let me go get that out of my closet because I'm ready to go out and walk around.
Sometimes technologies develop slowly and incrementally, and sometimes things happen all at once. It's a term, the tipping point. I think with this type of technology, we've actually found a tipping point where the actuation technology is there, the computation technology, the applications for spaceflight, and the willingness and people's interest in this type of technology. And all these things converging at once, I think that's what makes something, that's how the game has changed. All these technologies happen at the same time, and people are grasping that opportunity to really to make a difference. So it's not only changing the lives of astronauts, improving their health, but it's also improving lives here on Earth. We feel that it's not just game-changing, it's actually life-changing.
Spaceflight has many obstacles, one of which is weight. Any mission off this planet has a weight restriction. NASA has estimated roughly $10,000 per pound to get something into orbit, so weight reduction is a huge factor. If manufacturing costs could be brought down as well, millions of dollars could be saved on each launch. The challenge of creating low weight and less costly launch components is very attractive. The Game-Changing Office is taking this challenge very seriously and has created a composite cryotank to offset additional weight and possibly save money. Current propellant tanks are made from metals like aluminum. As the name suggests, the composite cryotank is being made from a strong, lightweight composite material that have a huge upside when talking about saving weight and money.
We start out the project looking at 30% weight savings over traditional state-of-the-art aluminum or aluminum lithium tanks. And we did a phase 1 activity with 4 contractors before we down selected to Boeing for phase 2. And out of that studies that we had, we were getting anywhere from like 35 to 40% weight savings. Every pound that you save in mass on a launch vehicle, you get that savings in payload. And it's depending on whether you're, at the core stage or an upper stage, that ratios vary. But you do get significant savings. So you get more performance, you get more capability, or you get increased payload.
The process of building the cryotank is not only cost-effective, the weight reductions could ultimately save millions during a mission. Current composite materials are cured in large ovens called autoclaves. This process can be very expensive, but NASA's composite cryotank is being developed out of autoclave, making it much less expensive.
Saving the out of autoclave or the autoclave expense, meaning that normally you have this huge tank and it's a composite and it's got all these materials that are in it, and you have to cure it in a huge oven. you got to maintain the oven, you got to buy the oven, you got to procure the oven. So if you can find a way to manufacture with the same technical integrity as a tank that's gone through the autoclave, outside the autoclave, you can cut development costs significantly. 30%, I think, is the number that they're saying. And not only development costs, but recurring costs. You make these tanks, it doesn't have to go into an oven.
The way it works is a fiber placement head on a robot is programmed to lay down the material exactly where it is needed. This new process reduces costs, time, and most importantly, produces a better product. Because all of this technology is relatively new, the NASA team is using a process called the building block approach. First, they test small coupons or pieces of the material to make sure that it can measure up to expectations. It is then made into larger pieces and tested again. The project is currently at the point where a scale model 2.4 meter tank is being tested, with the eventual goal to build a full-scale tank to fit on a launch vehicle. The current 2.4 meter section is located here in this silo in the west test area at the Marshall Space Flight Center, under the shadow of test stands for the Apollo engines. Engineers have placed a foam coating over the tank and will then test it in a way that would be expected on a launch vehicle.
We put the tank through the exact conditions that it would see in the launch vehicle. So we fill it with the cryogenic material, in this case it's liquid hydrogen, and then in the case of a launch vehicle, we may have to empty that. So we would fill and drain, pressurize, unpressurize, all to determine how the tank reacts to those conditions and loads.
With this test completed, engineers can look for problem areas, fix them, and then move on to building the larger tanks. And if successful, this game-changing process can be adapted to other parts of a launch vehicle, making it more lightweight and less expensive. These are just a few of the ideas that are being worked on by the Game-Changing Development Program Office. But many more innovative ideas and technologies are being moved through the game-changing lane each day. And with each new development, change is coming to NASA that is allowing the agency to rapidly infuse technology and make smarter decisions about how to move forward and create different approaches while changing the culture. Much of the credit for this positive change can be placed directly at the feet of Space Technology's Game-Changing Development Program Office.
Personally, I would love if 5 years from now somebody said they really changed the game. They made a difference for NASA. That's all I'd need to hear.
Okay, 3, 2, 1. Well, I've been lucky enough to spend exactly one leap year on the space station, 366 days. So you can imagine that in 366 days, you get to see the Earth quite a bit. Even though we are so busy on the space station, we do try to look outside and glimpse what's flying below us any chance we get. part of me, the dreamer, the little kid that started dreaming about this whole experience now basically 40 years ago, that part of me was still there, unchanged for 30 or 40 years, and just marveling incredulously at the beauty of it all. And I would see clouds and green and rivers, and it would just completely fill my eyes. The difference in observing the world or the universe from inside the space station, looking through the windows, or being outside, is what I describe as the same level of interaction that you can have looking at a beautiful aquarium from the safety of a room. When you're outside and all you have is a helmet and maybe 1.5 inch of plexiglass in front of your eyes, you can see details and colors and shades, the level of detail that you can capture, and the way you experience that universe is going to be very, very different. You want and you feel that you have become part of it, and you can develop that sense of belonging. I think that the first impact of the first flight was that I did see and I did sense how fragile, how small the Earth is. We are used to think of the Earth as something so vast and big, and we don't think that what we do, our daily life, can affect such a vast system. But from space, you get a sense that every individual, every living organism is somehow connected. Seeing the city lights at night, where a place like Europe or the United States or Asia, densely populated, everything is so interconnected, and all those lights and all those lives are apparent. They are right in front of you all together, and you think that all we are doing somehow as an effect on everybody else. You come back from an experience like that thinking that that's what's happening, and then you can see the effects, both the positive ones but mostly the negative ones, in a second flight. And I think you have to acknowledge and grow an awareness, and with that awareness comes the desire to share the experience and share that awareness. It's understanding that the science that's telling us how we are changing and influencing the world has solid mathematical and solid mathematical base. And then you see the effects of it and you just interiorize it. You make it your own experience. And I think that that's what happened. That's why astronauts develop that awareness of and the desire to help the environment somehow in any way they can.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Alright, good morning everybody. Roll call, got the pilot, got the co-pilot, GEOC operator, mission director. Alright, flight mission crew, FCIFs are complete and flight currencies are all checked. Crew schedule has been published. We're NASA 872. Engine start expecting 0600. Estimated landing of 07 tomorrow morning. Subdivision durations approximately 24.
All right, thanks everybody.
I didn't ignore your email.
Hawks are strong, powerful birds capable of flying thousands of miles each year. Some species undertake long migrational journeys, a testimony to their strength and stamina. Our bird will fly over 10,000 nautical miles and will reach an altitude of 65,000 feet.
Preparation for an HRX flight starts a couple of days before the flight, where we get together and look at the meteorological forecasts and decide where to send the aircraft.
Those targets are determined by the circulation of the atmosphere, which varies from day to day.
And so we design a flight based on meteorological data to go down and sample in near the tropical tropopause, so what altitude to sample, also what latitude and longitude to sample.
We're looking at all the areas where the scientists want to fly, and we coordinate those areas with the Federal Aviation Administration.
We work with the scientists beginning at that time to come up with options and a plan to get them what they need. We try and maximize the time that we spend in the air.
For this experiment, we're focused on regions where temperatures are cold because we're interested in high altitude clouds. These clouds are about 10 miles or 16 kilometers above the surface.
When all the instruments are ready for flight and everything's been checked out and the aircraft's been checked out, and we button up all the hatches and we're ready for flight.
24 wind calms, altimeter 2984.
Once everything is ready in the control room, we give the OK for engine start.
Got control panel, secure the aircraft to shores.
So we're ready for aircraft taxi prep.
Copy it, word.
Center line, 22 left.
Roger.
NASA 872, thanks. And Trapper, can I get a takeoff report?
Yes, sir. Runway's clear. You're going for takeoff.
Roger that.
40 knots. 80 knots.
Takeoff. Ready now.
And payload admission, this is data, KUS.
We fly it with a mouse and keyboard, and it's more like flying an airline that's always on autopilot.
Well, with the Global Hawk, we have these same controls, only we're just on the ground, and the aircraft could be, several thousand miles away.
Rather than pointing the nose in any given direction or setting a throttle for a particular power setting, we just tell the aircraft, go to this heading, go to this altitude, go to this airspeed. The system itself decides on the best way to get there.
And one of our challenges is to kind of understand the contingency state that the aircraft is in and make sure we understand what the aircraft is doing, and that's what we truly want the aircraft to do.
Most of the time the aircraft is flying in what we call a cruise climb mode. It's actually full throttle in a climb. It gets up to a maximum altitude and then it has to wait to burn fuel off, and as the aircraft gets lighter, it goes a little bit higher and a little bit higher, up to a maximum ceiling of about 65,000 feet.
Come easy left. Roger, release and then turn.
One of the things we do during these flights is we have a meteorological team, a team of forecasters down the hall who are watching the satellite products and telling us where thunderstorms are, for example.
There might be colder temperatures south of Hawaii versus just off the coast of South America or Central America. So we have to know where to direct the plane. So we look very carefully at the meteorological situation first. Then when they're in the air and you're flying along, oftentimes these forecasts are wrong.
So when the atmospheric conditions change during the flight, when we're out over the ocean, a lot of times there's a request for us to change our flight track. Maybe the area that they're interested in is in a different area. So one of the things that we will do is coordinate that flight change.
We will use the information we're collecting as we fly along to redirect the plane.
If you'll notice up on that forward deck of the airplane, there's a big white 48-inch dish. That's a KU, a commercial KU SATCOM dish, and that is constantly pointing at the satellite that we have subscribed to for the missions.
We actually get extensive data transmission from what the instruments are measuring in flight.
We decide based on what we see to send the aircraft somewhere else or to have it go down to different altitudes.
The classic case, as I said, is you look down, you see a cloud on the LiDAR and you say, we're going to turn around, descend into that cloud and sample it.
So we'll profile down through these thin clouds, making measurements of not only water vapor, but the temperature and the pressure and a range of other gases, including ozone, chlorofluorocarbons, and so forth, so that we can understand the movement of air and the behavior of the air in that layer as we dive down.
One of the great things about this is being that our ground station is building based and we have all of the scientists in the back room. We always fly with two pilots. This gives us the opportunity for one pilot, the mission commander, to get up, go to the back room, leave the other guy to monitor the airplane, and we can talk with any one of the particular scientists, whoever has the most important data that they want to get at that particular time, and we can work directly with that scientist, sit right down at the table with him or her, and decide what's the best way to get them what they want and still meet everybody else's needs.
Obviously, the pilots fly the plane. They're the ones who are talking to ground control, but the pilot has to know where to go, and that's where the scientist's role comes in. The scientist will pick the targets and direct the plane towards the appropriate targets, both before we fly and while we're flying.
It's quite a process because sometimes it can mean a major shift in the flight track. So we will look at what they have proposed and provide some feedback, and then we have to talk to air traffic control to make sure that what we're proposing is okay with them. So we'll change the flight track sometimes many times during a flight.
And so that's how we coordinate between the flight operations team and the payload operations team. So it's a very close collaboration during a flight between both groups.
Very interesting for me too, because coming from a platform where we would just have instruments loaded on the plane and we just go fly a mission, we get real-time interaction with the scientists, and I've learned a whole lot just in the few years I've been doing this on what's going on in the back end of the airplane. Very exciting and very interesting.
872 is coming right, hot fast. 30 seconds.
Well, what next and what's important to do?
We hope that ATREX will improve our understanding of this part of the atmosphere, but ultimately ATREX will raise some additional questions as well.
We have a lot of work to go, and we hope that doing ATREX with multiple missions, different times of year, in different parts of, mostly over the Pacific, but into the Indian Ocean, to fully understand the range of conditions that we'll see, that models have to consider all of those ranges of conditions in order to understand the climate system properly.
We need to develop some more instruments and fly them on Global Hawk and other high altitude aircraft to make measurements there as well.
Emily Dickinson once wrote, "The brain is wider than the sky." Many questions have been addressed along the way, and new ones have surfaced. We'll keep searching, for the answer is in the air. Carl Sagan once defined the Earth as the pale blue dot. "70% of its surface is covered by water. Life on our planet began in the oceans some 3.5 billion years ago. Since then, water has been an essential component for us. In fact, 2/3 of our bodies are made out of water. We can't imagine life without it. As far as we know, without the presence of liquid water, life is not possible at all. Water is all around us. It's not only in our oceans, but we also find it in rivers, lakes, ice, rain, clouds, even in the air we breathe in, as it's continuously evaporating into the atmosphere.
Water is important for all life. We wouldn't have life on this planet if there wasn't water. When astronomers try to think about other planets and whether they have life on it, the first question they ask is there liquid water?
We have liquid water covering nearly the entire planet, 70% of the planet covered by water. There's water in our atmosphere, in the air, all around us. You don't find any place, any chunk of air in the atmosphere that doesn't have some water molecules or some ice particles or some water droplets in it.
Without water as part of the climate system, we would have wild temperature swings in our atmosphere that would probably make any planet uninhabitable. So water is a key driver.
So water is everywhere. Now, the way water begins, of course, it's a liquid out here, and the sun beats down on the surface and it warms the water. It evaporates it. Just like on your stove, you put your pot of water and your heating element below it heats it up and it boils off, you get steam or you get water vapor. Same way that the sun's energy will warm and evaporate water. That water rises in our atmosphere, and as it rises, temperatures are cooler aloft, and so you form clouds. Clouds are water particles. They're little liquid water particles. Some are very tiny, and they float around as clouds. They can also freeze and form ice particles, and those ice particles float around. Those are also clouds. As the atmosphere moves that water vapor around and those cloud droplets, they fall out of the sky and they come down on the surface and they feed our lakes and our streams. They make the soil wet so that crops can grow. Water is really a fundamental part of our planet. It goes back to the oceans and then it goes through this cycle again. So you get this constant heating up of liquid water, becomes a gas. It precipitates out onto the land and it drives this, what we call the hydrological cycle.
So as water comes into the atmosphere, it has a number of effects. So it helps to make clouds, it helps to make rain, but water is actually a very important greenhouse gas.
Also, water carries energy with it. It takes a lot of energy to evaporate water. And then when water forms cloud droplets, it releases energy. So water is a big component of not only the hydrological cycle, the movement of water, but the energy cycle of the planet also, because it's a greenhouse gas and because when you evaporate water, it carries a lot of energy.
So the way it works is when we change the atmosphere, put more carbon dioxide in it, it gets warmer, and that allows the atmosphere to hold more water. The water is also a greenhouse gas, so that increases the temperature further, so it's a feedback effect.
Water, being a strong greenhouse gas, will actually amplify the greenhouse gas effect from these other longer-lived species like carbon dioxide and methane. So that's a very strong positive feedback loop which would keep driving the temperature up.
Or you could create more clouds and reflect more energy back to space, which is what we call a negative feedback.
So we have this complicated interaction between the positive feedbacks from the water vapor itself versus the clouds that it forms, giving you a negative feedback. And finding that right balance, that's part of what we're trying to understand with the entire hydrological cycle in the tropical part of the atmosphere.
And it turns out about half of the change in temperature of the atmosphere right now and the change predicted in the future associated with the increasing carbon dioxide is caused by this water vapor feedback.
Water comes and goes, and that's driven purely by the physics of how water works. It's a reactionary greenhouse gas as opposed to a longer-lived stable greenhouse gas. But water's the big player in the entire feedback loops of how the atmosphere works.
So it's very warm here in the tropics, and it's very moist, and so the air down near the surface has a lot of energy in it.
So deep convection in the form of thunderstorms and typhoons actually are more energetic. They go to higher altitudes.
And so it can go quite high. We see these big thunderstorms that develop, and that's this air being funneled up just like a boiling pot of water. The air gets funneled up into the upper troposphere here and actually go very high.
And so that extends the troposphere upward to higher altitudes, and the temperature keeps decreasing as you go up, and so it's colder.
And so eventually, most of the water gets frozen out as you get up to these altitudes of 50, 60,000 feet. So it's incredibly dry, even though down at the surface in the tropics, it's very wet and moist. It's very high humidity, it's damp. When you get to 55,000 feet, about 16 kilometers up, it's incredibly dry.
You still get some water making it up to the tropical tropopause, and there the atmospheric motions transport air into the stratosphere. So air is transported into the stratosphere with a small amount of water that's left behind, and that's controlled by the temperatures at the tropical tropopause. So if the tropopause is colder, less water will make it into the stratosphere. If it's somewhat warmer, more water will make it into the stratosphere.
Above us, up at 40, 50,000 feet in the tropics, the atmosphere is going to warm up through this century. And because of that, there will be less freeze drying of this air going up. And so the thinking is that water might go up. Now, water is a powerful greenhouse gas, so if water increases at those higher altitudes, it will act to trap more energy at the surface. So it could cause the temperature to actually go up higher.
Climate change will have huge impacts on food supply, on ocean levels and flooding of coastal regions.
So it's important to understand, put all of this together to understand how water will change through the next century.
The more we understand the processes, the better off society will be because of it.
ATREX, when studying the tropical tropopause, is addressing a key uncertainty in our ability to predict future changes in climate in response to human influences.
It is believed that Guam was first discovered by seafaring people who migrated from Southeast Asia around 2000 BC. When Portuguese explorer Ferdinand Magellan arrived at the island in the 16th century, he found a highly stratified society, experts in the art of sailing and skilled craftspeople, the Chamorro. Since then, numerous expeditions have investigated this region of the Pacific, yet there are still many discoveries to be made and places to be explored. Although this time we'll be looking up, way up into the sky.
Attention on deck, engine start on my mark.
Box number 7324. NASA 872. 872.
My land cover career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything, because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Dr. Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I use satellite imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are made up of a series of pixels to show what covers the Earth. A pixel, or picture elements, is the smallest unit of a digital image. When combined with thousands of other pixels, a picture is formed. Each pixel color shown represents a land cover type. It's from these pixels where ground verification or ground truthing come into play. You see, depending on what satellite is taking images, a pixel can cover roughly an area of 30 to 500 meters squared. For imagery captured by Landsat, a pixel is 30 meters squared, or about the size of a baseball diamond. However, part of that pixel showing forest might actually be water or shrubs. By taking land cover observations, citizen scientists can help answer these questions when it comes to land cover maps. So, why are these land cover observations so important? Why are they taken in the first place?
We also are looking at how these components are changing over time. So deforestation in the Amazon or across the world, how are cities expanding? A lot of different things to study, and really the view from space is the way that we do it here at NASA. We have big supercomputers that simulate the physics of the atmosphere and the land, the interaction between the Earth systems. It's important to have that, that land cover map. It sets certain parameters. Those models can actually be used to look at current day conditions and weather. So based on these current conditions, what might the Earth look like 50 or 100 years from now? There's an element of understanding, but then also being able to predict into the future, what that might be like, what these changes may mean for us.
Each point shown here represents a real-world measurement of environmental conditions. Scientists use computer models to fill in information where measurements may not exist. By verifying the satellite imagery and using the data for these models, scientists can predict changes in our environment more accurately. One of these scientists using land cover maps to track urbanization as part of her work is Dr. Amita Mehta of NASA's Goddard Space Flight Center.
So urbanization changes terrain as well as characteristics of the surface itself. And so impervious surface is what we look at when we are monitoring flooding. When there are, say, parking lots or cement and concrete surfaces, they increase. So previously, if it was a farmland or something which was not built, and if that is built now, that water previously that could go or percolate in the soil and in the ground now cannot go in, and it stays there. Monitoring helps you to plan for it. If you see land cover changing, even then you know that how water is going to flow in that region might change. If you have to send rescue out or you have to plan for relief activities, then if you know land cover, then you know where there might be help needed.
By using land cover maps and models that reflect changes over time, scientists can predict where flooding and other events may occur. With a changing climate, these predictions from models and land cover maps can help scientists better understand these changes and help communities prepare for them. But perhaps a more important reason as to why I take land cover observations is you get to participate in a community of scientists, citizen scientists, and students.
So it's a very important component that the citizen science and students of the GLOBE program and GLOBE Observer can contribute to is by really giving us the information on the ground of what they're seeing around them and in front of them. And we hope over time as well how maybe some of these things are changing, because those would be very valuable for science.
I saw the value of having information before a hazard happens, because once that fire went through an area, we can never recreate that data. This is all important for us to share and put together because that's how we understand Earth as a system. All of these things end up affecting where we live, why we live where we do, and why we make some of the choices that we do.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.
Rock, report range status. Range green.
T-minus 5, 4, 3, 2, 1. Go for main engine start. 0 and liftoff.
These are not the best of conditions, but for these knights of the highway, hauling a multi-million-dollar spacecraft more than 800 miles is all in a day's work. They're carrying NASA's next planet hunter, TESS. TESS stands for Transiting Exoplanet Survey Satellite. Its job is to search for habitable planets outside our solar system, but close enough to study. That's because we're not just looking for planets, we're looking for life. And the first leg of this spacecraft's journey to orbit is the ride to NASA's Kennedy Space Center.
So we left yesterday at Dulles. We left at 10:15 in the morning. We ran into an accident on 95, horrible weather, rain, down through Richmond.
The 16-hour road trip from Virginia to Florida wasn't easy, and protecting this one-of-a-kind spacecraft during its move was vital. Its shipping container is designed to keep TESS safe on the road.
The case gets used for a number of missions. It's mounted on some shock-absorbing bumpers so that we don't see a lot of the road noise getting into the spacecraft while we transit. We don't want any humidity inside. We don't want the temperature to change. So we have an air conditioning system as well. So we're just trying to keep it environmentally stable on the trip. And then we have very sensitive science instruments. So we actually provide a nitrogen purge. We spray nitrogen gas in to make sure that no air gets in contact with some of the sensitive components.
TESS has safely made it to Kennedy, where it is immediately taken to the Payload Hazardous Servicing Facility. But the job of keeping it clean is far from over.
TESS has really strict contamination control requirements. So what we've done is created a clean enclosure inside the high bay that acts like a clean room within a clean room, basically.
This is a unique mission full of first-time events that are sure to be a challenge.
TESS isn't like another mission. We haven't done another TESS. This is the first of its kind.
The time has come for this diverse team to put years of planning into practice as they begin the countdown to T0.
We've had a period of hard work that lasted for years, and when we finally get to the point of launch, it's very exciting. This is where the fun begins after we've gotten through all the early legwork and the planning, that we are actually going to now prepare a spacecraft for launch.
Building on the groundbreaking discoveries of the Kepler mission, TESS has scientists across the world excited about its possibilities.
TESS is probably one of the most interesting spacecrafts that I've ever worked on in my career, because of the science it's bringing back down to Earth. It's taking science fiction to science fact.
TESS will use the transit method to hunt for the telltale signs of planets orbiting other stars. In the transit method, the spacecraft watches the sky, and when a planet passes in front of a star, the star's light briefly dims. But Kepler only looked at one portion of the sky. TESS is taking this search to a whole new level.
What TESS is going to do is look around the entire sky around us to find stars nearby, much closer, 10 times closer than Kepler.
The really exciting part about this is it's the first all-sky survey of this type, using the transiting method to look for Earth-sized and super-Earth planets.
I think the real interest by the public in exoplanets is that everyone has a dream that there's an Earth analog out there, another planet that has the ability to have an atmosphere and water and sustain life on it. That, of course, is the ultimate sort of goal of exoplanet science.
When all the pre-launch tests, inspections, cleaning, and checkouts are done, it's time for TESS to join up with its launch vehicle, the SpaceX Falcon 9 rocket. This is a critical process, and it begins with encapsulation. This is the Falcon 9 payload fairing. Its smooth aerodynamic profile will give TESS a safe ride through the extreme heat and pressure of the climb to space. The vehicle systems engineer in NASA's Launch Services Program plays a critical role in bringing the spacecraft and rocket together.
We have our hands in just about everything. We have to know enough about each system to know how they all interact together, and we have to know how the vehicle operates as a whole. So that's how critical the vehicle system engineer is in this whole process. We've been working very closely with SpaceX from the start. Even when during their design phase and going through the whole certification process, the vehicle system engineer was integral in that role to understand what's going on with the SpaceX launch vehicle and how the NASA team can supplement a lot of what's going on.
The fairing is in one piece as it arrives at the door to the high bay. Inside, the test spacecraft is ready and waiting for encapsulation.
What's exciting about encapsulation is it's one of the last few things we do to prepare the spacecraft to get ready to go on the launch vehicle. It's exciting because you know we're going to be launching in a few days, which is the most exciting part of working this mission for the past couple of years.
TESS has to be ready for prime time when it gets into orbit, which means the last of its covers used during processing have to come off. Once TESS is inside the fairing, it won't be seen again on Earth. The payload fairing has been opened into two halves, and they're positioned on either side of TESS. The spacecraft is surrounded. Slowly and carefully, the fairings are moved into position until TESS is locked inside.
The encapsulation has just been completed. Right now they're getting ready to lift the spacecraft, the encapsulated spacecraft, onto the trailer, which they'll then transport to the launch site. And from there, they'll make the encapsulated spacecraft to the launch vehicle, and at that point, that's the last major thing before we get ready to launch. And that is exciting.
A specialized transporter rolls into the processing facility's high bay. It's here to take the payload fairing and its precious cargo to be attached to the Falcon 9 rocket. Getting TESS to this point was no small feat. It took several teams working closely together to ensure every system and every piece of hardware are ready for this mission. With the crane doing the heavy lifting, the fairing rises off the floor. It's guided toward the transporter, with team members helping every inch of the way. The fairing must be attached securely to the transporter for the final miles of its journey on Earth. There is no margin for error. The Falcon 9 rocket is waiting.
The Falcon 9 for the test mission is a new launch vehicle. We are planning to recover the first stage from the test mission on the drone ship, Of Course I Still Love You. If successful, this will be the 24th successful booster landing for SpaceX. By recovering first stages, not only do we understand more about our launch vehicle, it also enables us to reuse and refly that hardware, which is a key part of the SpaceX mission.
The fully assembled Falcon 9 rocket, with TESS on board, rolls out of the hangar at Space Launch Complex 40 at Cape Canaveral Air Force Station. Its final stop, the launch pad.
The SpaceX team is really proud to be part of such a cool mission, the TESS mission. The TESS satellite is looking for planets outside of our solar system in our galaxy, which aligns very well with the SpaceX vision to make life multiplanetary. To prepare for the rocket to be vertical on the pad today, the engineering team in the hangar did those final last checks. We mated the fairing to the rocket, and once the launch vehicle was finally checked out, the rocket rolled out of the hangar late last night and went vertical early this morning.
TESS is healthy. The Falcon 9 rocket stands ready. It's time for the final countdown.
So launch day is a pretty incredible day. Those last few minutes, you're just holding your breath. You find yourself holding your breath until, you get that T0 count. I lead a team of LSP engineers to successfully launch our spacecraft into orbit.
The SpaceX team has partnered with the NASA Launch Services Program, NASA Goddard, Orbital ATK, and MIT to enable that planet-finding mission.
We go on console about maybe 3.5 to 4 hours prior to launch. We do our voice checks to make sure we can activate and we have all the voice channels that we need to listen. We're listening to at any one point in time, maybe 6, 7 voice channels at the same time, so you're kind of training your ears to listen for your call sign. The team has a great responsibility to be able to look at all this data and say, yes, we are go for launch.
LD, go for launch. Falcon 9's in startup. Falcon 9 is configured for flight.
3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS.
status check to proceed with terminal count.
There is a moment at the start of every mission when everything comes together. A moment when years of preparation and planning are put to the test.
Clear to proceed.
There are no second chances.
You have permission to launch.
Success or failure is just a heartbeat away.
Rock report range status. Range green.
A spacecraft and its rocket on the pad, fully fueled and ready to launch.
Status check. Go Atlas. Go Centaur.
In that moment, a controlled explosion is released with such intense power it can propel a spacecraft off the Earth and into space for the benefit of all. We call this moment T0. This is its story. NASA is about to do something we've never done before. Nestled along the mountains on California's central coast is a little talked about space launch center known as Vandenberg Air Force Base. From here, history is about to be made.
This is the first time we've had an interplanetary launch from Vandenberg Air Force Base in California. The cool thing about this launch is that we've got such a capable rocket, the Atlas V, we don't have to launch from Florida.
InSight is going to be the first time we've had a spacecraft leave Earth's orbit launching from California. We've actually done studies for it even up to decades ago, but it just comes down to whether or not the mission had extra propellant left over and whether there was an operational reason to switch from an East Coast launch to a West Coast. This is just the first time all of it came together.
What we're going to do is we're going to unload the spacecraft really carefully, and then we're going to drive it a couple of miles to the Astrotech facility where they have a clean room all set up for us. Got about 2 months here. All we got to do is clean it up, test it out, put the fuel in the tanks and bolt it on the rocket, and off we go to Mars.
InSight is NASA's next groundbreaking mission, literally designed to break ground on Mars. Using probes and seismometers, InSight will listen for Mars quakes and measure how much heat the planet's interior gives off. If we're going to truly understand how rocky planets like Mars and Earth were created, we need to look inside.
It's unlike other missions that we've done to Mars. We have a number of orbiters, a number of landers that we've successfully explored this amazing planet. But this actually is the first mission where we're really looking on the inside, the inner space of Mars.
Sending a science mission to the Red Planet is never easy. Landing a probe on the surface is even harder. To accomplish this, InSight will have to shed its many components in a matter of minutes, bit by bit, like peeling an orange, until only the lander is left.
So the crew stage itself is the critical component that actually gets us to Mars. There's an aeroshell that absorbs the heat as we re-enter the atmosphere. That aeroshell enables us to go through the atmosphere of Mars successfully without getting the inside, the lander itself, too hot. We deploy a parachute. That parachute does two things. It really ensures the stability of the aeroshell as it's starting to get closer to the surface. It also slows down the spacecraft further until finally we drop out of the combination backshell and parachute, and then we do a propulsive descent down to the surface.
We know water exists on Mars, and where there's water, there could be signs of life. But we must ensure any organisms we discover weren't simply stowaways from Earth. This is where the Planetary Protection Team comes into play.
Planetary protection is what we do to responsibly explore other planets and moons in our solar system. In order to do that, we need to make sure that we send a clean spacecraft there. We would hate to get to another planet or moon and think we discovered life, but it was actually something that we brought with us. So we collect our samples on InSight, any part of InSight that's going to land on the surface of Mars. We bring it back to our lab and we process it using a NASA procedure. If we run into a situation where we take a sample and it comes back as having a higher number of bacteria than what we want, then we make sure that the engineers go back and clean those surfaces with the whole idea that we don't want to cloud our ability to potentially find life on another planet or moon.
Lockheed Martin Space of Denver, Colorado, built InSight with an extremely efficient design, streamlining what needs to be done at the launch site. They shipped the spacecraft to Vandenberg with no assembly required. Simply check it out, fuel it, test it, encapsulate it, and it's ready for launch.
The processing for our spacecraft has been very smooth. A lot of the processing had to do with fueling the spacecraft, removing some remove before flight items. Everything else was pretty much already installed on the spacecraft in Denver, Colorado before it was shipped here. And that's called a ship and shoot, which means there's not too much to do except for to fuel the vehicle and do some last minute power on checkouts of the onboard computers and subsystems.
These preparations are crucial. Everything must be working perfectly before InSight leaves Earth. This effort is designed to ensure a safe arrival and landing following the 6-month trip from Earth to Mars. In the meantime, United Launch Alliance, or ULA, is busy at their launch pad, Slick 3, assembling the world's most successful rocket, the Atlas V.
Well, I mean, we're building a rocket. What's not exciting about that? And really excited to be able to launch the first planetary mission from the West Coast.
First, ULA stacks their Atlas V booster onto the launch platform. Atlas V is powered by the mighty RD-180 rocket engine. The RD-180 is a powerhouse, burning highly refined kerosene known as RP-1 and liquid oxygen for thrust. For this mission, the RD-180 has more than enough power to get InSight off of Earth and heading towards Mars. When the booster's fuel is spent, the Centaur second stage kicks in and finishes the job. Centaur won't actually hit Mars. It will fly just past it. Final course corrections will be done by InSight itself to enter the Martian atmosphere and land on the surface. Once fueling and testing is complete, the team from United Launch Alliance will encapsulate InSight inside its payload fairing, the shell that keeps InSight clean and safe during its dangerous ascent through Earth's atmosphere.
We're at the phase of the mission where we're encapsulating with the launch vehicle, and the ULA team with their fairings now come in and they take the two halves of the fairings and they make a clamshell around the spacecraft to help protect it for the environments that we see during launch. And we do that because as we leave the Earth's atmosphere, the air and the molecules in the atmosphere would tear up our spacecraft otherwise, and the fairing is there to protect us.
With InSight encapsulated in its fairing, it's time to move the payload out to Slick 3. But this California coastline comes with its own set of challenges. The surrounding marine layer can swallow up a launch pad, reducing visibility to under a couple hundred feet.
So right now, it's on the transport vehicle and it's ready to roll. And we'll be rolling out around 2 a.m. At that point, we'll have a convoy that drives very slowly from the payload processing facility out to the Slick 3 Atlas V facility. And once it arrives, we'll hoist the encapsulated spacecraft up to the top of the mobile service tower and place it on the launch vehicle.
This morning when it was sitting on the truck and they put the crane on it, they started lifting it up. That's the last time this spacecraft's ever going to feel the ground of Earth. I'm just kind of jumping out of my skin. This is so exciting. We're getting so close to launch, and it's been a long, long road for me. This has been a challenging program. I mean, we've had a lot of technical issues to overcome. We actually had to stand down back in 2015, but since then we've gotten it all together, and things have been going so smoothly the last year. We really feel really confident about this launch now. We got it on top of the rocket. We're going to blast it off in just a few days, and when it gets to Mars and lands, finally it'll have solid ground under its feet again and get to work on probing the depths of Mars.
But InSight won't be traveling alone. Hitching a ride to the Red Planet are a pair of CubeSats, twin satellites called Marco A and Marco B.
So Marco is a dual payload riding as a secondary mission on its way to Mars.
So Marco is a pair of CubeSats, and CubeSats are really small spacecraft. They're essentially the size of a large cereal box, so about this big.
It's going to be relaying telemetry from the entry, descent, and landing of InSight back to Earth in near real time. After InSight is deployed on orbit and is heading to Mars, Centaur, which is behind me, ejects Marco A into orbit, and it'll slowly rotate itself so that Marco B ejects 180 degrees on the other side of the vehicle.
But Mako is a technology demonstration mission. It's actually one of the smallest spacecraft we've ever launched to interplanetary space. It's the first interplanetary CubeSat. So in of itself, it has all of these technology that we've never tested in deep space before. So if Mako works this time, one of the cool things that we could do is actually replicate that system and fly it with other missions in the future. And whether you're going to Mars or Venus or maybe even further away to an asteroid, you could think of it as bring your own telecom relay.
So everything went well today with the lift of the spacecraft and mate onto the rocket. It started off very foggy and windy, and right now it's a beautiful day, just typical California weather. And now we're ready to go to Mars.
But just as twilight falls across the base, the fog returns, cloaking the coast with a bone-chilling mist that will last until daybreak.
As we get closer to T0 liftoff time, a number of activities have to happen. There's a mobile service tower around the Atlas V rocket, and the InSight spacecraft is on top of the rocket, enclosed in the payload fairing. So we're going to back that mobile service tower away from the rocket to leave it exposed just beside the umbilical tower.
Stand engineer, proceed with MST roll to park position. Roger. MST bores shall be closed in park position. Roger.
The final launch pad preparation is underway. Once the mobile service tower is rolled back, InSight and Atlas V are just hours away from T0. Basking in the searchlights of the West Coast facility, they are presented with the glamour of a Hollywood premiere, fitting treatment for such an historical mission.
So there's a lot of excitement within the NASA launch team about the InSight mission. First time we're going to launch from the California coast, going to Mars. And what is really exciting to the team is this is the culmination of a lot of work. The teams have been working on this mission for over 5 years, and today is the day that they will see all of their hard work rewarded.
Status check to proceed with terminal count. Atlas systems. Propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Water. Go. Centaur systems. Propulsion. Go. Pneumatics. Go. LH2. Go. Facility. Go. Range coordinator. Clear to proceed. Launch director.
LC, you have permission to launch.
Go Atlas. Go Centaur. Go InSight. Proceeding with the count.
We're at T-minus 8, 7, 6, 5, 4, 3, 2, 0. And liftoff of the Atlas V, launching the first interplanetary mission from the West Coast. And NASA's InSight, the first outer space robotic explorer to study the interior of Mars.
Seconds after liftoff, the rocket punches through the marine layer, lighting the night sky for miles, visible all the way down to Los Angeles. An infrared camera showing the long tail of the exhaust plume captures some of the ascent, as well as an onboard ascent camera.
And we're nearing booster engine cutoff, or BECO.
Back to 4.6 Gs in preparation for BECO. Boost phase cooldown has completed. And we have BECO. Shutdown looks good. Stage separation. We have box and fuel pre-start. G&2 purge firing. The RCS is underway. We have ignition and full thrust. And we have indication of payload fairing jettison. Looks like a good step.
And the payload fairing that was encapsulating the InSight spacecraft has been jettisoned. The RL-10C engine, the second stage of the Centaur, continues to burn.
An hour and 28 minutes into the mission, the InSight spacecraft and the Marco twins are deployed from the Centaur upper stage, beginning the long voyage to Mars, where InSight will go to work shedding light on secrets hidden in the depths of the Red Planet.
Advanced Air Mobility, or AAM, is this vision of a new mode of transportation that will enable the safe and efficient movement of people and cargo by air to and from locations that are currently only accessed by road. One area the NASA team is researching is passenger ride quality. NASA's Advanced Air Mobility mission is researching what ride quality could be like for passengers traveling in eVTOL aircraft to make sure it'll be a smooth and safe ride. The idea is to conduct research on human subjects by studying their physiological response to the types of low-frequency motion, vibration, and noise stimuli that we expect AAM passengers will experience. We believe AAM aircraft will need to be designed smartly. They will need to be conducive to low cabin noise and low vibration from the rotors. They will need to be more resistant to being upset by turbulence. And they will need to be operated or flown in a predictable, repeatable, non-aggressive manner that will not result in large accelerations or sudden accelerations or rotations of the aircraft. It's really exciting to see the amount of innovation that is going on in the aerospace industry. It is truly a fascinating experience to see all these new designs come forth.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, and I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it, over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's still it's got better legs today than it did then.
Hi everyone, welcome to NASA's Goddard Space Flight Center. My name is Elizabeth and I'm the social media lead here for the Hubble Space Telescope. And we're live now with some really big news from Hubble. And here to tell us more about it, we have Dr. Jane Rigby with us, and she's a co-author of the result that we're going to be talking about, and also the operations project scientist for the recently launched James Webb Space Telescope. And we also have with us Dr. Patty Boyd, who previously worked as the Deputy Operations Project Scientist for Hubble and now works as the Chief of NASA's Exoplanets and Stellar Astrophysics Laboratory. Thank you both so much for joining me today. I'm really excited to hear about this Hubble news. And for anyone watching live, if you have questions during the stream, please feel free to comment them, and we're going to do our best to get to some at the end of the show. But for now, I think we should just jump right in. So, Patty, it sounds like Hubble just broke a pretty impressive record. Could you tell us what Hubble discovered?
Sure, I would love to, and it's really exciting to talk about this record-setting star. So, like so many other discoveries from Hubble, it starts with an image, a very beautiful image, and one of the first things that you can see in that image are galaxies. And those galaxies are actually gravitationally bound in a cluster. Those are fascinating objects in the universe. They have a huge amount of mass, and what's very special about this particular image, in addition to that beautiful cluster of galaxies, is it actually contains an image of a single star whose light left that object when the universe itself was less than 1 billion years old. So this is a rare event, and we're really excited to learn more about this object.
Yeah, that sounds super exciting. And just as a refresher for everyone, Hubble has been orbiting Earth for almost 32 years and is still generating incredible science like we just heard about. So Patty, could you also tell us just what can astronomers learn about our universe by examining this star?
So when we look at the stars in our own neighborhood, like when you look up at the night sky, those stars are in our Milky Way galaxy. They're in the same galaxy that we're in. We're a star, one of 100 billion or more in the Milky Way. And those stars evolved a lot like we did in this same Milky Way galaxy. And they're about, thousands of light years away from us when we look at them. So the light that from those stars is coming to us thousands of years later. When we're looking at this star called Earendel, we're looking at the universe itself when it was like in its first billion years. We're at 3.8 billion years now. The universe has changed a lot in that time. So Earendel is this rare window when we can actually look back and see how stars were working in those very early days of the universe.
Wow, that's very interesting. Thank you. And another cool part about this observation is that it was only possible because of an astrophysical phenomenon known as gravitational lensing. So Jane, can you kind of break down for us like what gravitational lensing is?
Sure. So we can see this star, even though we're looking back so far in time, because of two things. One, the speed of light's not that fast, right? So we're able, as Patty was saying, we look back in space to look back in time. And the other is this phenomenon of gravitational lensing, which is just the fact predicted by Einstein that mass bends space. And so light is traveling through a curved space-time, and so it acts like mass is bending light, gravity is bending light. Well, if you think about it, what happens when you're bending light? Well, eyeglasses are bending light, right? They're getting the light to change where it shows up in your eyeball so you can see better. So it turns out that this phenomenon of gravitational lensing, when you get big concentrations of mass, either a galaxy or better yet, a cluster of galaxies together, they can act like a cosmic telescope and bend the light, focus it toward, accidentally, toward us. And so this is a really rare phenomenon. About maybe 1 in 1,000 and 1 in 10,000 galaxies are gravitationally lensed. But when this happens, we can take advantage of these cosmic telescopes and then observe them with our human-built telescopes to see way farther than we normally can. And those background galaxies, they're way behind the cluster. They don't have anything to do with the cluster. We see them not only much brighter than they really are, but stretched and magnified, kind of like they're in a funhouse mirror. And that lets us study them in greater detail than we normally can with our current telescopes.
Okay, gotcha. That's really cool. And so another thing I'm wondering, like, how did astronomers, when they were making this observation, know that Earendel was an individual star rather than a bigger cosmic object?
Sure. So this is a cool case where this is a discovery that was half on purpose, half, oh wow, that's cool, which is how a lot of science works. So the cluster and the lens galaxy were found in 2016 by Dan Coe and collaborators. And so they found the arc and said, okay, that's a very high redshift arc, redshift 6, a lens galaxy at redshift 6, about 1 billion years after the Big Bang is how we see it. And so, and then Brian Welch, a graduate student at Johns Hopkins, was given the task of modeling this thing and doing the lens model of where's all the mass in the cluster and getting that to reproduce the distorted shapes that we see of the lens galaxies. And as he was doing this, there's this dot in the middle of the lens galaxy. And try as he could, that dot had to be really small in all the models, like super small, like the size of our solar system. And the magnification had to be really high, like thousands. And so the most obvious explanation is that we're seeing either one star or maybe a couple stars, but it's not like a big star cluster, but we're seeing down to the scales of individual star or multiple stars all the way out 1 billion years after the Big Bang.
Okay, wow. And speaking of, this star being within the first billion years of the Big Bang, Patty, how did astronomers know that about this star? How did they know it was in there?
That's a great question. And so, like many of the images that Hubble takes of these fields, these treasury fields, we're observing them to collect as much data as not only the team wants to get the science that they want to get out, but that the entire community can really mine that rich archive and get a lot of science out. So one of the ways you can get the most science out of an image like this is to observe it in multiple filters. And the filters are basically different colors of light. So they specify a certain range of colors. And so this is a multicolor image using 2 instruments on the telescope. And what that allows us to do is, for the galaxies, each galaxy is going to have a certain brightness in those filters. And we can look at how that brightness changes as a function of our filter. And what we see with these objects that are very far, they're red-shifted. We call it red-shifted. As they move further from us, the whole universe is actually expanding. The light gets shifted into the red. And what that will do to a galaxy's spectrum that's far red-shifted is it'll actually kind of block it out in the optical. You won't see the light there. It'll just start to peak out the redder and redder that filter gets. So if you notice in the image that smear that we're looking at, the sunrise arc it's called, it's very red compared to the rest of the image. And that's why, is the light's just starting to pick up as we go redder. And you can use that to estimate its redshift. And that is exactly how the objects in that arc are estimated. They're all at about the same redshift of 6.2. And you use that number and the photometric information that you have to estimate everything else. Its distance and then its size scale is related to that. So there's just a tremendous amount of scientific information in these multicolor images, in addition to just the beauty of looking at the galaxies that are in them.
Oh yeah, for sure. And Patty, also, why is it important to be studying this star that is within the first billion years of the Big Bang?
So when we look around at our local universe or the stars in our own galaxy, we get a picture of how the universe has evolved. And one of the coolest stories about that is where matter came from, where the heavy elements came from, where the carbon, calcium, oxygen that makes up everything, our bodies, our bones, our telescopes, where did those elements come from? And the answer is that they're fused in the centers, in the cores of stars. And massive stars in particular are very efficient at this. They fuse lower elements like hydrogen and helium into heavier elements, and then they explode in supernova explosions, and they spew that material out into their local environment so the next generation of stars can pull that in as they're forming. Those are the kind of things that form rocky planets like the Earth, where we've got like an iron core and all those elements in our atmospheres. Those were fused in earlier generations of stars. So Arendelle is this single star, the farthest yet that we've been able to observe, and it will allow us to see how that process started to be put together in the very earliest days. When did those very early heavy elements start to be infused into the material? And it's just a window that's opening up onto, the next big thing, because that light is pushed so far into the red that we need a telescope that can go even further into the red than Hubble can to really uncover the cool things.
Yeah, and speaking of, I think another fantastic part about all of this is that there's already approved observations to look at Arendelle with the recently launched James Webb Space Telescope, which is a super powerful infrared space telescope that just launched in December. We're so excited for it to begin science operations this summer. And Jane, could you kind of tell us how Webb might bring this Hubble discovery even farther?
Sure. So I learned about this lens star when the discoverers came to me, said, so do you want to be, we're trying to figure out how to plan some Webb observations. Are you in? I'm like, oh, I'm totally in. That's cool. So what we worked out was a set of observations with NIRCam, which is the near-infrared imager, to get colors in all of those filters that are too red for Hubble to do well, right, or to do at all, right? And so Webb will pick up where Hubble left off, getting redder filters. So we'll have very crisp, gorgeous images. We've already proven with Webb that we can take gorgeous images. It's as a very, very sharp telescope. And now we're getting the science instruments ready to go. The second science instrument that we will target for this galaxy and star is NIRSPEC, the near-infrared spectrograph. And so we'll be taking spectra of not only the lensed galaxy, the sunrise arc, but also the star Arundel. And so the NIRSPEC has a lot of cool bells and whistles. One of them is it has this microshutter array that has 250,000 doors that can open and close magnetically. And so we'll open up doors, we'll close most of them so we don't get the brightness of the sky in the way. And then we'll just open some doors for the lens galaxy and for Arundel the star. And we'll be getting spectra, right, with a little prism to tell us about what's inside that galaxy. What is the temperature of that star? How bright is it really? How, as Patty was talking about, how much of the heavier elements that were made in stars are in this galaxy versus just the boring hydrogen and helium that's made in the Big Bang.
Okay, gotcha. And so more broadly speaking, why is it important that both Hubble and Webb are going to be operating at the same time?
Sure, so Hubble and Webb are really complementary. They're not really in competition. When we built Webb, we knew full well there was a Hubble up there doing great stuff, and we didn't try to replicate that functionality. So it's really like players in a band, like, you know, your drummer and your keyboardist are doing different things. And so you select them for different skills. So Webb is really designed to do the things that Hubble can't. It has much greater spectroscopic capabilities than Hubble, so we can really see what the universe is made of, which is great because that's part of what my research is. I love spectroscopy. What's stuff made of? And then the other part is that we're operating in the infrared with Webb. So we're looking, the bluest light that Webb can see is like a dusky red, like red wine. And then it just gets redder from there, right? So whereas Hubble can see into the near infrared, and then it can see pretty hard into the ultraviolet, like bluer than cats or bees can see.
Okay, yeah. It's going to be really great. I'm very excited for them both to be working together up there. And back to Hubble, Patty, could you just sort of tell us how Hubble's doing these days? How long we can expect it to last?
Sure, absolutely. So Hubble is actually doing great. And it was launched in 1990, so it's coming up on its 32nd birthday in space. That is a long time for an observatory to be in space. It's in a low Earth orbit, and its orbit was chosen so that it could be rendezvoused with the space shuttle. And astronauts could actually grab it and bring it back into the bay there and service it. What servicing meant was that it could refurbish the instruments, refurbish the computer, the power systems, and this was done 5 times during the lifetime of Hubble. During the last servicing mission, the astronauts worked very hard to leave the telescope at the peak of its capabilities. And ever since then, there's been a team of engineers and scientists working together on the ground to extend the lifetime as much as possible. So we're expecting Hubble to continue into the next decade so that we can squeeze as much great science out of Hubble as possible.
That's fantastic. Thank you, guys. All right, so bear with me for a second. We've been getting some questions from social media, so let's see if there's anything we can talk about here. Okay, so we did talk about this a little bit earlier, but maybe, Patty, if you want to go into this a little bit more. Someone on YouTube is just curious, more knowing about how we can tell this is a star rather than, you know, a galaxy, basically. Or Jane, if you want to take that one on,
Sure.
either way.
I can take that one.
Okay.
So the main constraint that it has to be really small. So the main constraint is that it's really small and really bright. And so the size constraint comes mostly from the fact that in the images, it looks like a dot. It's round. It isn't stretched. And if it had any significant size, like bigger than the size of our solar system, then given the really high magnification, we would see it stretched. But we don't, we see it as a dot. And so that places a really strict limit on the size. In the paper, we give it in terms of, but it, you know, it's got to, they're all about the size of the solar system. So it's got to be smaller than like out to Pluto, right? So that's one constraint. It's got to be something that fits in a small box. Okay. And given that really high magnification, something like thousands, and it's whether it's 1,000 or 10,000, we showed a bunch of different models to show that it's somewhere in that range, okay? So you have something that's given its brightness and magnified by factors of 1,000, well, that's like 1,000,000 times the mass of the sun, 1,000,000 times the luminosity, the brightness of the sun, okay? So, all right, what is out there that is bright as a million suns and fits in our solar system? Well, that's really very massive stars, or binaries, could be binary, or it could be a accreting black hole. But we also know it hasn't changed in brightness. So we have observations. Hubble has observed this star multiple times, in part to look for supernova, to look for lensed exploding stars. And in those multiple epochs, we don't see any sign that it's changed brightness. So one of the characteristic features of accreting black holes is that they go up and down in brightness and they change. And so we think the most likely explanation in the paper is that this really is a massive star.
Yeah, okay, makes sense. Thank you. Awesome. Well, thank you all so much for sending in these questions on social media. I think we are unfortunately running out of time for today, though, so we're going to have to wrap things up. But thank you all for tuning in to learn more about Hubble's discovery of the farthest individual star ever seen. This is a really cool story, so if you want to find out more, be sure to check out nasa.gov/Hubble. And as always, you can keep up with Hubble on social media at NASA Hubble on Facebook, Twitter, and Instagram. Thank you all so much for joining us today, and have a great weekend. Bye, everyone.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, and I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong, to hold it all together. So over the process of working on it over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term warm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's still it's got better legs today than it did then.
Hello everyone, I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Surely good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small. Something you might have at home. A little stick of chapstick. We'll go ahead and use our force, being our bungee cord here. We'll put it on our bungee, and we'll pull it back. And let it go. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of the force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have, so let's see how the acceleration is affected. Pull back the same amount on the force, and here we go. And there you have it, Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times. You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
Mission and liftoff. Touchdown confirmed. Hello, United States.
To explore every phase of cosmic history.
It's all about the Earth and what we can learn about it from the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Center 2 for velocity calcimation. You can go ahead and leave steps 4, 5, and 4, 6. We're moving on to
Tracy,
step
you
5.
want to go right now for that activity?
Thank you.
Okay, Tracy, we copy, and that's good information. We'll pass it along.
Welcome back. This month on Station Life, we're going to highlight the International Space Station as a platform for studying the Earth and take a behind-the-scenes look at what it's like to live and work aboard the International Space Station. You know, they say a picture's worth 1,000 words. The first pictures taken by humans from space forever changed the way we view ourselves and our world. If you've ever flown on an airplane in the window seat, you know the natural desire to stare out the window. Well, aboard the International Space Station, one of our favorite things to do during our off time is to stare at the beauty of our home planet.
take a moment every day to look out the window and appreciate where you are.
Literally watch the Earth go by. We're going around the Earth once every 90 minutes. So you see a sunrise and a sunset every hour and a half.
It's just so vast and so vibrant in color, and so much contrast between the black that it kind of overwhelms you at first.
Don't just look out the window during the day. Go for the times between day and night, and then night and day, and take some time to look out into the universe at nighttime, because that's when you can really see all the stars. And you can see that the stars are not only like in a planetarium where they're sort of in a 2D field, they're actually 3D, and some are farther than others.
But you could see the blues and the oranges and the reds and the whites and the yellows, and really see more color about the stars, which indicates more about where they are in their life cycle, what kind of things they're burning and doing. And you would think that you'd get tired of looking out the window, but you never do.
Like I said before, a picture's worth 1,000 words. But in the case of International Space Station imagery, a picture could also be worth 1,000 lives. An imaging system aboard the station called Environmental Research and Visualization System, ISERV, captured photographs of Earth from space for use in developing countries affected by natural disasters. This is yet another way the orbiting laboratory is serving humanity off the Earth for the Earth.
SURVEYOR is a joint NASA and USAID program where we're working with developing countries around the world and strengthening their ability to use satellites to address the many problems that they have, including floods, fires, harmful algal blooms, and other types of events that they have where they can use satellites to really make better decisions.
We're using space information to help decisions that affect people in the village where they live.
When there's a major disaster, governments around the world come together, and they provide all of the satellite data basically that the world has to offer. But there's smaller disasters that occur in the countries that we work in that may not make the front page of the New York Times, but in that country it's a really big deal. We asked ourselves, could we make a difference if we had a dedicated imager for acquiring imagery quickly after natural disasters, and to be able to provide that imagery back to the countries that need them, that have real decisions that need to be made with a very quick turnaround. As NASA, we looked in our own backyard and started thinking, could we use the International Space Station? The International Space Station was really a fantastic asset to take advantage of because it passes over 90% of the Earth's populated area every 24 hours. We developed an imaging system and we called it ISERV, which basically is a camera and a telescope system that sits inside the International Space Station and can collect imagery when it passes over natural disasters or other events that we need to collect imagery.
Initially, we were planning to take few pictures per day.
So we contacted all the USAID missions around the world, and in total we had more than 2,000 requests coming, for people who need images from ISERV.
And we moved to 1,000 images per day.
We provided ISERV imagery for many, many natural disasters, including floods and fires, for deforestation, for volcanic eruptions, for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
And now we have a huge archives of images of areas around the world. So this is something that was not really there before.
ISERV is an example of, in essence, making the International Space Station even more international and connecting space to village to better understand and protect our home planet.
Imagine bread loaf-sized satellites zipping around the Earth each day, imaging the globe and providing updates on the environment. Thanks to the International Space Station, this constellation of satellite image gathering has been made a reality. With the mission of photographing the majority of the Earth every day, Planet Labs created small satellites, individually referred to as doves, to capture ground imagery for use in humanitarian, environmental, and commercial applications. With the 2005 NASA Authorization Act designating the U.S. segment of the station as a national laboratory, the space station drives growth of a robust commercial marketplace in space through endeavors like Planet Labs. The Earth imaging mission of Planet Labs' Dove satellites takes another leap toward creating benefits on Earth, resulting from innovation in space.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That, in many ways, was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
And they called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage. So we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than one or two satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GIM airlock, it's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
I used to think when I was growing up in Florida, lots of thunderstorms in Florida, you know, that here's this storm over top of me and it's just this individual little thing that just is about a storm over Florida. And in fact, now after looking at the Earth from space, I see that that little storm in Florida is connected to Africa and Europe and all across the planet. And one of the most impressive things to see is how the Earth presents itself as alive when you're watching these storms at night just trickle across the whole surface of the planet like its own nervous system. And the emotions of the Earth, you know, seeing storms that are developing and the way you know from having that experience on Earth how it's probably impacting the people and the places down there. It's like, oh, is it upset and mad today versus the sunshine over some other part of the planet? And really gets you looking at it in a different way, an appreciative and respectful way. When you're crossing the deserts in Africa and the way the dunes form, and they almost look like little, birds have run across the sand. And then this contrast you'll get from kind of the pinks and oranges and whites to these dark grays and almost deep blues and of rocks and everything that are intersecting with it. And the Bahamas and the northern coast of Venezuela, which quite honestly is, I think, the most beautiful place on our planet. It is just incredible.
Well, so far we've learned about using the ISS as a platform for iServe, which captures imagery of the Earth to provide disaster assistance, and deploying small satellites called doves. We expect good things to come from both of these experiments and look forward to their robust potential. NASA has selected proposals for 2 new future instruments, Getty and EcoStress. These sensors on the ISS will give scientists new ways to observe how forests and ecosystems are affected by climate change. Our next piece is about a recently completed mission of an Earth-observing instrument on the ISS called HYCO. Its name stands for Hyperspectral Imager for the Coastal Ocean. Check it out.
Carroll Township's a very rural area in northern Ohio, right on Lake Erie. Lake Erie has always been very important to Carroll Township and its residents. We use it for drinking water, we treat it, and it's really our livelihood.
In Lake Erie, for what unknown reason, suddenly the toxin level spiked, and that got through the treatment system.
It was indicated to me that it is pretty dangerous.
Cyanotoxins can cause skin rashes,
Headaches,
nausea,
vomiting, stomach problems,
nervous system problems,
liver damage,
to death.
We sampled and we had about 2.5 times the limit from the World Health Organization. The second sample was approximately 3.5 times. Our plant wasn't set up to handle what was coming in from Lake Erie. One of my biggest worries was actually hurting someone or even worse. So we shut it off right away, shut everything off. We had a very close call that day. The last thing you want to do is produce an unsafe water and allow your people to drink it. What we need is a better way to track and predict these cyanobacteria entries from our source water so that we can make sure that this never happens again.
A lot of the times we'll find out after the fact that there's a problem with cyanobacteria in the water because the blooms already occurred. We either get results of sick animals or sick people. We need a paradigm shift. We need to go from being constantly reactive to these blooms to having a capability that allows us to become proactive. And the U.S. Environmental Protection Agency has been very encouraging of allowing for some high-risk, high-reward projects. And that allowed us to think outside the box, way outside the box. We've been fortunate enough to make use of a sensor on the International Space Station called HYCO, which stands for the Hyperspectral Imager for the Coastal Ocean.
HYCO consists of 2 instruments. One is a camera, and the second instrument is a spectrophotometer, which actually gives us the spectrum of light leaving that water.
The camera on a cell phone, for example, contains about 3 bands of data in a red channel, a green channel, and a blue channel.
HICO gathers light from the red, orange, yellow, green, blue, indigo, and violet parts of the spectrum. So using this technology, we're able to now detect those water quality parameters such as water clarity, what the phytoplankton concentration is in your water, how much light is being absorbed in your water, as well as what's the distribution of cyanobacteria in those waters, and does that concentration pose a health hazard?
So what this means is instead of waiting for someone to report that there's a problem with cyanobacteria bloom, we can monitor these water bodies from space
and get information that we can rapidly get out to the water quality managers through a smartphone application that we've developed.
So the app allows you to drop a pinpoint, and that pin can be placed in an area where a drinking water treatment plant may have an intake, and see what the current water quality conditions were. Each user gets that information near real time, so they can make judgment calls on whether they have to respond or take action.
Having the HICO on the International Space Station has been the ideal test bed for our research.
This is an amazing partnership. The Naval Research Laboratory had HICO on NASA's International Space Station. As HICO acquired a scene, it was transferred to the Naval Research Laboratory. And then the Environmental Protection Agency was able to do the analysis and the validation to send this information out through a prototype mobile application. Yes, this technology will reduce costs and provide near real-time information. But the big goal here is protecting humans. And if we can reduce exposures both to humans and even animals, then we've achieved our goal.
Our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. Utilizing the ISS as a ready-built platform for studying the Earth is well underway. So far, we've learned about iServe, Planet Labs Dove satellites, and HICO. 2 more experiments, or payloads in NASA speak, are on schedule to get to the ISS later this year. There's SAGE 3 and Lightning Imaging Sensor. SAGE 3 will measure ozone and other gases in the upper atmosphere to help scientists assess the ozone layer and how it's recovering. And that Lightning Imaging Sensor will monitor global lightning for Earth science studies and support operational weather forecasting and warning. Looks like utilizing the ISS to further benefit all of humankind? It's right on track. Thanks for joining us on Station Live at our behind-the-scenes look at using the International Space Station as a platform for studying the Earth. And be sure to follow us on Facebook and Twitter for the latest research news. And don't forget to download our straight-up gangsta app on your mobile device. It's totally legit. Until next time, we're working off the Earth for the Earth.
And liftoff.
10 seconds.
I think what you get a sense of is just how awesome the universe is and how tiny each of us are in the grand scheme of the wonder that exists out there. Realizing that and realizing just how overwhelmingly huge the Earth is, how overwhelmingly the physics dominates what we're doing, and that we're living in this solar system, galaxy, universe, lets you know that this is someplace kind of special. To be a part of the mission that serves on station, to be part of the mission that goes exploring space into this vastness is simply, one, an honor, but two, almost mind-changing. Mind-changing because we have businesses, we have missions here, we're focused on accomplishing the near-term goal. You get up there and you see the overwhelming portion of the Earth, the vastness that you're exploring into, and you go, wow, there is just so many questions, so much for us to do, so much for us to be able to help our brothers and sisters with. We had a special opportunity on space station because of the window arrangements to be able to seriously get immersed in the imagery. Going to the windows to watch areas that were of great interest. Patagonia, for instance, is just a beautiful, rich environment of earth tones as well as the glaciers, the water. It is just picturesque to the point where you go, I need to go visit that place. You want to find things on the Earth because it is memorable, but also insightful. For instance, you're going over a tan and you go, oh, you know what, I bet you I'm close to the pyramids. And so you go to the window to take a look at if you are close to the pyramids, and then take some shots that you can take home. There are areas of the world that have volcanoes, and you just happen to catch in one photograph 2 or 3 active volcanoes. It's a nice experience to be able to look out the window and go, wow, we really are seeing the living Earth living, and being able to be a part of it from such a vantage point. We saw Hades troubles while we were up there. The Gulf oil spill from the horizon occurred while we were up there. A number of hurricanes or tropical cyclones occurred while we were up there. You know there's a ton of energy in there. You know it's heading towards populated areas. It's not beautiful at that point. It's utter respect is what I would categorize it. I got visited by 3 space shuttles. Several of the crew members never looked outside the cupola before. I would bring them one at a time to the cupola. Tell them to close their eyes, open up all the windows, the shutters on the windows, and then tell them to open up their eyes. And that instant, when you're overwhelmed with that vista, when your eyes see nothing but the beauty of the Earth, every single one of them, every single crew member that I brought in there for that exposure cried. It is heart-stopping. It is soul-pounding. It is breathtaking.
Wherever, however, whenever. We're here, there. We're everywhere. NASA Space Communications and Navigation. Exploration enabled.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, everyone, and a very pleasant good evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Educations, and welcome to the Von Karman series. It has been a pleasure and an honor to bring these talks to you. In the 1930s, a group of amateur rocket enthusiasts nicknamed the Suicide Squad essentially founded NASA's Jet Propulsion Laboratory. Their goal was to do the impossible, to reach beyond. JPL today is the leading center for robotic exploration of the solar system, daily reaching for that beyond and making it possible. From landing on Mars to visiting every planet in the solar system, to Voyager's faint whisperings at the edge of the solar system. The JPL motto, taken from the Man in the Arena speech, is Dare Mighty Things. I am grateful there are these amazing human beings that dare these mightiest of things and create the next. Tonight, we'll talk with one of our robotic mobility engineers about the importance of autonomy in these groundbreaking missions and how they help us with the ever-present question of what's next. And before we go any further, I'd like to introduce our questions co-host for this evening. She is the lead producer for the studio here at JPL. Please welcome Rachel Etheridge. Hi, Rachel.
Thank you. Hi. Thank you so much, Brian, and hi, everybody out there. I just want to remind everyone watching that this is your space program. We want you to be involved with this conversation. So whether you're watching on YouTube or Facebook Live or LinkedIn, ask questions in the chat box, and our social media team, who are at the ready, will bring in as many as we can in our talk tonight. And if you don't see the chat box, just reload your page and it should be right there. On a more personal note, Hiro and I have been working closely together for over 2 years now, and I'm just so excited to be able to bring your questions to Hiro, who's our speaker tonight. Back to you, Brian.
Thank you very much, Rachel. And that's a pretty good intro. We're going to get into his bio as we go through the story, but please welcome Dr. Hiro Ono. Hi, Hiro. Hello.
Hello, Brian. How's it going? And hi, Rachel.
It's going wonderfully. Let's just dive right in, because when we're talking about the future, we're talking about what's next, we got to talk about where we came from, right? So Hiro,
Sure.
Tell me how you got here. Tell me how you ended up working at JPL.
Yeah, it's a long story, but that starts when I was 5 years old. My father was basically a space geek, so, if you bring up the first slide, he bought me this telescope when I was 5, and we spent many hours, right? To look at stars, look at planets, look at the moon, bring up the Saturn, that fascinated me. And then when I was 6 years old, this spacecraft called Voyager 2 went to Neptune. That was 1989. Maybe some of the listeners still remember. That was a sensational, news to me, to my father. We again spent a lot of hours in front of the TV, looking at, watching the news, following what's going on. And I remember one thing that my father told me, right, when watching about Voyager. If you, shrink the solar system, so that the Earth is the size of this tiny marble ball, then how far you think the Neptune would be? 3 miles. Oh, of course, I grew up in Tokyo, Japan, where my accent comes from. So he didn't say 3 miles, he said 5 kilometers. But anyways, can you imagine, imagine that this Earth is, this tiny marble ball, right? And then this spacecraft flew all the way through across the solar system, spending 12 years to get there, reach to this beautiful blue planet and send pictures back. It's so amazing. And, somehow I've heard that this spacecraft was created by this place called JPL. So, since then I thought, when I grow up, I want to build a spacecraft like Voyager. JPL has been a dream place since then. And 24 years later, luckily I arrived at my childhood dream place, and here I am.
So if this is your dream place, how did you get doing? We've talked kind of leading up to this about how you get to do your dream job every day. How did you get interested in autonomy? How did you get interested in this specific part of it?
Yeah, that's more like, maybe there's not singular point, but maybe, one turning point was that, when I was 12, my father gave me this, second-hand laptop. She worked for Toshiba. So that was Toshiba's, I forgot the model number, but that's the one before Windows. So there's no Windows, Macintosh, everything is in command line. So I got his second-hand laptop, and he, also gave me this book about C language, program language. And somehow I got into it. You type in command, you make the program, and then computer moves as I instructed. So that was my first time. What I did that time was basically creating games, right? That's all kids do when picking up programs. But then, as I, go to college, grad school, I found my passion to, this machine intelligence. So that's how I come to interest in it.
So you're interested in programming. Well, let's talk about why. Let's combine you and the amazing person that you are and the amazing thing that they're doing here at JPL. Why is this important to exploration?
Yeah, think about who are the best explorers on Earth.
Okay.
It's humans, right? Human beings, because we topped the highest mountain, we dove to the deepest part of the ocean, we flew the sky, we even went to the moon. But what makes humans the best explorer, right? We are not the species that can run fastest. We are not the species that can, swim, fly.
Yeah.
It's not the physical capability, it's the intelligence, right? It's our intelligence that makes us the best explorer. So now, we want to make the robotic explorer. Of course, our robot has to be physically capable to go through the space, and has to survive the environment for sure. But that's not all, right? We eventually want to explore, want the robots to explore the space like us. So therefore, we need intelligence for those robots.
Well, let's talk about that intelligence. I mean, it sounds science fiction when you use the phrase intelligence. I mean, is this becoming real? Is this becoming new? What's going on here? Yeah.
Right? It may sound scary, right? But actually, almost all, maybe all spacecrafts that flown before are more or less autonomous, right? So, if you open up the slide 3, I believe. There you go. The interesting fact is that the very first spacecrafts that we launched were fully autonomous. Examples are our very first spacecraft, the American first spacecraft, Explorer 1, and Explorer 4 is the one with, kind of pencil-shaped one. Actually, can you move to the next slide? This is an interesting one, actually. This was the very first probe that went to the moon, and its mission was to, take a single photo of the moon. But, around that time, there's no computer on board, right? There's even no receivers, meaning that we cannot send any commands. Once you launch it, the only thing we can do on the ground is to keep receiving the signal from it. So how does it work? How did they plan to take a photo of the moon with the spacecraft, right? They have a sensor that catches the moon's light, so basically it reacts to the moonlight. Romantic, right? Then activates the photo resistor or something to snap which didn't go well, but that was the fully autonomous and possibly dumb spacecraft way before. And then can you move back to slide 3? Around early 1960s, there's a revolution caused by digital computer. That was the time when digital computer was available for spacecraft for the first time, around the time of Apollo. So now, with the onboard computer combined with receiver, we can first, become capable to send commands to the space that has already been launched before, right? So this was revolutionary because spacecraft was still dumb, but we become capable of projecting our intelligence right, to space. Basically, making the spacecrafts our avatar, right? So that enabled us to do much more complex exploration. And there was a time, when Voyager was there. But still, the spacecraft like Voyager has its own onboard autonomy. The example was that, when Voyager 2 was launched, right after that, one of the receivers was dead. So onboard algorithm, was pretty simple if then rule, but it switched to the backup receiver, which saved the spacecraft. And, the Voyager 2 is still flying on the backup receiver for 45 years, which is amazing.
Pretty grateful to hear that as I'm wearing my Voyager 45-year pin right here.
Oh, there you go.
So if we're talking about Voyager, we're talking about, where are we now with autonomy? That's an amazing chart, but where are we today?
Exactly. So, this chart is kind of a rough sketch, but we see that the trend is inversed, inverted. Now we observe the increased level of autonomy again, and probably the Perseverance rover, the Mars rover that landed on Mars like 2 years ago or so. I think it's just a little bit more than 2 years, right? I think that's one of the smartest spacecrafts that ever flown through the world so far. Let's go to slide 5. There are a few notable capabilities, but one of them that I was deeply involved was autonomous driving. These days, the cars on Earth start driving semi-autonomously, but the fun fact is that we've been driving on Mars autonomously, at least in part, since I think 15 years ago or so. But for this mission, the Perseverance mission, we knew that we need to substantially enhance the capability of autonomous driving to achieve its goal. So, that's one of my contributions to this mission. This map, it's basically a drive map of Perseverance. We landed on the place called Jezero crater, which was a lake with water, some, I guess, 4 billion years ago or so. Therefore, some scientists suspect that we might be able to find the evidence of the past life that might have existed on Mars here in this place. Anyways, so we landed at the place where this arrow is pointing, and we first moved to the south, moved a bit to the west, and took a few samples. We moved back to the landing site, and then drove kind of counterclockwise to go towards the north-west direction. Each dot on this map represents the position of the rover for each sole Martian day. And note that at the beginning, these dots are pretty dense, right? Meaning that the rover was driving pretty slowly. After we came back to the landing site and then, observed that each dot is very sparse, meaning that the rover was driving pretty quickly. Around that time, rover drove around 200 meters per Martian day, or which is what, 100 and I don't know. I'm not good at conversion between meter and feet. Anyways,
you don't have to. You're working for now. You can work in the metric. You don't have to do it the other way.
Exactly right.
Yeah.
Anyway, so that was the time when we called Drive campaign. We fully utilized this enhanced AutoNav capability to push our limits to drive as fast as possible. And around that time, we, as I said, we drove around 200 meters per sol. Up to now, we drove about 60% of the distance autonomously. And just a few weeks ago, we again broke the record of the driving distance per plan. That was 655 meters. So we were very happy about how much this new autonomy capability, pushed the boundary of driving on Mars. Let's look at the movie on the next slide. Yeah, this was a time 5 years ago. when we worked on the development of the AutoNav, this is a place called Mars Yard. When we test these things regularly. Summer of 2018 was the hottest summer for us. I spent hundreds of hours with my colleagues, Olivier Toupet, Tyler Del Sesto, Mark McHenry, Mark, my mom, to test them, fix the bug, of this capability. Can you go next, please? And then this is not Mars Yard on Earth. This is real Mars. This is the real movie. Came out from Seoul 360 Drive. That was, I think, about, again, 200-meter drive. Yes, we are driving very nicely. And I think there's one more slide about AutoNav. Yeah, so this is the 3D reconstruction from the driving data I bought from which saw. Yes, so yeah, autonomy is helping Mars rover to drive faster and farther. But another thing to note is that autonomy also helped landing on Mars, which was the capability called TRN, Terrain Relative Navigation, which I was not involved, but that's basically an ability to allow us to, land, avoid the dangerous landing site, and land on a safe place. So yes, autonomy, means a lot for this Mars rover mission.
So autonomy is huge for right now. It's huge for these missions that we're working on at this moment. Something that these VK talks that we've tried to do is also remind people of the human element behind robotics and autonomy. This is a special mission for you in particular, right? The Mars 2020 mission.
Yeah, there was quite a bit of the personal story. Again, since Voyager, of course, I took a close watch on all the NASA JPL planetary mission, right? Magellan and Galileo, and in 1997, that's when I was 14 years old, I believe. Mars Pathfinder landed on Mars, right? That was the first landing on Mars since Viking. First Mars landing that I've seen, and so I watched on TV. There was this 7 minutes of terror. The 7 minutes right before the landing, where you cannot talk to the spacecraft. So the only thing that the people on the ground can do is to wait. So people waited, right, anxiously, right? Hey, what's happening? Did it crash on Mars? Did it go well? And the moment they heard from the Pathfinder the confirmation signal of landing, these people literally jumped around, right? Jumped around and yelling around, and some even cried, hugging each other, right? So I was like, wow, I've never seen grown-ups, jumping like kids like that. Yeah. Wow, that's something that I want to see in the future. And then, actually, I think we have a slide, which is slide 9. Can you move there? Yeah, there you go. That was Curiosity. But then, the next one was Spirit and Opportunity. That was 2004. So I was a junior in college. This happened again, right? So, okay, I thought I want to join them. So after my college, I came to the US for graduate school and got a PhD. And I thought the time is right. So I knocked the door of JPL. I interviewed, but I didn't get the offer that time. I was kind of brokenhearted. I went back to Japan and I got a university job over there. That was 2012. That was when Curiosity landed on Mars. So, this picture was from Curiosity. I watched it, I watched the webcast on my laptop in the school cafeteria. And I was like, what I'm doing here, right? I thought I was going to join them, but, I'm still on the other side of the screen. So, yeah, but then, luckily thanks to a few lucky turns of the events, I got a second chance, and I interviewed with JPL again. That time I finally got an offer. So that was again 24 years after Voyager 2. So after I joined JPL, I worked on Mars 2020 mission on many aspects. And 2 years ago, I finally could join the celebration. Except that was during the COVID, so I cannot see it on the lab. Instead, I celebrated from home. But can you switch to the next slide, please? That's gonna be slide 10, I believe. Yeah. So that's when I celebrated with my family in a super messy living room, of course, because my daughter was 4 years old. Your living room must be like this during COVID when you have a girl or boy. Yes. Yeah. So that was my moment of lifetime.
It's a moment of a lifetime, and we all were going through it. But that's incredible that you got to celebrate with your family. I'm just so happy for you because it's never a straight path, is it? Sometimes you have to move to the left and right and go backwards before you can come and get to do your dream job. But let's go back. All right, I want to jump back. I want to get back into this autonomy. I want to get back into science. I want to talk about that record you just said, because 600 meters. You said you didn't like to do we'll do it for you. It's about a half a mile, right?
Yeah, right.
That's a half a mile.
Yeah.
So what's beyond that? What's beyond Mars 2020?
Yeah, right. It's half a mile. That's the distance, basically to the nearest Trader Joe's from my home. Okay. Yeah. So yes, that is a lot to us, but it's not a lot to compared to how much we can run, how much we can drive on Earth, right?
Yeah.
But obviously, we can do more. There's an example from the past. Can you go to slide 11? In Apollo mission, from Apollo 15 to 17, we used this lunar buggy. Astronauts drove, 10 to 20 kilometers just in a few days. The max speed was 12 miles per hour, which doesn't sound very fast, but remind that this was not on 110 freeway. By the way, you cannot drive 12 miles per hour on 110 freeway when at a peak power. Anyways, that was on the moon, and 12 miles per hour was 100 times faster than the Mars rover. There are many reasons why the Mars rover is so slow, power availability, mechanical reasons, but there's another reason, if you look closely about this picture, it has pretty simple mobility system combined with a very intelligent perception and planning algorithm, but not in computer, on humans neural net, right? That was one of the keys, right? So, the question is, if we can, not completely replicating what humans can do, but at least can we do 1/10 of what humans can do? Can we get a little bit closer to what humans can do than what Mars rovers are doing? So, that's that motivates, some of my research projects. Let's go to slide 12. Yeah, so here's one example. When driving, I'm currently working as a rover driver. I'm a trainee, so I'm being trained. When we're driving the rover manually, we care a lot about terrains. We typically don't want to drive on slippery terrains because, in the past, our rover got stuck in sand a few times. But for the onboard algorithm, for the autonomous driving algorithm, it only uses stereo cameras, meaning that it can only use geometric information. It can tell that, hey, there are rocks, there are, holes, but it cannot tell like humans, hey, there are rocks here, there are sands there. If robots can tell the terrain type by itself, then probably it can drive safer and more efficient, right? So what we did before, can you go to slide 13? So, we trained a neural net, artificial neural net, to look at an onboard image and basically classify, hey, where are drivable rocks and soils, where are slippery sands. I did with my many colleagues, Dig and Nathan, Mike Payton, Michael Swan, many other people. We implemented that. We also implemented on a test rover and drove this dried river called Arroyo Seco right next to JPL. It went very well. So that could be one way that we can improve the rover's autonomy. Going to slide 16, please. Another thing that I did with Neil Okawa, Sharon Stafftree, Ethan Yue, and many other people. So we thought we maybe, so the one of the big difference between, the autonomous driving algorithm that we are using for perseverance and human drivers is that human has instinct, right? Right the moment when you see the environment around you, you can instinctively think, hey, that's the rock that you have to avoid. There's an open space over there. You don't have to think much, right? So I thought, can we replicate that kind of instinct by using machine learning? Yes, we can. We can train the neural net to tell which part of the terrains, which path options are more promising than the others, so that it can accelerate the planning algorithm. This is just two of many examples, but there are a lot of possibilities, by applying the latest technologies to, help future spacecraft more, safer and more efficient.
Well, in talking about this and planning this talk, I was thinking about this as I drove home about how I naturally know when to hit the brake. I know how far away I'm going to be. How you said the word train. How do you teach something like this to a machine?
Yeah, that's a good question, right? Any of my attempts to teach something to my daughter miserably failed. So I know how hard it is to teach, right? Something to, well, at least artificial neural net is not as rebellious as my daughter. So maybe that, anyways, yeah, but training the artificial neural net, particularly deep neural net, is challenging because it requires huge amount of data, much more than your kids require. So in the case of terrain classification, for example, right, you typically need tens of thousands, maybe hundreds of thousands of examples to make it reliable. So where we can get that data, right? So that was one of the challenges that we faced. We tried a few different things, but in the end, what worked very well was to get help from people on the internet.
Okay.
Can you go to slide 14, please? So during COVID, we launched this project called AI for Mars on internet. It's on the site called Zooniverse. Basically, it's like, we said, hey, everyone on the internet, would you kindly help us to create the examples to teach the rover? And actually, many people say, oh, yeah, right? So it's very easy. Anyone can go to the site. You can Google AI for Mars, number 4, stylized, and, open this page, and you can view the real images for Mars. And all you are asked to do is to put these bounding boxes around rocks, around sand. This training data comes to us, which is used to train our neural net, which might be used in future spacecraft. So I'm glad so many people were excited. We got, I think, 50,000 volunteers in total. We got, I think, around 600,000, labels, inputs from people. So I really appreciate, people's passion, to help future spacecrafts, make it smarter.
I like that you use the phrase passion there, because we'll do anything for Mars and for these things. But JPL is more than Mars, right? We talked about Voyager. We're talking about all these other places. Yeah. Let's go beyond. How does autonomy help us beyond the red planet?
Yeah, of course, Mars is not our final destination. It's one of the closest planets, and beyond the orbit of Mars, there are more interesting things, unexplored, waiting to be explored, right? Can you go to slide 17? One of those fascinating and underexplored worlds are these icy moons of gas giants. Around Jupiter, Saturn, Uranus, and Neptune, there are many moons, mostly made of ice or covered by ice. Europa, Ganymede, Callisto, Titan, Triton, and Enceladus. Those are just a few examples. They're fascinating because many of them would likely, not all of them probably, but some of them have subsurface ocean. There are liquid water ocean, right, below this thick shell of ice. Likely Europa, likely on Enceladus, maybe on Titan, maybe on other moons. And some of them, are considered potentially habitable. No one knows if life can live there, if it's there or not. But some scientists suspect that these oceans could be habitable. Among these icy worlds, one of the most fascinating worlds is Enceladus. Can you go to the next slide, please? Slide 18. Enceladus, this is a relatively small moon of Saturn. It's about 500 kilometers across. The surface area is around about Texas. So what makes this world unique is this geysers, found by Cassini when it flew near the south pole of this moon. It found that something was splashing out of this moon to space. It turned out that this is a water vapor, likely coming out from the subsurface ocean, meaning that there are cracks, in the ice shell. There are some conduit or crevasse. I don't know what it is. No one knows what exactly it is, but there is a mechanism, pathway, that water comes out from the interior of this moon to the space, and actually this water vapor forms one of the rings of Saturn. So, it's fascinating in many ways, right? But one reason is that, hey, this could be, a great pathway for us through which we can exploit. Let's explore more with the next slide, slide 19. This is, what scientists imagine the interior of the moon is. Again, as I said, there's a shell of ice below which there is likely a liquid ocean, and around South Pole there is conduit, geysers. So we thought, can we make a tiny robot that can dive into these conduit, goes down all the way to the ocean, and possibly, meet life if there's any. So can you go to the next slide, please? Some years ago, in 2016, my colleague and my friends and I got this, really small funding from a program called NIAC, NASA's Innovative Advanced Concept Program, to take a closer look about this seemingly crazy idea of sending robot down to this, active vents, and studied if it is ever possible or not. Skipping all the way to the conclusion, we found that, of course, no one knows how it looks like below the surface of Enceladus. There could be, infinite number of possibilities, but, there are two super roughly speaking, the reality could be more complex than this one. But super roughly speaking, there are two possibilities. One is that that this vent is wide open. There's a clean interface of the water from which the water boils and somehow accelerated and goes to space. The other possibility is called cryovolcanic model. It's basically inverted rocket nozzle. The high pressure liquid gas mixture goes up the vent and gas expands that propels the jet. We found that this idea of letting the robot going down the vent is likely feasible for open conduit model. It would be possible for cryovolcanic model. It is harder, but if the vent size is more than 10 centimeters, which cannot be guaranteed, but given that there seems to be more than hundreds of vent openings, what's the chance that we can find at least one vent that is more than 10 centimeters? Probably is quite likely. So can you go to the next slides, please? We did some experiments in the working freezer, and also next slide, we run some CFD, computational fluid dynamics, and then we arrived this robot. Can you go to slide 22, please? One more. We felt, okay, so this could be one way to make this happen. A tiny robot, maybe, again, 10 centimeter in width, maybe 30 centimeter in length, has a few limbs. At the end, there are ice screws to stick to the wall so that it's not blown away. Maybe it's going to crawl out of the lander and moves to the vent and go down. Of course, this is not the design of a robot. This is one of many possible designs, and we are actively exploring more promising designs. So this could be a fascinating idea. And then of course, this robot is going to go into this vent, which has so many unknowns. Right, you cannot fly your spacecraft above it and make a detailed map. So, it has to deal with uncertainty. It has to move vertically. You have to control this complex robot to do so, and also the environment is dynamic. So there are so many reasons that this robot has to be, again, highly intelligent.
So, Hiro, I want to jump forward and loop back. I want to talk about Voyager again and talk about autonomy in something like this. And if we go to our next image, you can truly see how alone it is out there. Talk to me about something like this and what is truly, after you being here for 34 years after this and all these great things, talk to me about that.
It's amazing, right? It's fascinating that this spacecraft, keeps flying after 34 years. When I was inspired, right? It's still flying beyond the heliopods, into the interstellar space. And interestingly, there's no other spacecraft still that went beyond where Voyager is, right? But surely someday, we should catch up and move beyond, right? We gonna explore the icy moons of gas giants someday. We're gonna go to the subsurface ocean. We're gonna probably go back to Neptune's system someday. In particular, its moon Triton, which is very interesting. Maybe KBOs. We know there are many Pluto-sized dwarf planets beyond the orbit of Neptune. Eventually, maybe interstellar space, right? Like TRAPPIST-1 system, which has multiple habitable planets, which may take, hundreds of thousands of years to get there, maybe, So, thinking about Voyager, right? It already happened. Sometimes, after a success was made, we often kind of take it granted, right? It's hard to imagine how innovative it was, but if you put yourself from the viewpoint of the past, this idea of ground tour, right? Visiting 4 major planets, gas giant planets, in one mission, which basically what Voyager 2 did, was initially conceived in 1965 by this graduate student named Gary Flandreau. And that time, 1965, what JPL did and what whole world did actually was to send only 2 spacecrafts successfully to other planets, right? One to Venus, one to Mars. And, that time, this guy was talking about building a spacecraft that lasts tens of years and going all the way to Uranus and Neptune and eventually to interstellar space. What you're talking about, right? That was the craziest idea at the time. No one believed it, laughed at it. But, but it happened eventually. JPL made it happen. So Voyager reminds us that, JPL is a place where grown-ups are allowed to dream big, right? And it's a place where those big dreams are turned into reality.
With that reality, before we started this talk, you were holding your child in your arms while you were setting up.
Yeah.
How, when you look at this and look for what's next, not just for this mission, but for all these missions, but for also life, I mean, how is this working for you?
Yeah, I mean, life means my personal life, right? I guess.
Yeah, I mean, I can hear it around you too. I can hear it right now live. It's a very exciting life you got. Yeah.
Yeah. So why don't you show the last slide? Yeah, that was actually last weekend. The Jupiter and Venus were at conjunction. So I took my daughter to the front yard and pull out the telescope from the garage and looked at the planets. I'm still getting stars, after 35 years when my father gave me this telescope. Not with my father anymore, with my kids. I like this. I like this a lot, to getting stars still. I think for 2 reasons, right? One is that, I said that JP is a place where we can dream big. But of course, we are not, thinking about big things 40 hours per week every day, right? There's so many, little things to bother, right? Just like any other workplace, hey, this thing was broken, we have to fix that bag. We are running on funding, we have to keep our stakeholders happy. There's so, many little things. But, if I go out in the night and get stars, that kind of let me forget about those little, things and, reminds me why I'm doing this job, where I started, what my big dream has been, right? And of course, it's also, for my daughter, right? To inspire my kids, like my father did for me, like Voyager did for me. We, work hard to, make our big dreams come true, which inspires the next generation, like my kids, so that they can even have bigger dreams. And when they grow up, perhaps they're gonna, work on their own dream. And that's the way that humans make progress.
That is the way that we make progress. Thank you so much, Hiro. There have been a lot of great questions out there on all the platforms, so I'm going to throw it back over to Rachel. How's it going out there, Rachel?
Oh, goodness. Okay, I'll tell you. We're not going to get to every single question. I think we maybe have time for about 5 or so. 4 to 5. Well, let's see how many we can get through. So, Hiro, there's so many amazing questions.
Rachel, can I interrupt you for a second? Your audio is getting a little fuzzy right now, so I'll ask the first one that you've highlighted for me. If you want to reload, and we can ask that back in. So Akshay on LinkedIn wants to know, did you find any differences or surprises in training Perseverance's autonav on Earth and when it started operating on Mars?
Great question. Yeah, maybe the biggest surprise is that it works so well. Right before we activated the autodev, my worry was that, what if my code crashes this, multi-billion-dollar rover, but it hasn't happened. It works so well, so yeah, maybe that's a positive surprise that I had.
Very cool. Rachel, you back with us?
I hope so. Am I back?
Yay!
Yes.
You sound great.
Welcome back.
Okay, thank you. Sorry, everyone out there, for the audio issue, but I'm glad to be back. Okay, so Mace Bob on YouTube asks to you, Hiro, do you think we're close to a robot being able to decide to pursue discoveries that the mission planners were unable to identify?
Unfortunately, we are far from it. In my opinion, yes, artificial intelligence made really impressive progress in the past, I guess a decade or so. Everyone knows about it. There are so much news about ChatGPT, for example. But in general, AI works very well as long as its inputs and outputs are confined within computer network. But when it has to handle the real world, it has to handle physical interaction. It's still way behind. For example, I'm a Japanese, so I can easily pick up tofu with chopsticks, right? That's a very hard task for robots. Picking up rocks, drilling a hole. So I don't believe that AI or or autonomy gonna take over humans, particularly in areas of physical interaction and creativity. So it's still far from the time when AI will replace our scientists, in my opinion. But AI is our helpful friends, and as it gets more and more capable, if it can do just 1/10 of what humans can do, we can just move way beyond.
Yeah. Oh, wonderful answer, Hiro. So we have time for 2 more questions. But on on a similar note, and I really like this one. Well, you'll see why. Josh on YouTube asks, how often is human input needed by the autonomous robots?
It really depends. Depends on the type of the algorithm you make. Learning is not the only way, right? Conventional autonomy algorithms, you can call it classical AI, is basically something that human engineers design, right? Instead of let it learn by itself, right? So engineers design how it's gonna behave, and you turn it on, then it keeps going, right? There are learning algorithms, and there are algorithms that needs to be supervised. That needs examples to be trained. There are algorithms that can self-train. It can teach itself. There are algorithms, it gets feedback from people, like teacher and students. Students, do some work, and teachers gives feedback, and so there are many different ways. So we cannot say, I cannot give a simple answer, but it depends.
Understood. Okay, last question. I'm sorry to not get to all of your questions. They are actually amazing, so I'm hoping we can send all of these over to Hiro, just so he knows what's on your mind.
I spoke too much. I should have.
No, you didn't. You spoke just the right amount. This one I'm very excited to ask. So what is one of your favorite moments that you've experienced of our solar system through a robot?
Oh,
it's a good one.
The question was, what's the best moment?
Yeah. Essentially, what's your favorite moment, right? Operating these rovers, you've experienced something that so few people get to experience. Maybe you can think of one moment. I'm sure there's many, though.
Yeah, I think it's still the landing of Perseverance, the moment, because, it's not because I was involved in landing, that was not my job, but, simply because, if it doesn't land well, then, everything that I did before was, go away, right? But also, I don't know, as a team, as a project, hundreds, maybe thousands of people, spent so many years to, make this happen. And it hinged on this, 7 minutes of terror, how this, autonomous robot can do its job by itself. And we were so anxiously watching it. And when this, confirmation signal came back from Mars, we are on Mars, that was really a, moment for me.
Amazing. On that note, Brian, I know you will close us out. Thank you.
Thank you. No, thank you both very much. That is all the time that we have for tonight. Please join us in April when we discuss Earth and the EMIT mission. I would personally like to thank Christopher, Colin, Max, Bill, Corey, Robert, Gabby, Emily, Rachel, Mark, Curtis, Nikki, Amanda, the Kims, Joey, and everyone behind the scenes who make these public talks possible. It truly does take a team. I would like to thank our co-host Rachel and our speaker hero for the passion, expertise, and general awesomeness. Our final thank you is to you, the audience, who join us every single month. This is your space program, and it is our honor to bring you these monthly talks. Stay safe, stay kind, stay curious, and we'll see you next month.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is how did Earth's atmosphere evolve over time, and how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. It'll take us 3 years to make the rocket, only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this? So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
This continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the iSCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp. We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the North and South poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight. Can you guys hear Kjellmar? We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish, if we can.
This is iSCAT. It's been very quiet, very difficult to launch.
Do you think we're gonna launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
Welcome to NASA Edge.
An inside and outside look
at all things NASA.
On today's show, we're going to be talking about nanotechnology,
which is technology that's really small, or as I like to say, co-host-sized technology.
Well, I think it's a little bit smaller than co-host. Maybe like the G.I. Joe with the Kung Fu grip, or maybe Ant-Man size small.
All right, Ant-Man I'll buy, but it's probably even smaller than that, probably deeply embedded in wearables for Ant-Man.
Well, you know, in today's show, we're going to be looking at nanosensors, nanowires, nanotubes, and composite overwrap pressure vessels.
Or COPVs.
Yeah, which is really what's interesting to me about the technology. It's not a single technology with a single use. It's a technology that's being applied all across industry in a lot of different areas, and even across NASA.
And speaking of COPVs, we're going to have Mia Siochio on the show today, and she's going to talk to us about how NASA is using nanotechnology in some upcoming tests.
But first up, I had a chance to talk with Steve Gaddis, who's going to give us a broad picture of nanotechnology. We're here with Steve Gaddis, the manager for the Game Changing Development Program Office. Steve, how you doing?
Doing good.
So Steve, we have this whole technology campaign where the theme is technology drives exploration.
Absolutely, and I believe it.
What's that mean, technology drives exploration?
It means if you want to do these cool things that we haven't done before, we have to develop the technologies to go do them. We can't simply just keep doing what we've already done in the past, right? We've done some cool things, but we want new missions. We want to go farther than we've been. We want to drill down. We want to bring things back. So we need these new technologies.
Now with Game Changing, you're sort of a subset of the Space Technology Mission Directorate at NASA headquarters. And so what's the focus on Game Changing as opposed to the other technology subprograms?
We're the disruptive program. We're the DARPA-like program out of the 9. However, all the programs, they're looking for revolutionary and incremental developments in technology. But our associate administrator really wants us to take some risk. He expects a certain amount of failure in the activities that we're pursuing, the high payoff, high risk type activities. And so he'd like to see the risk take place with us instead of maybe in some of our sister programs where we're demonstrating on orbit, or we're demonstrating on the International Space Station, or we're demonstrating on a ride with another government agency or the commercial crew type folks.
So when you talk about specific technologies in your program, are you taking programs from scratch, or are you getting programs from another group that have already been through a certain, mature process?
So it's a mixed bag. Some things we generate from scratch. However, what we like to see them get to a TRL, technology readiness level of around 2 or 3 before we pick them up. And in many cases, someone's done the basic research, whether it's industry or whether it's a university or whether it's some of our research centers. They've proved the concept. Getting from 3 to a TRL 6 or 7 is really where the challenge is, and that's where GCD fits, that mid-TRL range.
Now, when we talk about TRL, we're looking at a scale from 1 to 9.
1 to 9. 9 meaning it's flown in space multiple times, heritage. 6 or 7 means it's going to be demonstrated, or it was demonstrated in a relevant environment such as space.
And in your TRL range, it won't fly in space, but it will be tested here on Earth.
It depends, but that's primarily the focus. We do TRL 3 to 5 and 6, and 5 is a near relevant environment, could be a suborbital environment, but several things that we do also go on to station, right? So that's obviously in orbit, it's in space as well. So a small part of our portfolio does make it to space.
Now, what are some technologies in your portfolio?
Man, there's some really cool things. Some of which are far out, some are a little closer home. We're looking at wearable technologies, and that would be like in the old Star Trek days, when someone's got the comm on their shirt and they hit the comm and they can communicate. Others, it's relaying information back and forth. The astronauts need things like that. And we've been working on something called an exoskeleton, and essentially what this began to do was just provide exercise for the astronauts, right? They got to take all that equipment up there. It takes space, volume, power, etc. But if we can take this one it compacts, it stores very nicely, and it can give them that resistance exercise. But then the reverse of that is if they had to be in a situation where they needed a little extra horsepower, it could give them that as well. That's been a spin-off to the Veterans Administration, helping wounded warriors get back into action. We're developing new robots, humanoid robots. Then in a particular area that's of interest to me is nanotechnology, which is just a blossoming field. They're making almost daily discoveries with nanotechnology. They'll take these carbon nanotubes, they'll mix them with a fluid, and then this fluid will end up with a new characteristic that they can apply to something. So we're looking at making materials out of these nanomaterials. We call them nanocomposites. And if we think composites themselves reduce mass and cost, this takes it another order of magnitude. So we're very interested in it. We're looking at nanosensors, very small sensors that you can put on something that can track your blood chemistry and report that out. Also, sensors that can be weaved into something that you can't even tell it's in the material because it's a nano-type sensor. We're looking at a COPV, which is a carbon overwrap pressure vessel, right? So it's a tank, and we'll take this nanomaterial and we'll wrap it over this aluminum inner structure.
To strengthen it? Or?
Yeah, to strengthen it. And it also reduces the weight because it doesn't all have to be aluminum. We've got one of those that's going to be flown on the sounding rocket next year. We're very excited about it. We're also looking at nanowires. We just set a world record with a nanowire with the most electrical conductivity ever demonstrated to date.
That's amazing.
I mean, it is amazing. It's groundbreaking.
It's game-changing.
It's game-changing.
That's right.
It really is. So we're looking at the nanowires. We're looking at the nanosensors. We're pursuing the nanocomposites. Really cutting-edge, cool technology. Lots of things like that.
You know, Steve, he's a real game changer. He did a great job giving us an overview of how NASA uses nanotechnology.
You know, one day I'd like to see how nanosensors will work in things like watches and phones.
Well, you've come to the right place because we had a chance to sit down with two important people who are using the cell phone and nanosensors.
Yeah, we had a chance to talk with Maya and Jessica about how NASA is incorporating this technology into cell phones and using them in different ways. But what I'm really curious is, can we really understand just how small this technology is to do just that? May I understand nano is small. So with nanosensors, I'm assuming you're dealing with really small sensors. But what exactly are nanosensors doing?
Yeah, nanosensors are a product of nanoscience and nanotechnology. When materials go to that small scale, their properties are fundamentally different from bulk materials. So scientists all around the world, have been working very hard trying to take advantage of this difference in properties between the bulk scale and the nanoscale and trying to make useful things, which are devices, systems and architectures, materials for a wide variety of applications, touching upon every economic sector, which is electronics, computing, materials, manufacturing, health, medicine, national security, transportation, energy storage. And I don't want to leave out space exploration.
I was going to say, that's a lot of stuff anyway.
Yeah.
You mentioned space exploration, so I'm wondering, how are nanosensors being used by NASA?
The nanosensors are being developed to replace bulky instruments NASA has been using. No matter what you want to measure, whether you want to measure a composition of a gas or a vapor, or you want to measure radiation, historically we have always taken bulky instruments. And remember, every pound of anything that we lift to near Earth orbit, it costs us about $10,000 a pound. The same 1 pound of anything would cost roughly about $100,000 a pound, for Mars and other missions. Okay, so we have an incentive actually to miniaturize the size of the payload. So that's why we want to move from bulky instruments to sensors. That's one reason. The second reason is, no matter where we go, okay, we don't have utility companies sitting there waiting for us. Okay, we have to generate our own power, and we have to be very wise how we use that power. So the sensors, not only they're small in size, but they also consume very low power. So that's why over the last decade or so, we've been working on developing nano-based chemical sensors, biosensors, and radiation sensors.
Now, when you're looking at these biosensors, and we're looking primarily for crew health, crew safety, what would they be used for?
What are the applications? Yeah, we've developed them for crew health and diagnostic purposes. That's our most recent project that we worked with the Game Changing Technology Office on. And so for that project, we developed this sensor to look at a variety of different protein biomarkers for cardiac health. And so when you're in microgravity, there's a lot of strain that's placed on the heart. So to monitor the health of the heart for our astronaut crew is critical. So that is the most recent technology that we developed for them. We've also worked on this sensor looking at microbial contaminants and the water supply. So this is an environmental kind of application for NASA to make sure that the water that the astronauts are drinking is actually safe to drink.
Now, when you're looking at the astronaut's heart, is it a sensor that you place on their body, or is it something they ingest, or what? How's
This is an external sensor that will take 1 drop of blood and be able to screen for a number of different proteins. And depending on the levels of proteins and which proteins are present, we can make an informed diagnosis of the health of the crew member's heart.
Do these sensors have a long shelf life, or is it something that lasts for a short period of time because of the complexity of the sensor?
It depends a little bit on how we fabricate them and how we package them. The sensor itself, without any kind of surface modifications done to it, has a very long shelf life. I have sensors in my lab that are probably 10 years old that I can still pick up and use today. What limits the shelf life of these types of sensors is we often introduce some sort of biological probe molecule on that surface. So depending on what that probe is, that's going to dictate the storage needs as well as the shelf life of the device. We've been placing a lot of emphasis on making probes that are very robust so that we can increase that shelf life for our missions, so that we're not looking to replace these sensors every 6 months, that we can actually keep them for years at a time and continually reuse them.
And one of the coolest things that you're showing us this past week was the fact that you have a cell phone technology adapted to these nanosensors. So you have an application that you developed on the phone that can actually be used in concert with the nanosensor.
So this was designed actually for the chemical sensor project. And this phone has a plug-in port on one side that contains the sensor chip, has a fan that will direct airflow from the environment over the sensor surface. And then just using the electronics that are part of the phone, we have a nice little instrument that will actually read what kind of chemical environment the sensor is exposed to.
Now, would you have multiple nanosensors within that adapter for the phone, or is it just one nanosensor?
So we have one chip, but these chips can be made with a number of different sensors. They can have hundreds of sensors. They could even have thousands of sensors on one chip, all working together to tell the user of the phone what the environment is.
Guys, that was some great information on nanosensors. I can definitely see how that is a game changer, because once it's commercially available, it will definitely change our lives.
I tell you what, we could have spent a whole show on nanosensors. That's how cool the technology is.
That's right, Chris, but we're only scratching the surface at looking at this technology. I had a chance to sit down with Jim Geyer, and he explained how NASA is using nanotechnology to develop better, stronger wires. Let's check it out. Jim, I understand that you're working with carbon nanotubes as a potential replacement for conventional wiring, but I didn't know wiring needed an upgrade. What exactly are you doing to improve wires?
Well, I don't think a lot of people understand that wiring really takes up a large amount of the mass in current spacecraft and aircraft. Like a 747 has nearly 2 tons of wiring in it, and a space shuttle had over almost 300 miles of wire. This is a lot of weight, and so conventional wiring with copper, it turns out is very heavy. Copper is dense, and it's also not very strong. And so we're looking for a way to have a better mechanical properties, actually, than conventional wires have.
So these carbon nanotubes, when you make a wire out of them, how do they perform in terms of strength?
They're much stronger, they're more thermally conductive, so you don't get hot spots and so on. They're very flexible. They're actually much more flexible than copper, and they don't fatigue. Fatigue is when you get a breakage from moving back and forth.
That's how I break wire intentionally sometimes.
Exactly. And in fact, they ran tests and they were not able to run enough cycles to actually break these carbon nanotube wires. They finally had to give up and go on to the next test.
Okay, so the carbon nanotubes are stronger and they're lighter. How do they perform in terms of conductivity? Well,
conductivity is the issue. It turns out that carbon nanotubes, while theoretically have a very, very high conductivity, to use them practically, you have to make these bundles, because an actual carbon nanotube is less than microscopic. And so to use them, we have to actually bundle them together. And when you bundle them together, you lose a lot of that conductivity.
And that's principally where your work is then. You're going to solve this conductivity problem.
That's our goal.
Okay.
Right. What we're doing is we are chemically altering the carbon nanotubes. We're doing a process called intercalation, which means to insert, and we are inserting halogen atoms. These are bromine, chlorine, iodine, in between the bundles. And when we do that, it makes the bundles actually much more conductive. And so what we're trying to do is get to the place where our conductivity is high enough that we can run these as electrical conductors. They're not going to be as conductive as copper, but because the wiring in aircraft and spacecraft is not limited by the conductivity, but by the strength, we're going to be able to save a tremendous amount of weight. We're in the early stages of our research, but we've already developed carbon nanotube wires that have a specific conductivity. That's a conductivity per gram equal to copper.
Well, solution, problem solved. That's great. No, that's a good step, right?
It's a good step, but it's not the only step. Okay. Because right now we're working with very, very tiny amounts. I mean, milligrams of material, and we're going to have to work with kilograms of materials. And so we have both the process of our partners who actually make these fibers have to scale up so that they can make large quantities, and we have to scale up our chemical processes so that we can modify them.
Okay, so scaling up is actually the big challenge.
It is.
Okay, see, for a second I thought if I understood this properly, I'd understand how Peter Parker could shoot web. Okay, but apparently with the scale-up issue, not even he could handle it at that
I'm afraid not.
All right, well, appreciate it. I wish you the best of luck, and I hope soon to see copper wire. Well, I don't want to see them go away, but at least in terms of these aircraft and spacecraft, saving that weight and giving us all the conductivity we need.
I hope so.
It's interesting to see how NASA, as they improve on a technology, just how complex the process becomes. And I never would have thought about it, but creating nanowire is actually a groundbreaking or game-changing technology.
Yeah, and that's a cool area of research that Jim's working on. But another area that NASA's looking at is carbon nanotubes and overwrap pressure vessels. So what they want to do is they want to take a COPV, or a composite overwrap pressure vessel, and spin it with carbon nanotubes.
And those carbon nanotube composites are, as you said, very difficult to work with. So NASA is actually looking at a couple different approaches.
And I had an opportunity to look real closely at least one of those approaches. Let's check it out. We're here with Aslan Biagi, who's the project manager for nanotechnology. So Aslan, tell us about what you're doing with nanotechnology.
Our goal is to actually use the nanotechnology and make lighter materials so that we can reduce weight on the vehicles and launch vehicles.
And I understand you have a big flight test that you're moving toward.
Yes, so our carbon nanotube reinforcement composites that we're developing in the nanotechnology project will later be placed on a composite overwrap pressure vessel, which will be launched on a sounding rocket.
Haven't we launched like composite overwrap vessels before? What's unique about this one?
So COPVs have been on NASA for a long time. The only difference here is that we're using carbon nanotubes instead of carbon fibers, which is the typical material that we use for the COPVs. Now we're transitioning into carbon nanotubes, and that's actually making the material 2 times stronger than carbon fiber and also lighter. And that's the game-changing part of it.
Tiffany, how do you guys prepare for a carbon overwrap pressure vessel test?
So we start off by taking the tensile strength of ring specimens, where we have an aluminum ring and they're overwrapped with a carbon nanotube yarn and resin in a composite structure. And the reason why we do this is to help us predict the load at where our composite overwrap material is failing. So the rings are speckle painted for digital imaging correlation, so we can better determine how and where the failure occurs.
So you guys actually plan in these tests to actually break the rings?
Yes, we test the bare aluminum rings first so we can get a baseline value of the load where the aluminum ring is failing, and then from there we can subtract the failure from the composite overwrap material from the baseline so that we can know the tensile strength of the overwrap material itself.
Have you done actually any tests? Do you know how successful or how strong this overwrap is going to be?
Yes, right now the first layer of material that we're putting onto the rings fell at about close to 600 pounds of force from that small overwrap material. The overwrap material that we're testing is only about 0.36 inches wide.
Nice. So you do test on rings as well as full tanks, is that correct?
Yes, the tanks are the end goal, but for everything that we're doing right now is for the ring test to prepare for the ultimate burst test, and that's actually when the tanks will be wound with this particular type of material.
You use that word burst specifically because you really want to pressurize the tank to the point of failure, which creates a burst.
Yes, correct. Yeah.
I hope you're successful bursting the tank.
Thank you. We hope that there's not going to be a really large knockdown in properties compared to carbon fiber composites. This technology at this level is still in the premature stages. We're just trying to help do as much research as possible on these preliminary tests so that we can further advance this technology and get it to the area where carbon fiber composites are currently.
So John, Tiffany gets a lot of data from these tests. How are you using that data to prepare for the upcoming flight test?
Well, what we've done is made sure that we've interacted with Wallup's sounding rocket experts to make sure that we capture the entire flight environment and all the design requirements for our COPV and bring those into the laboratory and have Tiffany duplicate the critical environments that the material has to operate in. This gives me data that I then use to size or dimension the COPV, determine how much nanocomposite is actually applied to meet the performance and safety requirements that Wallops has for their sounding rocket flight. We consider the vibration environments and the temperatures that a COPV will see and make sure that all the forces and loads that are applied to the COPV are accounted for in our design.
How will an improved technology, this game-changing technology, help future missions?
Well, we know that the carbon nanotube is one of the most strong and stiff materials known to man. If we can get that material into an engineering application, we could probably make much lighter spaceflight hardware than what we're doing right now. By adding this small nanotube wrap, we could easily increase the strength of the tank by a factor of 2, with only increasing the weight of the tank by perhaps 10%. So that's an enormous gain in strength.
We're back to continue our discussion on the processes to wrap the pressure vessels. We just saw one. Mia, tell us about another.
Okay, so what we've done here is taken a spool of carbon nanotube yarn, and instead of processing it in a large machine, we took the critical steps that we use in a large machine and downscaled the equipment. And so what that allowed us to do is take a small amount of material, get the resin infiltrated in it, and wind either a cylinder or a bottle directly from the yarn.
So essentially what you're doing is you're sort of miniaturizing that process.
Correct. So in order for us to optimize the process using the least amount of material and also getting the process done quickly, normally when we do this type of operation, we use a machine that takes up an entire room. Okay, so we've now downsized that process into a tabletop piece of equipment.
Well, what are the benefits of miniaturizing the entire process?
So several benefits come out of that. One is we basically are tailoring the process that we're developing to the amount of material that's available. We can very quickly rapid prototype in a sense. We can try several different conditions very quickly, changing that using the least amount of material. And also it allows us to modify the machine very quickly to adapt to what we learn as we are winding this material.
When you miniaturize it, are you skipping steps? Because when you look at your device, you don't have many moving parts compared to the commercial
That's correct.
size. And so what have you done to get the same benefits?
Okay, so here are the critical steps, right? You take the yarn, which is dry, and then we need to send it through a bath so that the resin will be absorbed onto the yarn. And then after the resin is absorbed, really what we want to use that infused yarn with is to wind it around the bottle. Okay, so in a very short distance, we're able to achieve that. It's in about a couple of feet, right? We're able to see that process right away.
Now that you have the process that has been miniaturized, what is the next step?
So in order to get our article certified for flight, it needs to be made on a commercial scale. And so those steps that we have defined and optimized are now going to be transferred to a space flight center, which is used to building these types of flight articles. And those basic steps are basically now being adapted back to a commercial machine.
And then from there, that pressure vessel will be transferred to the flight facility where it will be launched on a sounding rocket in 2016.
Correct. We're going to be launching from Wallops, yes.
Now, nanotechnology began several years ago. Well, it's been around for a while, but from where you started with it, how has it evolved over the years?
When we started working with carbon nanotubes, they were still available in powder form. And because on the nanoscale they had such tremendous properties, people thought we could just essentially sprinkle some on a polymer matrix and get the benefit of these materials. We studied it for several years and realized that is not a method that we can get the type of properties that we're looking for, because we're competing with state-of-the-art structural materials, which are carbon fiber composites. So around 5 years ago, we actually switched approach and worked with a vendor so that we used predominantly continuous format of carbon nanotubes. Now, the challenge there is that in the bulk form, it does not have the kind of properties that were existing in the nanoscale. We had to basically optimize the process to take advantage of these processes and work in collaboration with the manufacturer to also optimize those properties from the starting material. So they had to modify their production process to accommodate this. And so there was interactive exchange of information so that we can both get better material properties. In a span of about 3 years, we've made significant advances that take us far from where we started, to the degree that I can say that just 2 years ago we did not have the kind of properties we have now.
And where do you see the future, or how close are you into perfecting carbon nano composites?
So
that's kind of a big question.
Perfection, yes, perfection is hard to achieve. So here's the thing. When you talk about perfection, we are comparing against a material that's been around for about 50 years, right? Although we've come a long way when we actually analyze the materials that we have now for carbon nanotubes, they're nowhere near optimal. The good news is, despite them not being optimal, they're already performing at par with some carbon fiber composites, right? There's a lot of upside to this material that we don't fully understand at this point. And so there's very large areas of research yet that we can explore to really tap the potential of this material.
Now, earlier Steve Gaddis said that they are working for a high reward from high risk. What is the reward you're looking for from carbon nanotube composites?
When we first started looking at carbon nanotubes, the reason we're looking at it is because there's high potential for this material to be a disruptive technology. And the reason is it is multiple times stronger and stiffer than carbon fiber. What we're trying to do now is we are looking to optimize it so that it is at least 2 or 3 times stronger yet than what is possible now. And the reason is there are some applications like access to space, especially if we're going to Mars, where significant reduction of mass is very important, because what you launch is hundreds of times heavier than what your actual payload is. So we're trying to reduce the mass of the payload. If we can get 2 to 3 times stronger than state-of-the-art material, it makes a mission to Mars possible. And that's why we say this is a disruptive technology.
And that is game-changing.
Yes.
You're watching NASA Edge.
An inside and outside look at all
Did you know that if you were born after 2000, during your entire life there has been someone living in space? That's thanks to the International Space Station, which celebrated its 20th anniversary of continuous human habitation in 2020. You've probably heard a lot about the incredible science that happens on board the station, but the outside is actually prime real estate for all kinds of experiments and technology development too.
The International Space Station is a great platform to demonstrate servicing technology because it provides power, data, there's robotics in space.
With Tech on Deck, we'll be talking about some key experiments that have taken place outside in the harsh environment of space, which will help us advance human exploration.
Nexus is NASA's Exploration and In-Space Services Project Division at the Goddard Space Flight Center. The goal of the division is to usher in a new era of more sustainable, affordable, and resilient spaceflight, both near the Earth, around the Moon, and deep into the solar system. Many members of the Nexus team started off with the Hubble telescope servicing missions. We've taken that technology, applied that to robotic servicing.
From robotic refueling missions that will help spacecraft live longer and journey farther to autonomous navigation systems, NASA's Exploration and In-Space Services Division has taken advantage of the wonderful opportunity station offers to test new technologies. As we look to exploring our solar system and beyond, and establishing a sustained human presence in space beyond low Earth orbit, many of these technologies will play a key role.
We use the robots on Space Station to demonstrate the technologies needed to enable satellite servicing in the future. We've also used the robots on Space Station to do some of the more repetitive tasks or the dangerous tasks that astronauts shouldn't be doing, like going outside the space station to try to look for ammonia leaks. Robots are very good at moving fine, delicate positions, moving back and forth, doing those sorts of tasks that would be challenging for humans to do.
In order to live in space, astronauts will first need to reach their far-out destinations like Mars. This will require refueling and replenishment of oxygen supplies, things the robotic refueling missions worked to demonstrate on station. They will also need to be able to construct, maintain, and repair their habitats, as well as adapt to unforeseen circumstances.
Because we're in space in low Earth orbit, we have lighting conditions that are representative of objects in space, and so allows us to launch tools and modules into orbit, put them on the space station, and then use those robotic technologies and all the infrastructure that comes with the space station to mature those technologies in a way that's much, much less expensive than if we try to launch our own satellite and demonstrate those for the first time, not using the space station.
For these endeavors, Nexus's work with astronaut tools, satellite servicing, and on-orbit assembly and manufacturing will do the trick.
We develop the technologies that are needed to advance exploration in ways you can service satellites in the future, build satellites and build structures on orbit, refuel satellites on the way to other planets, repair those satellites much like we do on that side of space station. Both humans and robots are used to maintain habitats in space. We're developing technologies that can be used by NASA and others to make those a reality.
The International Space Station is the perfect testing ground for technologies that will be used to propel humans farther than we've ever gone before. The station is helping us build the necessary foundation to make it possible. Outside of the International Space Station, space can be a lonely place. Most satellites are designed to live their lives alone, and we've yet to find life outside of Earth. This means that when we launch a spacecraft or satellite, for the most part it's on its own, and has a limited lifespan based on when critical items like fuel run out or something breaks. You wouldn't throw away your car if it ran out of gas, and thanks to the advent of modern-day robotics, software, and computing power, we will soon be able to apply that logic to satellites. We are on the cusp of breaking the one-and-done paradigm that exists for most satellites. An important step in that direction is NASA's Robotic Refueling Mission, or RRM, demonstration on the International Space Station. Because refueling a satellite that was not designed to be refueled has never been done before, practice is key. With that in mind, the first two phases of RRM took place on station from 2011 to 2017 and tested the tools, technologies, and techniques to refuel and repair satellites in orbit.
RM and RM Phase 2 were designed to demonstrate end-to-end refueling of a spacecraft, as well as the first steps of cryogenic refueling or replenishment. We wanted to use the robot on the International Space Station to be able to demonstrate the technologies and techniques to do this refueling, so we built innovative tools to bridge the gap between the robot and the payload interfaces.
Consisting of a module or box affixed to the outside of station and robotic tools, the demonstrations use station's Dexter robot to operate tools and test servicing tasks such as cutting and peeling back protective thermal blankets, unscrewing caps, turning valves, transferring fluid, inspection, and intermediary steps leading up to refueling.
Once we were all done, we were able to transfer fuel end-to-end through a spacecraft fill and drain valve that wasn't designed to be robotically refueled.
The RRM demonstration helped test and prove technologies that will make refueling satellites not designed to be refueled possible, something that will be further demonstrated by NASA's On-Orbit Servicing, Assembly, and Manufacturing 1 mission. But it also helped to lay the groundwork for designing future satellites in a way to make them more easily serviceable.
These missions were important because we needed to demonstrate in orbit that this technology was ready. There were a lot of people that felt that at the time of RRM that the technology was so far in the future that they didn't feel what we were talking about was possible. So we needed to demonstrate in orbit this technology so that we could start changing the paradigm and incorporate these technologies into the future spacecraft designs and missions.
RRM Phase 1 and 2 were all about preparing an interface for refueling, which in many ways is half the battle. To robotically refuel a satellite, you need to perform a series of highly dexterous tasks to even access the valve. The next step is to actually perform refueling tasks, which is what the next phase, RRM3, has been demonstrating on station over a series of operations since 2018. RRM is a critical piece of the sustainable spaceflight puzzle that helps us with the ability to robotically refuel, repair, and maintain satellites in both near and distant orbits, well beyond the reach of where humans can go today. For generations, Mars has beckoned. Now, the red planet is within our reach. But how do we get there? The key is in the details, and in the technology. First and foremost, you need fuel. This is not only true for getting to Mars, but for any form of deep space exploration. Being able to replenish fuel on a long-duration journey means massive amounts aren't needed up front, freeing up space for other important things. Enter Robotic Refueling Mission 3, or RRM3 for short. This demonstration launched to the International Space Station in December of 2018 and has helped us develop tools and techniques needed to replenish cryogenic fluid in space. Transferring cryogenic fluids has never been done before in space. These super cold fluids can be used as propellants, coolants, or for life support systems. Being able to replenish these fluids that run out, otherwise known as consumables, is an important part of the sustainable exploration roadmap. Not just for Mars, but for NASA's Artemis program, which will land the first woman and the next man on the moon. Since refueling cryogenic fluids in space has never been done before, RRM3 tested the technologies and techniques needed to make that possible. First, we sent the RRM3 payload and its 3 main tools to Space Station, where astronauts assembled the parts.
When I was living aboard the International Space Station in the spring of 2019, I was fortunate enough to take part in the very small part in the Robotic Refueling Mission 3. And my job was to unload the components of the actual RRM3 from one of our visiting vehicles, and we take it into our Japanese experimental module, the GEM, where we have an airlock. And right inside of the airlock, we unpacked all of the boxes, much like you would a piece of furniture that you had to assemble yourself at home. So unpacked all of the pieces, we did a checkout. We worked with the ground, we got everything assembled, and then we placed it into the Japanese airlock. And from there, we were able to put it outside of the International Space Station. So my involvement in RRM3 was the physical final assembly of the actual components.
RM-3 was delivered to the space station by a SpaceX Dragon on the company's 16th Commercial Resupply Services mission and installed on the outside of station by the Canadian robot Dexter. Dexter then picked up the tools from the JEM airlock and installed them onto the RM-3 payload. The ground operations team was now ready to begin operating the 3 tools to test how they would work in space. For the first set of operations, conducted in August 2019, Dexter used one of the RM-3 tools to prepare the RM-3 module's interface for transferring cryogenic fuel. The second set of operations was then conducted in October 2020. For these, Dexter used one of the remaining 2 tools to insert an 11-foot-long hose in an open port and the other snake-like camera inspection tools simultaneously to verify the hose's position in the inside of RM-3's tubing. This marked the first time that Dexter had tools in both arms working the same tasks simultaneously. The RM-3 demonstration added experience and information to NASA's knowledge base on the storage and transferring cryogenic fluids in space. It is currently still on station where it will conduct one final set of operations in mid-2022. For getting to the Moon, Mars, and beyond, cryogenic fluids will be used as propellants and to maintain life support systems for astronauts. The Mars atmosphere is made up of carbon dioxide, which could be converted to liquid oxygen, a type of cryogenic fluid that can be used both as propellant and for breathing. Astronauts may be able to fuel rockets or replenish their oxygen supplies using compounds found in the Martian atmosphere. A tool on the Mars Perseverance rover called Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, is set to demonstrate the first ever conversion of Martian carbon dioxide to oxygen, which is another important piece of the puzzle. In order to make a sustained human presence in space a reality, humans and robots will have to work together using technologies like those developed by RM-3 and MOXIE.
A lot of people ask about, whose job is exploring outer space? Is it robots or is it humans? And I believe that it requires teamwork between robots and humans, and that our exploration is not complete or even possible without both. So robots can go farther, they're less expensive, and they can go for longer periods of time. They don't require as much maintenance. You don't have to feed and care for a robot, much like you do if you send me back to space. So like the Mars rovers, the Galileo that explored Jupiter and its moons, the Hubble and the soon-to-be James Webb Space Telescope, they are doing missions in locations that humans to this point don't have the capability to go. There's also something very important about humans wanting to know what it's like to be there. It's not enough for humans to take a picture of Mount Everest or Antarctica and say, oh, okay, that's what it looks like. The human condition is we are born to explore. We're born to say, what if? What's just beyond what we know? And what is it like to be there? And so the human side of space exploration, first of all, it's orders of magnitude closer to Earth. We have not been able to send humans nearly as far as we've been able to send robotic probes. But they're 2 very different missions, and they serve a different type of curiosity.
Mars and deep space are calling human explorers, and RM-3 is a step toward helping NASA answer that call. Though it sounds complex, the idea is simple. Having the ability to refuel will allow NASA to embark on longer journeys to explore the depths of our solar system. Did you know there's a 3-eyed raven currently perched on the International Space Station? Not an actual bird, but rather a technology payload that is helping NASA develop a relative navigation system, or autopilot, for spacecraft. Launched to station in 2017 aboard a SpaceX Dragon on the company's 10th Commercial Resupply Services mission for NASA, and installed on the outside of ISS by station's Dexter robot, Raven is equipped with 3 distinct camera vision systems: visible, infrared, and LiDAR. Combined with NASA-developed software algorithms, this rotating module of technology keeps a weather eye on arriving spacecraft. Raven's head, containing its 3 eyes, or cameras, is always on the swivel, which is made possible by its integral gimbal.
Raven is an on-orbit test bed that was built to mature technologies related to relative navigation sensors and algorithms. Raven was launched to the International Space Station aboard a SpaceX Dragon capsule in February 2017. And it's been operational on the space station since that time. So using 3 different sensors on Raven that are on a movable gimbal platform, Raven can track the incoming visiting vehicle to station all the way from very, very far away, all the way up to where they dock with the space station. So basically, at any given time, Raven can tell you where the incoming visiting vehicle is in space relative to the space station and what attitude or pointing direction it is.
Raven sends the data it collects from tracking and observing incoming spacecraft to its processor or brain, called SpaceCube. This information then tells Raven how it needs to move to continue to track the spacecraft and gauge relative distance and positioning. NASA engineers have taken what they've learned from multiple Raven observations over the years to adjust and fine-tune the relative navigation system as needed, so it's ready for the upcoming on-orbit servicing, assembly, and manufacturing 1 mission, which will robotically refuel a satellite, among other things.
Raven is a sensor system that can image an object, process those images on board in real time with advanced algorithms, and calculate the pose of the object relative to itself.
These factors come together to create something like spacecraft autopilot. Much like a self-driving car can maintain cruise control based on the speed of the vehicle it follows, 2 free-flying spacecraft will be able to dock with one another using this technology. Though this operation is similar to the autonomous docking of visiting spacecraft to station, Raven's unique application is necessary for docking 2 satellites with the challenges of each moving and rotating in every direction during the rendezvous and docking phase.
Using that information to then guide the first spacecraft to autonomously rendezvous with and dock with the second spacecraft. So that means finding it in space, aligning with it appropriately, and then bringing the 2 vehicles together without smashing them into and destroying each of them, all without human intervention.
This capability is the kind of thing you need for docking with spacecraft that were not originally designed to be docked with and serviced, which happens to be a vast majority of them. That's why Raven's time on station is critical for the future of on-orbit servicing, assembly, and manufacturing, or OSAM. The OSAM-1 mission will use Raven's relative navigation capability to autonomously, meaning no humans involved, rendezvous and dock with the satellite, and then telerobotically refuel it. This will be the first time in history a spacecraft not originally designed to be serviced will be refueled as a means to extend its operational life. Raven is also important for future exploration missions.
Raven's technologies can be applied to future NASA missions because if humans want to make a footprint in the solar system beyond low Earth orbit, which is where the International Space Station is located, we're going to have to rely on some form of autonomous docking technologies in the future. Whether it be an unmanned cargo vehicle meeting up in orbit around the moon, refueling tankers located in geosynchronous Earth orbit, or a return vehicle arriving on Mars in advance of a crewed landing, all of these feats will require the technology we're developing with Raven.
Using its 3 eyes, Raven is looking to the moon, Mars, and beyond.
Relying on highly robust autonomous systems becomes more crucial the further you move away from Earth as the communications time increases drastically. Once you move past low Earth orbit, it becomes very impossible for humans on Earth to do these highly complex maneuvers in real time. It's more efficient to allow computers to perform these sequences autonomously without human intervention.
Although Raven has successfully concluded its main mission objectives, it remains on station. Meanwhile, its team on the ground is using what they've learned to develop more never-before-seen technologies that will enable future space exploration.
Before I started digging in that other bag, here you go. No problem.
If you need to fix something in space that wasn't designed to be fixed, it's going to take all the experience you can get. With that in mind, when the International Space Station's Alpha Magnetic Spectrometer, or AMS, needed repairs, NASA's Johnson Space Center and Goddard Space Flight Center used their joint expertise to make it happen. At Goddard, that expertise resides in NASA's Exploration and In-Space Services Division, or NEXUS, which evolved from the office that was responsible for the Hubble Space Telescope servicing missions. Key to these missions was the development of specialized tools. While you've probably heard of Hubble, you may not be as familiar with AMS, so let's start there. Designed for a 3-year mission of sifting through cosmic ray particles, AMS has been looking for signs of dark matter from its position on station since 2011. Hundreds of researchers have used the data collected to investigate the source of the mysterious substance to help us better understand the origins of the universe. To continue this important data collection, AMS needed an upgrade due to general wear and tear from the harsh environment of space, specifically a new cooling system. A repair could extend its life beyond what was originally planned. Sounds easy enough, right? In fact, due to the instrument's complexity and the fact that it was not designed to be repaired, even gaining access to the system to replace it was difficult. AMS's design did not incorporate the kinds of interfaces that make spacewalks easier, or have the ability to be serviced with traditional multi-purpose tools. And so, over the course of 4 years, NASA got to work designing and developing some of the most complex spacewalks since the Hubble servicing missions in the 90s and early 2000s to fix AMS.
The AMS tools themselves were unique. They were built specifically for this task, a task that was never intended to be performed on a spacewalk. And so that required a lot of thinking about how we were going to get inside so that we could access the tubes that we needed to cut into and then install the new thermal control system, but also how to put handling aids on it so that we had a place to attach our tethers, to attach our foot restraints, to have handholds, have a place to attach equipment that we needed out there.
NASA developed 20 specialized tools to make the job possible, and on November 15, 2019, astronauts Andrew Morgan and Luca Parmitano got to work. On this first spacewalk, astronauts needed to get access. By design, 5 of the tools could be seen floating off into space, attached to the debris shield that was removed to give the astronauts access to the heart of AMS.
The debris shield handling aid was one of the first tools that Luca installed on the EVA, and this gave us a handhold to install on the debris shield to work from, but also a handle for me to hold on to ultimately when we jettisoned it overboard to the aft side of the ISS, which was a lot of fun to do.
The astronauts continued with 3 more spacewalks over the next 2 months, using all of the specially designed tools. One such tool was the tube cutting guide, which was a direct result of multiple practice sessions at Johnson Space Center facilities like the Neutral Buoyancy Lab. While practicing, astronauts communicated the need for a way to identify and verify the correct tubes to cut, since they all look the same to the astronauts' eyes within the spacesuit.
After we had removed the debris shield and the VSB cover, now we have the tubes exposed, and we actually had to cut into those tubes in order to pull out the correct ones to connect with the new thermal control system, the new pump. In order to do that, we had to be very sure of the tubes that we were cutting. These ingenious tube cutting guides installed over the top of the tubes and made sure that we knew and we were communicating correctly with the ground team to make sure that we were cutting the correct tube at the right time.
In January 2020, Luca Parmitano and Drew Morgan completed the 4th and final spacewalk to repair AMS. Because of their work and the ingenuity of tool designers and engineers, the instrument is now back in commission and able to continue to collect data about the origins of our universe for years to come.
People from Goddard and JC spend a lot of time developing these tools with their knowledge and the support of astronauts like Chris Cassidy. And we are very thankful that we were privileged to use those tools and to put them to very successful use. Thank you very much.
It is great to be back at America's Space Coast, at this historic place with the men and women of the John F. Kennedy Space Center. And it's here today in the 21st century that the modern marvels that launched from these grounds prove that the public and private sectors are achieving far more together than we ever have apart. American businesses are developing new rockets, spaceships, satellites that are taking us further into space than ever before, and renewing our confidence that we can and will achieve the impossible once again. This truth echoes through the history of the Kennedy Space Center. Named for a president who challenged the American people to marshal the best of our, in his words, energies and skills to become the world's leading spacefaring nation. I know America will once again astonish the world with the heights we reach and the wonders we achieve. And as these feats of American enterprise and ingenuity attest, much more than the bridge to space, Kennedy Space Center is the bridge to the future.
The reason that you would do any kind of experiment in space is if there's something particular about the space environment, and most often that is microgravity. So mostly the ISS gives us the ability to either do something that we can't do in a facility on Earth or investigate some phenomenon, some property in a way that we can't on Earth. So for example, some of the tissue architecture, these really delicate tissues, as you start to build them up, they would collapse because you have gravity, or the cells would naturally settle to the bottom of the plate. And so you just can't study the answer to the question that you're looking for. So the space station lets us have that ability to either test what the effect of gravity is or remove that problem entirely from our experimental setup. Yeah, the space station's an incredible place to conduct research. It was sort of like being in the world's most amazing lab when I was up there in 2016. So when you're a scientist, you're used to working on one thing over and over and maybe really refining the details on that over the course of a PhD thesis or a lab project. On space station, you get somebody's incredibly refined project times 200 different fields. So for me, it was a chance to learn about all of these different areas of science, and they each have a team behind them. So I was usually pretty excited to open the container and do whatever experiment that day brought. I also really got a chance to talk to those PIs, the principal investigators, and those scientific teams, and understand everything that was going on behind their experiments and read their papers. So by the time I got to doing the experiment, I was pretty excited to take it out and to see what was going to change in microgravity. Yeah, science in space, it's an amazing lab and it's incredibly fun. So we are smiling all the time. I'm Kate Rubens. I'm a scientist and an astronaut.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.
We have been given the scientific knowledge, the technical ability, and the material to pursue the exploration of the universe.
of the great powers of the International Space Station is its duration. The ability to do an experiment, take that knowledge, design a new experiment, follow on with that knowledge, and then do the next generation after that.
NASA's been launching vehicles for decades, and each one of those vehicles has an experiment on them. But never before have we had a laboratory totally dedicated to these kind of experiments.
One of the things that's most promising is that the scientific value and the economic value that will come from the space station research is just starting to show up.
The developments that we're making now are really setting the stage for this commercial market in space. The efforts that have led up to this through the performance of all of these research investigations that we've already had on board, doing foundational research and testing out new technologies and methods, feed this market and feed the capability of doing future research in space and also in having new commercial entities operate in that space.
We put together the ISS Benefits for Humanity book to really compile the stories that we knew of the amazing things that had been accomplished. The challenge with science is that it takes time. So even a new discovery that is clearly relevant to treating a medical condition could take decades for that treatment to actually come to market. And so we wanted to capture the state of those different new discoveries and how they were proceeding into benefits for humanity. But we also wanted to tell the stories of the people whose lives had already been changed.
We've put in specialized sections to both economic value and scientific value in order to try and demonstrate to folks what sort of value space station research has.
The scientific valuation section, we were interested in just saying, hey, we have all these publications, these scientific publications that come from ISS. What should we do with them? How should we communicate why they're important? Yeah, we've got thousands of publications, but what does it mean? And how has it advanced science as a whole for Earth and also for spaceflight? So what was shocking to me is, wow, look at all the publications that have come from space station research, and other people in non-space disciplines are finding those publications and using them in their own research. And where you can integrate space research into everyday research on Earth, you know you're having the most impact on science.
One thing we're adding is a lot more information about commercial development in low Earth orbit that is leveraging the space station.
The space economy today is still emerging, but its valuation has doubled in the last 10 years, and there are more active participants in low Earth orbit than there have ever been. The International Space Station has contributed to the commercialization in a couple of different ways. First, with commercial resupply, encouraging companies to develop their own capabilities, and then those capabilities can be used not just by the International Space Station. In terms of research, there are 12 commercial facilities that are operating right now, and they've greatly expanded the kinds of research that can be accomplished on ISS, and they're really bringing both new customers into the space market, but also they are allowing new entities to form that are learning the processes by which you conduct business in space.
Commercialization is key to the further exploration mission that NASA has. We intend to use space station to help commercial entities enter the market in low Earth orbit. And we also expect them to be able to provide goods and services that someday will help us in our exploration mission beyond low Earth orbit.
Scientists tend to ask, what's the next question? So the next question for space station is, what are we going to do next with this platform?
This is the golden age of research. We will likely never see such a strong microgravity science program in the future. We will have lots of human exploration, but to have a sustained laboratory in the way that we have now's the time.
This research is feeding our exploration goals beyond low Earth orbit and developing the companies that hope to make low Earth orbit part of their business plans. These two goals go hand in hand, and the International Space Station is the way to get there.
We really want to tell the stories of people and products and economic development, all of those things that are making the world a better place through our international cooperation on the space station.
Most of the children, they come here with waterborne disease.
So many children under 5 suffer from diarrhea.
They're complaining about the abdominal pain, skin rashes.
They get waterborne illness through drinking water.
Most of the community members had little knowledge regarding the use of safe water and what safe water is.
Because most of the water we use it without knowing it is affected with disease or not.
So we need to test them so that we make sure that the water is safe or not safe.
A lot of people have the idea that water quality is too hard to do in the field and it's too complicated.
Having to transport samples, having to have reliable electricity, having to heat samples or keep samples at certain temperatures or put them in refrigerators.
But probably the biggest challenge is actually the cost.
The price was really high, up to $300 a test.
So all those things come together to make it really difficult to use a traditional laboratory approach when you're testing water. What's been missing is the really simple, cheap test kit, and that solution came from above. On the space station, we recycle almost all of the water that the astronauts drink, and that constitutes a risk because if that water became contaminated, the astronauts would have to abandon the space station in the worst case scenario. What we needed on the space station was something that was small, easy to transport, and didn't require a lot of training for the astronauts. We developed a water test kit that was really easy to use and used off-the-shelf components, and we called that the Microbial Water Analysis Kit, or MWAC. It's basically a bag that changes color in it, and the astronauts just had to hook it up to the water system, take the sample, store it overnight, and read it the next day. It worked great, and it's still in use today. This was when we realized we had a chance to make a difference in the world using the same technology that was used by NASA, but applied in a remote area of a developing country.
We started MWater for the biggest health crisis on the planet, which is a lack of safe water. The test kit is revolutionary because of its cost. It lowers the cost of testing water points from hundreds of dollars to about $5 to $7. It can be done on site in the remote region, and it can give you a result within 24 hours.
I take a sample today, tomorrow I have results. To use a MWater kit is very easy.
But we learned that testing water by itself wasn't enough. With the mobile app, people could map water sources and record the data.
So that way we're building sort of a global database of water information that everybody can contribute to and share with others.
So what that meant was people who before didn't have a feasible and affordable way to test water suddenly had the means to know which water sources around them were safe.
It's made people much more aware of the issues of water quality. That's a very powerful thing.
And that's all due to technology that we've borrowed from the International Space Station. So now we're able to assemble a really low-cost water quality test kit to ship all over the world.
We've been working with the local health ministry and the water utility in Mwanza, Tanzania since 2013.
Through that technology, most of the citizens in Mwanza have an increased awareness regarding the kind of water they use and whether it causes them any waterborne illnesses or not.
People are now treating their water and avoiding sources of water which could be contaminated. I've seen a growing awareness.
It is very unusual for technology that is used in international space stations to be used in developing countries like Tanzania, but it can be used, and it should be used because this technology is not limited to only developed countries, but for all humankind.
The International Space Station is the most unique laboratory that exists. There are things that you can learn, things that you can do in space that you just can't do on the Earth.
Space Station really provides an opportunity to explore, for example, say medical applications.
The aging and the osteoporosis and muscle wasting conditions are greatly accelerated in microgravity.
Understanding those phenomena allow us to look at how we can improve treatment of disease here on Earth.
What we have is the capability to affect people's quality of life.
But it's not just drug companies that can benefit from experiments or research in space, but it's a host of industries across the board.
But it wasn't always easy to get there.
Historically, access to space was limited to companies and corporations, which were selected by the government, and what we lost was the true creativity of so many innovative smaller companies that really didn't understand how to get to space.
When we were doing the reauthorization of NASA, we wanted to expand the opportunities to different areas of experimentation and also different entities.
Recognizing the untapped potential for commercial access to space, in 2005, Congress declared the U.S. portion of the International Space Station a national laboratory.
Essentially, it opened up opportunities for research that could be done on the space station that would benefit us here on Earth.
Everyday companies and everyday researchers and everyday people can think about using the space station. That's a fundamental change that was never allowed before.
Today, we offer opportunities to the researcher that never existed before.
Whether it be seed funding to help support the actual project,
To access to experts to create hardware,
that rocket ride up, the on-station time with the astronaut as your lab technician, what we're doing is really making it as easy as possible for people here on Earth to do space-based research without becoming space experts.
our part of the mission is to help guide these non-traditional innovative users from their traditional labs here on the ground to a very unusual and important asset in space. The ISS National Lab has space versions of hardware that you can often find in laboratories here on the ground.
Everything from even animal habitats,
plant growth chambers,
freezers,
3D printers,
Earth observation windows,
incubators,
furnaces,
to centrifuges,
microscopes.
The list goes on and on. So we're working with companies that you would never imagine, and they would never have imagined using the International Space Station, and they're seeing great results from that.
And the International Space Station offers researchers like me an opportunity to find the key variables.
It's helping us to pinpoint therapeutic molecules.
The space station really provides us a unique opportunity, a unique environment to do some basic and fundamental research that allows us to develop products better.
The ISS allows us to do a series of experiments in weightlessness that will have profound impacts for life on Earth.
Having a U.S. national lab in space has allowed for the formation of a wide range of companies. It's creating a new economy, a sustainable marketplace that has services, commercial products, competition. There's no limit to what we can be doing in a few years.
One of the great powers of the International Space Station is its duration. The ability to do an experiment, take that knowledge, design a new experiment, follow on with that knowledge, and then do the next generation after that.
NASA's been launching vehicles for decades, and each one of those vehicles has an experiment on them. But never before have we had a laboratory totally dedicated to these kind of experiments.
One of the things that's most promising is that the scientific value and the economic value that will come from the space station research is just starting to show up.
The developments that we're making now are really setting the stage for this commercial market in space. The efforts that have led up to this through the performance of all of these research investigations that we've already had on board, doing foundational research and testing out new technologies and methods, feed this market and feed the capability of doing future research in space and also in having new commercial entities operate in that space.
We put together the ISS Benefits for Humanity book to really compile the stories that we knew of the amazing things that had been accomplished. The challenge with science is that it takes time. So even a new discovery that is clearly relevant to treating a medical condition could take decades for that treatment to actually come to market. And so we wanted to capture the state of those different new discoveries and how they were proceeding into benefits for humanity. But we also wanted to tell the stories of the people whose lives had already been changed.
We've put in specialized sections to both economic value and scientific value in order to try and demonstrate to folks what sort of value space station research has.
The scientific valuation section, we were interested in just saying, hey, we have all these publications, these scientific publications that come from ISS. What should we do with them? How should we communicate why they're important? Yeah, we've got thousands of publications, but what does it mean? And how has it advanced science as a whole for Earth and also for spaceflight? So what was shocking to me is, wow, look at all the publications that have come from space station research, and other people in non-space disciplines are finding those publications and using them in their own research. And where you can integrate space research into everyday research on Earth, you know you're having the most impact on science.
One thing we're adding is a lot more information about commercial development in low Earth orbit that is leveraging the space station.
The space economy today is still emerging, but its valuation has doubled in the last 10 years, and there are more active participants in low Earth orbit than there have ever been. The International Space Station has contributed to the commercialization in a couple of different ways. First, with commercial resupply, encouraging companies to develop their own capabilities, and then those capabilities can be used not just by the International Space Station. In terms of research, there are 12 commercial facilities that are operating right now, and they've greatly expanded the kinds of research that can be accomplished on ISS, and they're really bringing both new customers into the space market, but also they are allowing new entities to form that are learning the processes by which you conduct business in space.
Commercialization is key to the further exploration mission that NASA has. We intend to use space station to help commercial entities enter the market in low Earth orbit. And we also expect them to be able to provide goods and services that someday will help us in our exploration mission beyond low Earth orbit.
Scientists tend to ask, what's the next question? So the next question for space station is, what are we going to do next with this platform?
This is the golden age of research. We will likely never see such a strong microgravity science program in the future. We will have lots of human exploration, but to have a sustained laboratory in the way that we have now's the time.
This research is feeding our exploration goals beyond low Earth orbit and developing the companies that hope to make low Earth orbit part of their business plans. These two goals go hand in hand, and the International Space Station is the way to get there.
We really want to tell the stories of people and products and economic development, all of those things that are making the world a better place through our international cooperation on the space station.
In 1988, Dr. James Hansen, then director of NASA's Goddard Institute for Space Studies, stood before the U.S. Senate and testified that
global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. This last year, 2021, comes in as the 6th warmest year on record, and it continues this large, long-term warming that Jim Hansen was detecting even in 1988. And in 1988, that was also a globally warmest year, but now that ranks only 28th in the ranking. And so the warming that we've had since Jim Hansen's testimony has been dramatic and totally vindicates the concern and the warnings that he put out at that time.
the Goddard Institute for Space Studies, or GISS for short, maintains NASA's record of Earth's surface temperature, called GISS temp, that shows a clear and unequivocal increase in our planet's temperature. GISS temp stretches from 1880, long before NASA existed, until the present day. Now, when you think of NASA, you probably think of, well, space, right? And we do lots of work studying Earth from above. But the GISS temp record is actually built from the ground up. We collect measurements taken from weather stations, Antarctic research stations, and ships and ocean buoys all around the planet to understand what temperature changes look like globally. And why does the record start in 1880? That's the earliest period that we have sufficiently reliable measurements from ships and weather stations in enough places to be confident in the global record. Interestingly, it's also shortly after the time we call the Industrial Revolution, when humans started putting significant amounts of carbon dioxide in the atmosphere. But we'll get back to that later.
There are millions of measurements over the last 140 odd years. We put those together. We're using data from literally tens of thousands of different stations around the world. We use the information that's there to create a global picture of what's happening, and that gives us a very accurate estimate of how any year ranks, or what the anomaly is for any one year compared to what happened in the 19th century or what happened in the middle of the 20th century.
So we have our statistical reconstruction of Earth's recent climate, but in research science, we like to check our work. There are a couple ways we can do this. First of all, teamwork. Our colleagues at NOAA and at other agencies and universities around the world also create their own records, and we can line them up side by side and see just how closely they align. Everyone's independent climate records show the same thing. Earth is warming significantly and rapidly. And here at NASA, we have an even cooler way to check our work: space. Right now, we have more than 24 satellites dedicated just to studying our planet. Satellites can take measurements of the entire planet and line them up with our estimate of global temperature change. And sure enough, they also match. Our measurements from space match up well with what our analysis tells us. Earth's climate is warming. The next big question: why is our planet warming? Well, let's jump back to the Industrial Revolution. The release of carbon, mostly carbon dioxide, from human activities like driving cars, flying planes, and industrial burning of fossil fuels is responsible for the majority of climate change. Carbon exists in stores underground as oil, gas, and coal. When we burn it, we release it into our atmosphere, where it traps excess heat coming from the sun, raising the temperature. We've known for more than a century that carbon dioxide added to our atmosphere traps additional heat and is a major contributor to the greenhouse effect. So we can also track the concentration of carbon dioxide in our atmosphere, the primary cause of the current climate change. Both from space, using NASA satellites like the orbiting Carbon Observatories 2 and 3, and from the ground. If you've heard of the Keeling curve, you're familiar with one of these records. Researchers have been taking daily measurements of atmospheric carbon dioxide from Mauna Loa, Hawaii since the 1950s. From space and the ground, the signal is clear. There's a lot more carbon in the atmosphere than there used to be. Other things have changed too. We've chopped down tropical forests, caused the ozone hole, and filled the air with soot, smog, and other kinds of air pollution. And this is on top of natural variations caused by the dynamics of the ocean, or volcanoes, or variations in the sun's activity. And so we can ask whether it's human activities warming our planet. At NASA, we have some big and powerful computers, able to make 6.8 trillion calculations per second. We put these huge supercomputers to work to recreate Earth's climate. So we have thousands of ideas of what could naturally cause climate change. We have 4 billion years of history where nearly anything and everything you could imagine has impacted Earth's climate. But each of these events has their own distinct fingerprint, which we can identify, a pattern of behavior with natural variability. Using supercomputers, we can run simulations of natural climate drivers, solar energy changes, wobbles in Earth's orbits, ocean turnover, volcanic eruptions, and we can run simulations of human effects. And what we've seen is...
it's us. There's no way around it. Looking at the evidence, we're the force that's enacting these changes. I am so proud of our ability to understand the climate, but I'm terrified of what we found.
But it's not just the causes of climate change, it's also the effects. Because it's not just about knowing why our planet is warming. It's also about understanding and preparing for the effects of added warmth.
Measurement of global average temperatures is so important because it's one of the most direct indicators of Earth's changing climate. But the Earth is really a system of environmental systems: land, ocean, atmosphere, and ice, and changes in one system impact the others. Our oceans are our first line of defense in climate change because they absorb so much of the extra trapped energy in the Earth system.
We are seeing the impacts of climate change now. Now we know that as our climate warms, wet areas are getting wetter and dry areas are getting drier. For example, we see more intense snowstorms. We see slower hurricanes that are causing more precipitation that inundate land. And we have more extreme precipitation in the form of atmospheric rivers that come from the Pacific and reach our west coast.
The oceans are absorbing a large amount of heat because of climate change. And once that heat is in the ocean, it actually travels all around the planet because of the ocean currents. And that has impacts on local weather and long-term climate.
As the planet warms, it's not just the ocean that's warming, it's also the ice that sits in the ocean and on land. The ice on land being warmed increases melting, which is increasing freshwater input into the polar oceans and causing sea levels to rise across the globe.
So as the climate is changing, we really are seeing a lot of changes to the environment up in the Arctic. We're seeing more permafrost thaw when it's warmer up there. The warmer air temperature can lead to warmer ground temperature, and we get that thawing of that permafrost layer.
We're finding that the fire season is being exacerbated by longer periods of drought and decreased snowfall.
Knowing that our climate is changing due to human activities means that we know how to lessen the effects of future warming. And knowing how we know what causes climate change confirms that our efforts would be meaningful. The situation is serious, but it's not hopeless. Together, we can decide to make a better choice.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, and I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it, over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term warm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's still it's got better legs today than it did then.
NASA researchers spend weeks, even months at a time in remote locations around the world, collecting critical data about Earth's environment. Many studies are done from the air, using NASA's fleet of research aircraft. One such mission is Operation Icebridge, a multi-year study of polar ice conducted by the NASA Airborne Science Program. Icebridge sends NASA's P-3 flying laboratory to Greenland and Alaska in the spring to study changing ice conditions in the Arctic. A second aircraft, the NASA DC-8, flies from Punta Arenas in southern Chile in the fall to measure land and sea ice over Antarctica. It takes months of planning to execute a major international mission like Icebridge. Diplomatic clearances, configuring the aircraft with scientific instruments, and finding facilities that can support the people and the airplane itself are just some of the preparations needed for Icebridge to meet its mission requirements and goals.
To deploy to someplace like Chile, we plan a good 6 months before the mission to bring everything together so that once you arrive here, we're ready to execute missions on a daily basis.
Typically a mission director, a mission manager, program manager, we get called different names. We'll do the site surveys for the location, liaisoning with the government, of the host government to the host airport. That's the real legwork that's done prior, is coming out and making sure that they can house and feed us and take care of the people in the hotels. You name it. There's a lot of little tiny details that can't be overstated.
The biggest logistical challenge for the project as a whole is to set up all of the lab space and the facilities so that the scientists can process their data and make their decisions about which project.
Logistics is huge for something like this because we have to make sure we can all support the people in the field as well as the aircraft. So we think a lot about aircraft spares and then little details about the support equipment for the airplane.
Usually on every deployment we're going somewhere, there's at least a group that goes out and scopes it out. A lot of it's done like while we're working other missions. And they will talk with the airfield, set up and tell them what we're going to be doing. And then as they're communicating back with us with what capabilities the airfield has to support us, that way we know what to ship.
For a deployment more than 6,000 miles away in the southern hemisphere, the maintenance crew needs to carry an extensive payload to maintain the DC-8 on site and keep the mission on schedule.
Yeah, we put them right on the side there. Yeah,
More than 13,000 pounds of cargo are packed on the DC-8. Everything from spare tires, parts, and tools to basic comforts of home for the near daily 11-hour research flights over Antarctica.
On a deployment like this, we bring the equipment with us, and we also ship a lot of other things by sea in a big container so that we can keep the airplane moving. It'll come back from a mission. If there's anything wrong that needs to be repaired before the next flight, we have the maintenance crew to support it during the night and get it ready for a mission the following day.
The DC-8 flight operations team works around the clock to support Operation Icebridge, providing ground support for takeoffs and landings, operating the plane on research flights, and making sure sensitive science instruments stay powered up and heated overnight. The airfield is staffed 24 hours a day.
We have a makeup of about 28 people supporting the flight operations down here, and that consists of the pilots, flight engineers, navigators, mission directors, and then the maintenance crew that's split between mechanics and avionics technicians.
The maintenance team often works on tight deadlines to prepare the aircraft for its next deployment. Just 10 days after removing one set of science instruments from a previous mission, the DC-8 is reconfigured for Icebridge. In 3 weeks' time, the plane is transformed into a working science laboratory with a suite of radar and laser instruments and cameras installed throughout the cabin, cargo pit, and fuselage.
Yeah, the unique thing about the DC-8 is that it was modified to accept, at this point, we've got about 100 different instruments that have been integrated into this airframe. And so part of the modifications that were done early on was to make the airplane as versatile as possible. So if you were to look through the airframe, you'd see cutouts in both the bottom of the aircraft and the upper side of the aircraft. And a number of the windows were modified to carry structural loads of instruments being installed as well. So we can look in pretty much every direction there is outside this airplane as we're traveling through the sky.
Once the science instruments are installed, the flight operations team conducts a series of ground checks and instrument test flights over the California desert to make sure the DC-8 is mission ready.
Looks like maybe it's level now. Right, looks like it's a wings level and rock course.
So the reason why we picked these sites over the desert in California is because they have these dry lake beds there. And they are a very flat area that's ideally suited for our purpose. So we can put a GPS receiver on a car and kind of drive around on these flat lake beds, measure them, and then a few days later fly over the same area with the DC-8 and take a measurement from the air, compare the two measurements and use the data from the ground to calibrate and validate the airborne measurements.
While the aircraft is prepared for the trip to Chile, the science and flight operations teams are required to undergo specialized safety training, regardless of if they've flown on the DC-8 in the past.
Well, for the DC-8, everybody who flies has to go through basically a safety briefing. We go in a little bit more detail because we do more things on our airplanes than commercial airliners do. From our pilots, they go through survival training, water and land, and depending on where they're going, some of them have been through Arctic. All of our crew members, they all have to go to altitude chamber, water survival, land survival, and what we do here is we just build on that and then try and bring anybody else that hasn't had any formal training up to speed so they have at least a working knowledge of the kind of conditions that can happen if something was to go wrong with the aircraft.
Safety equipment tailored for Icebridge is also packed on the DC-8.
Overhead compartments, we've got 20-man life rafts. There's 4 of those on board the aircraft. We have 2 what we call global survival kits, which has different survival items inside of there. For this particular deployment, we also have anti-exposure suits, which if they were going to the water, we have enough for everybody on board the aircraft for that.
Once the aircraft and passengers are cleared to fly, it's time to pack up for the long transit flight from Armstrong Flight Research Center in California to the southern tip of Chile. The exhausted team gets an opportunity to rest on the overnight journey to Santiago, where a second flight crew is on standby to complete the journey to Punta Arenas.
To get to this part of the globe, it's about 14 hours of flying. We had pre-deployed a crew to Santiago to join the flight at that point so that the crew that flew all night could then step out of the cockpit and rest. And that allowed us to continue on that next day down to Punta Arenas, Chile, without having to stop overnight.
It's a cold and windy welcome at the Punta Arenas Airport, the mission base for Operation Icebridge. The scientists and flight crew will call this place home until the end of November.
We are setting up base stations here at the airport that record the GPS data for various instruments. We're talking to people in the weather office, at the tower, the air traffic controllers, and that typically takes about a day, getting everybody settled in here and preparing everything for the first science flight.
With 2 complete flight crews available, science flights are planned on consecutive days to collect as much data as possible over Antarctica.
On a typical Punta Arenas deployment, we have about 300 flight hours. And if we fly as much as we can, which we typically do, we kind of travel a distance in Antarctica that's equivalent to 3 or 4 times around the equator.
I think this is a glacier we're crossing.
Flight tracks are carefully designed by the Icebridge science team months in advance. Survey lines need to be precise, not only to make repeat measurements in exact locations, but also to ensure the plane keeps a safe distance from specially protected areas and animal habitats. A sophisticated guidance system on the DC-8 helps the flight crew keep the plane on track and navigate around more than 1,700 known wildlife locations on the Antarctic continent.
Some of the flights are hand-flown using moving map displays that have a flight track depicted on them. Others are guided by what's called the ATM instrument, where it actually puts out a signal that we feed into the aircraft navigation system, where it guides the airplane laterally.
So the ATM stands for Airborne Topographic Mapper. We designed a supplemental system to the ATM. Some people call it the ATM Navigator. What it does is it couples into the aircraft's own autopilot and helps it to steer the aircraft as accurate as we need it to be. We can generally steer the airplane well within 100 feet and often within 20 feet of where we want it to be. And that means that if you imagine a line that represents our desired track, more than half the time that line will lie within the cabin of the aircraft.
Antarctica's harsh and often unpredictable weather determines when and where the ice bridge team will fly each day.
I've got rising terrain, 12 o'clock, 7 miles.
Tally-ho. Tally-ho, and I'm going to start climbing here.
Pilots need perfect visibility of the terrain for safety.
We'll clear it. It does get steeper as we get closer to it, so we can pitch up a little bit.
Several science instruments need a clear line of sight between the aircraft and the ground to collect proper measurements.
Meteorology is obviously a very big deal with Ice Bridge. It essentially governs everything that we do on any given day. We have to fly down low and near the terrain in order for our instruments to work as they're optimally designed to work. So it means we need clear skies below the altitude at which we're operating in order to do this kind of work. We know from experience which parts of Antarctica are likely to have good weather and which parts are not. So we design the missions so that each of the missions has a maximum chance of success based on the likely weather scenarios.
We come up with about twice as many mission plans as we can possibly fly in the field. And that's simply so that we have enough target areas to choose from that have good weather while we are here in the field. And then we prioritize these plans.
We have to spend a very large amount of our time while we're in the field trying to sort of ascertain what the weather is going to do. It's a bit like reading tea leaves. It's a very inexact science. We depend entirely on what the meteorologists tell us through computer models. We talk a lot to the meteorologists here at the airport. They're terrific. They give us a lot of help.
The Chilean hosts provide everything from weather expertise to daily flight lunches for the Ice Bridge team. Airport firefighters and emergency responders are also prepared to help in case anything goes wrong with the aircraft.
So we don't use retread tires.
The DC-8 is not your typical airplane. Structural enhancements, new engines, and cutting-edge data systems make the aircraft a versatile, long-endurance platform for earth science research.
The DC-8 is uniquely capable for this kind of operation, mainly because of its long legs. It can fly for about 14 hours on a full fuel load.
We have to pretty much commute every day to Antarctica and commute back. And then we need also the capability of collect several hours of data. Typically on every flight we collect several terabytes of data all together. So we have 8 different science instruments on the aircraft, and in total it's a very complex set of measurements that we take over ice sheets, and doing it all at the same time in the same location from one airplane. It's really a tremendous resource.
It is amazing that a large airplane that was designed originally to be an airliner could be so diverse, but by its design, it meets a lot of the requirements NASA had set for the type of science studies they wanted to execute using an airplane to support. This particular airplane was built in 1969, but many of the systems have been upgraded over the years to keep up with current technology. For instance, the airplane has a satellite communication system on it, which something like that didn't even exist when it was originally built. So what's nice about that is we can move data real time during the flights off the airplane to people anywhere in the world via the satellite system and then the internet, and they can send us information real time as well. We can X-chat, it's like texting back and forth to each other. We can send photographs, we can send technical data. You don't have to actually be on the flight to participate.
My view of this airplane is that it's the ideal airplane for the kind of mission we use it for, because it's built very strong. And in the old days, when these were being designed and built, the airplanes were overbuilt to be on the safe side. We have a nickname for it. It's a DC-8, and the DC stands for Douglas Cable Car, because unlike the modern airplanes that use electronics and hydraulics to control the airplane in flight, this airplane is controlled with steel cables. So we do hurricane research, we fly through hurricanes, and we do a lot of different types of scientific research, and the airplane can take a lot of damage that would cripple other more modern airplanes, and this airplane still flies fine. It's like an old truck. It's solid and almost indestructible.
A wall of stickers at the mission director's console tells the story of the many missions the DC-8 has flown since it went into NASA's service in 1987. This aircraft and many others operated by the NASA Airborne Science Program fly thousands of hours every year all over the world to support a variety of Earth science research missions. It takes careful coordination and detailed planning behind the scenes to make these missions possible and to gain a better understanding of how our planet is changing.
In 1988, Dr. James Hansen, then director of NASA's Goddard Institute for Space Studies, stood before the U.S. Senate and testified that
global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. This last year, 2021, comes in as the 6th warmest year on record, and it continues this large, long-term warming that Jim Hansen was detecting even in 1988. And in 1988, that was also a globally warmest year, but now that ranks only 28th in the ranking. And so the warming that we've had since Jim Hansen's testimony has been dramatic and totally vindicates the concern and the warnings that he put out at that time.
the Goddard Institute for Space Studies, or GISS for short, maintains NASA's record of Earth's surface temperature, called GISS temp, that shows a clear and unequivocal increase in our planet's temperature. GISS temp stretches from 1880, long before NASA existed, until the present day. Now, when you think of NASA, you probably think of, well, space, right? And we do lots of work studying Earth from above. But the GISS temp record is actually built from the ground up. We collect measurements taken from weather stations, Antarctic research stations, and ships and ocean buoys all around the planet to understand what temperature changes look like globally. And why does the record start in 1880? That's the earliest period that we have sufficiently reliable measurements from ships and weather stations in enough places to be confident in the global record. Interestingly, it's also shortly after the time we call the Industrial Revolution, when humans started putting significant amounts of carbon dioxide in the atmosphere. But we'll get back to that later.
There are millions of measurements over the last 140 odd years. We put those together. We're using data from literally tens of thousands of different stations around the world. We use the information that's there to create a global picture of what's happening, and that gives us a very accurate estimate of how any year ranks, or what the anomaly is for any one year compared to what happened in the 19th century or what happened in the middle of the 20th century.
So we have our statistical reconstruction of Earth's recent climate, but in research science, we like to check our work. There are a couple ways we can do this. First of all, teamwork. Our colleagues at NOAA and at other agencies and universities around the world also create their own records, and we can line them up side by side and see just how closely they align. Everyone's independent climate records show the same thing. Earth is warming significantly and rapidly. And here at NASA, we have an even cooler way to check our work. space. Right now, we have more than 24 satellites dedicated just to studying our planet. Satellites can take measurements of the entire planet and line them up with our estimate of global temperature change. And sure enough, they also match. Our measurements from space match up well with what our analysis tells us. Earth's climate is warming. The next big question: why is our planet warming? Well, let's jump back to the Industrial Revolution. The release of carbon, mostly carbon dioxide, from human activities like driving cars, flying planes, and industrial burning of fossil fuels is responsible for the majority of climate change. Carbon exists in stores underground as oil, gas, and coal. When we burn it, we release it into our atmosphere, where it traps excess heat coming from the sun, raising the temperature. We've known for more than a century that carbon dioxide added to our atmosphere traps additional heat and is a major contributor to the greenhouse effect. So we can also track the concentration of carbon dioxide in our atmosphere, the primary cause of the current climate change. Both from space, using NASA satellites like the orbiting Carbon Observatories 2 and 3, and from the ground. If you've heard of the Keeling curve, you're familiar with one of these records. Researchers have been taking daily measurements of atmospheric carbon dioxide from Mauna Loa, Hawaii since the 1950s. From space and the ground, the signal is clear. There's a lot more carbon in the atmosphere than there used to be. Other things have changed too. We've chopped down tropical forests, caused the ozone hole, and filled the air with soot, smog, and other kinds of air pollution. And this is on top of natural variations caused by the dynamics of the ocean, or volcanoes, or variations in the sun's activity. And so we can ask whether it's human activities warming our planet. At NASA, we have some big and powerful computers, able to make 6.8 trillion calculations per second. We put these huge supercomputers to work to recreate Earth's climate. So we have thousands of ideas of what could naturally cause climate change. We have 4 billion years of history where nearly anything and everything you could imagine has impacted Earth's climate. But each of these events has their own distinct fingerprint, which we can identify, a pattern of behavior with natural variability. Using supercomputers, we can run simulations of natural climate drivers, solar energy changes, wobbles in Earth's orbits, ocean turnover, volcanic eruptions, and we can run simulations of human effects. And what we've seen is...
it's us. There's no way around it. Looking at the evidence, we're the force that's enacting these changes. I am so proud of our ability to understand the climate, but I'm terrified of what we found.
But it's not just the causes of climate change, it's also the effects. Because it's not just about knowing why our planet is warming. It's also about understanding and preparing for the effects of added warmth.
Measurement of global average temperatures is so important because it's one of the most direct indicators of Earth's changing climate. But the Earth is really a system of environmental systems: land, ocean, atmosphere, and ice, and changes in one system impact the others. Our oceans are our first line of defense in climate change because they absorb so much of the extra trapped energy in the Earth system.
We are seeing the impacts of climate change now. Now we know that as our climate warms, wet areas are getting wetter and dry areas are getting drier. For example, we see more intense snowstorms. We see slower hurricanes that are causing more precipitation that inundate land. And we have more extreme precipitation in the form of atmospheric rivers that come from the Pacific and reach our west coast.
The oceans are absorbing a large amount of heat because of climate change. And once that heat is in the ocean, it actually travels all around the planet because of the ocean currents. And that has impacts on local weather and long-term climate.
As the planet warms, it's not just the ocean that's warming, it's also the ice that sits in the ocean and on land. The ice on land being warmed increases melting, which is increasing freshwater input into the polar oceans and causing sea levels to rise across the globe.
So as the climate is changing, we really are seeing a lot of changes to the environment up in the Arctic. We're seeing more permafrost thaw when it's warmer up there. The warmer air temperature can lead to warmer ground temperature, and we get that thawing of that permafrost layer.
We're finding that the fire season is being exacerbated by longer periods of drought and decreased snowfall.
Knowing that our climate is changing due to human activities means that we know how to lessen the effects of future warming. And knowing how we know what causes climate change confirms that our efforts would be meaningful. The situation is serious, but it's not hopeless. Together, we can decide to make a better choice.
If they're going to make something that we don't know how to burn in a rocket engine, let's do some research. My name is Diane Linney, and I am working to build refineries and gas stations on the moon and Mars. One of the first things we need to do is we need to dig up our dirt. I was working my vegetable garden using a small rototiller. The dirt was very dry on top, but of course as soon as I tilled it up, I got some wet dirt. And I thought, wow, we're trying to harvest the water out of the soil on the moon and Mars to process it into something more useful. We get to play in our sandbox. We can measure how much soil went up into the scoop. Actually, I wanted to be a lawyer when I was in high school. My high school physics and calculus teacher said, you're a woman and you're really good in math and science, you should try engineering. Up until now, we've taken everything we need with us. We're trying to build gas stations and refineries so we don't have to bring all our propellant with us. Our ancestors called it living off the land. It's just a lot of fun that we get to try and push the technology and make new things.
It's extremely exciting. In my lectures, there are always young people in the audience, and they always want to know when they're bringing it back, you know. And I always say, I don't think ever. I think NASA, they realizes that they have two marks, so to speak, but somehow they can be made to coexist. We had to analyze what had been done by NASA in the past. Finally, we realized that we had to have a unifier, something that was very strong to hold it all together. So over the process of working on it, over the first month, I think we got simpler and simpler with our solutions so that it would work miles away on a T-38 or a rocket or a space shuttle. We were trying to embody in the logo innovation. The organization still had aeronautics as well as space, and so that you see a kind of nose cone design inside of the A's and propulsion, kind of upward thrust. Great simplicity, but still movement.
Roger, roll, Discovery.
The term worm came out of Florida in a newspaper down there, and it was meant to be derogatory, and I personally thought it was very derogatory. And eventually, over the years, the worm became a term of endearment, but it wasn't meant that at all in the beginning. When they started producing apparel a couple of years ago, they found out how young people in particular really like this program, and so they've allowed it to kind of come back to life on its own. It's validation, I think, of the sort of timeless approach that we brought to this. Space is about the future, and if we can still hang in there, and if it still represents that, then it's quite a victory, I think. Aesthetics aside, the goal was to do that, to hold up for decades, and apparently it's still it's got better legs today than it did then.
tropical regions are among the hottest and most humid places on Earth, but also the coldest and driest. Yeah, you heard right. While temperatures on the surface can range from 80 to 90 degrees Fahrenheit all year round, they can dramatically drop as you go up in altitude. In fact, as you get closer to the stratosphere, they can be as low as minus 110 degrees Fahrenheit. This extremely cold region between the troposphere and the stratosphere is called the tropical tropopause layer.
In the tropics, it's very warm and moist down here at the surface. When you get up to the tropopause layer, it's very cold and dry.
So it turns out that the tropopause is actually coldest in the western Pacific.
Right above Guam is an ideal place because it is the coldest and the driest part of the tropics.
Everything is ready for the second phase of the field experiment. We are 13 degrees north of the equator in the Pacific, our new home away from home for the next several weeks. We are in Guam.
So the tropics are the part of the planet that gets the warmest from the heating from the sun because it gets the most sunlight on average.
Because the surface is so warm and there's so much water, you evaporate water, liquid water becomes a vapor, so you have this very hot, moist air down here at the surface. So this is air that's got a lot of energy. And just like a boiling pot of water, it can rise very high.
And it tends to pull other gases that come from the surface up with it. So this is the part of the world where most of the circulation getting up from the surface up into the upper part of the troposphere and into the stratosphere, this is where it occurs.
So here in the tropics, we see these thunderstorms boiling up to very, very high altitudes, and so we have a very high elevated tropopause here in the tropics.
As you get convective processes going, the air rises. As you know, if you take air and you expand it, it cools really fast.
And it turns out that, in fact, the warmest places in the world are in the tropics, but about 55,000 feet above us, about 16 kilometers, is one of the coldest places on Earth.
So what that does is, as it cools really fast, all that water vapor in the air going up gets squeezed out. It's like wringing a towel, and all the water starts to squeeze out. So you get cloud processes formed, it squeezes out the water. The air that comes out the top tends to be dry.
You still get some water making it up to the tropical tropopause, and there the atmospheric motions transport air into the stratosphere. So air is transported into the stratosphere with a small amount of water that's left behind.
And this is the area that tends to be the controlling mechanism for how much water gets into the upper troposphere and then onto the stratosphere.
So if you want to understand the composition of the stratosphere, how much water there is, how much ozone-destroying substances or trace gases there are, you need to go to the tropics and study the region around the troposphere and the tropics.
So this is the spot to be. So this is the area where the ocean gets the warmest, the convection is the strongest, and then the air that comes out the top gets the coldest.
And we've known that for many decades, and for at least 20 years we've known we really need to go to the Western Pacific to study the extreme dehydration where the tropopause is coldest, and where the most extreme dehydration to low water vapor concentrations occurs.
Now, Guam is the coldest and driest part of the tropics.
It's actually a warm region at the surface and a cold region at the tropopause. And Guam is right in the center of action. Plus it has the airfields and facilities we need to operate our high altitude aircraft.
It takes a lot of work to plan a remote deployment of this size.
Yeah, preparing for a mission where we're deployed, where we have to take the entire team and the aircraft and all of our equipment, is really quite an effort.
Making sure we had a hangar available to us, making sure we had office space available, making sure that we had areas that we could set up our aircraft control trailer and our instrument control trailer.
It's also difficult because you're away from where you built your instruments, where you operate your aircraft. So if you have a problem, you have to ship everything here.
Because when you're this far from home, so to speak, you know, you got to have everything here. Not just the airplane and the people, but all your equipment, including spares.
Actually, all the work that's gone into this ATREX project has been one of the most difficult things I've ever done.
So when we operate out of Edwards Air Force Base, we operate from a fixed structure called the Global Hawk Operations Center. That's the main command and control center for the NASA Global Hawks.
Well, what's different from operating here in Guam versus operating back at Edwards is we have these mobile ground stations. So that's where we fly the airplane and operate our payloads from.
So the front room, the flight operations room, is replicated with a 40-foot trailer with all the communications equipment, all the computers, all the servers, everything. And then we have another trailer that replicates the 14 workstations that the payload operations room has, and that's in another trailer.
And we're basically providing the same functionality from Anderson Air Force Base in a forward location that we would have back at Edwards Air Force Base.
We can deploy anywhere in the world with these trailers as long as we have the appropriate setup.
Okay, that sounds like a good plan. So we're ready for aircraft.
For the ATREX campaign, the NASA Global Hawk is basing out of Anderson Air Force Base. And from Anderson Air Force Base, we'll be flying north all the way up to the Aleutians, east towards the Philippines, south down by Australia and New Zealand, and out to the east all the way to about Tahiti, the other side of Hawaii, basically. It's roughly about a 4,000 mile radius of range that the Global Hawk has here from here at Anderson Air Force Base.
We really have daily meetings. I know certainly the forecasters, the modeling group, and our pilots meet almost every day whenever we're getting ready for a flight. We are working every day on the aircraft, working with the scientists. They've got to pre-flight their instruments. After flight, they've got to post-flight their instruments. Some want to come off, some don't want to come off. So it's a constant ballet of activity around the airplane in between flights until the day when we're ready to go. Everyone comes on. We'll have engine start at 5 o'clock, which means they've got to come in at 11 o'clock at night, work till 2 a.m., do their thing with the instruments, and our crew comes in, buttons up the jet. It's rolling out at 4 o'clock. Engine start at 5, take off at 6. So it's an ensemble of people all doing really great work together to make this whole thing happen.
And FA72, we have a good power transition, good engine start.
And Trapper, can I get a takeoff report?
Yes, sir. Runway is clear. You're going for takeoff.
Roger that.
Three, two, one.
So the Global Hawk has great capability with tremendous range and endurance.
So many lessons learned from this campaign that will make our Global Hawk operation a much more globally deployable package.
And as we've demonstrated, we can do a lot of science from Dryden, California, or we can deploy, as we've illustrated here, to reach out. And I think we've shown now that we can really go almost anywhere in the world.
Because this is our first deployment away, really away from the mainland. This will be our first, it won't be our last, and we will be well suited to take our show on the road anywhere in the world from now on.
We're collecting data over the tropical Western Pacific, data that will improve our understanding of our atmosphere, weather, and climate. The Atrix mission will help us better comprehend the world we live in, to learn more about this planet we call home. Throughout many field campaigns, we've come a long way in expanding our knowledge and understanding of our atmosphere. But this hasn't been a one-person effort. Collaboration and close coordination within the Atrix team have made this endeavor possible.
For any field experiment you do, you have the questions that you're trying to answer, and then you figure out which data do you need to best answer the questions. Once you've done that, then you figure out who has the capability of making those measurements.
So basically what we've done is gathered the leading experts in theory, modeling of the atmosphere, and in making these very challenging measurements.
And that's the only way that you can really do science. You have to go to the right place and measure at the right time with the right people.
And part of the reason I really like these airborne science campaigns is they're sort of these grand endeavors where everybody comes out to the field, we're all working very hard with a common goal, and very thankful to have the opportunity to get these measurements. The other thing about these NASA campaigns is the data will then be shared with everybody. So it'll be used by people from all different countries.
The more people who use the data, the more of an impact our data have.
We're all basically working together, trying to understand how the atmosphere works.
The data we have gathered will be used to benefit humanity for many years to come.
When you make an observation, that's only the beginning of the story. It's like walking into a crime scene and taking a picture and collecting some evidence. Footwork begins after that, the real work of putting everything together to produce a full picture of what's happening in our atmosphere.
And Atrix is basically part of that puzzle. We're addressing a key uncertainty in how the models predict future climate change.
We have to actually figure out how all of these things work.
So the real underlying objective of ATREX is to understand climate change. Now, it's well known that climate change will have dramatic effects on people and ecosystems across the planet.
The atmosphere is always changing. Levels of gases are changing, temperatures are changing, and you have to make very precise measurements in order to try to see those changes.
So when satellites measure, they measure basically looking through the atmosphere over a very long path length, multiple hundreds of kilometers they're averaging the data over. So if you have low water and somewhat higher water, what you're going to measure there is the average. When the airplane flies through these air masses, they're measuring over 10s and 20 meters at a time, so they're getting that entire variability.
So far, we've gathered these fine structure measurements of clouds and water vapor and the interaction between water vapor and clouds, and that's being used to better understand how the clouds form and how they affect the amount of water that's getting in the stratosphere. The other thing we've done is we've gotten a lot of measurements of these ozone-destroying substances in the tropical tropopause layer, which will ultimately get into the stratosphere, so we can better predict how much of these get into the stratosphere and again improve predictions of ozone destruction and the ozone layer recovery.
All of these processes are the things that we're after with ATREX.
15 seconds.
After with ATREX.
15 seconds, one pass. SA-72 is off. Right. SA-72 switches 6.
The ATREX mission, we've seen some very, very interesting relationships between temperature, water, and particles that we're seeing in the atmosphere. This is really wonderful information and will be incredibly useful for how we can improve our modeling of the atmosphere.
But anytime you do climate science can be contentious in many parts of the world. So having data that is out there, free and open and defendable is important. If your data aren't available for everybody, it's always going to be in question.
The way we look at it from the science community is that the data is all shared. So it'll be shared amongst different institutions and different agencies and even different countries all around the world. Because we all have the common goal of trying to understand how the atmosphere is working and how the atmosphere is changing.
The scientists' understanding of the climate system and answering the key questions that can help resolve the uncertainties that decision makers have to make. It's key.
And so we'll still need measurements, and the measurements will improve and our understanding will improve, but we'll need these measurements to further quantify how the atmosphere is changing.
The more we understand the processes, the better off society will be because of it. And some of those key processes, the only way you're going to answer them are through airborne campaigns like the one we're doing here.
Our future very much depends on the understanding of the world around us, on how this complex system we call Earth changes. That's why our mission is not only about doing research, but also about encouraging younger generations. They are the future of science and the key to continue understanding and improving the lives of all of us who call this planet home.
The students do not normally have an opportunity to see this.
To show them that there's actually stuff beyond just looking at what's in a book is very invaluable.
It gives them meaning and relevance to the work that they do in school.
I can't stress it enough just how important it is for the students to make that connection, because that's where they make their decision as to what they're going to do for the rest of their life.
It's fantastic to have real scientists, real pilots, real engineers and technicians coming in and sharing their experiences with the kids, because that brings science to life.
So we are bringing our science into their classrooms, as well as bringing the students here to see our science in action. And we're hoping that this will inspire some of the students to pursue careers in science, technology, engineering, or math, and one day maybe even work for NASA.
I saw how excited the kids were, so it's awesome.